All right, people. I believe everybody is doing great, nice, and absolutely fine. Let me know in the live chat if I'm audible and visible properly. Everyone. With the fire symbols, the Josh has to be high, okay? Because in this marathon, we will be completing two chapters. The first one is magnetic effects of current, and the second one is magnetism and matter, okay? We'll be completing both the chapters in just one go. Everybody of you, I just need to know in the live chat if I am audible and visible properly with the thumbs ups, with the fire symbols over there. Great. Let's see how many hours, sir. Let's see. Okay. It will take approximately 7 to 8 hours because we have to complete both the chapters, two chapters in this particular one shot. And let the people join and we will start accordingly. Let the people join. Okay. Just a second, my dear people. So, how is everything going? Okay. So, guys, okay. So, in this particular chapter, as you guys know that we will be starting from the scratch, we'll be starting from the basics, okay? And I will be showing you every single problem pattern, okay? All the concepts we'll be talking about, okay? We do not leave the concepts, we do not leave the topics in any of the one shots. Same we will be doing over here also, okay? So, I hope the Josh is high from your end also. Okay. So, guys, okay, tell me, how many of you are following consistently this particular series? Okay, we have actually a lot of topics and I have put up every single problem pattern in this one shot. And we'll be covering all of those from the scratch, from the basics, okay? Now, I think we need to start. One of the student is saying, sir, potentiometer. Okay, when it comes to the potentiometer, that has been removed from your NCRT as well as from your NEET syllabus. So we don't have to learn NCRT. We don't have to learn the potentiometer. That's why I didn't touch it in the current electricity chapter. And because we are following the new pattern of the syllabus. Second point is, I have shown you the, we say, midpoint potential formula. By using midpoint potential formula, you can solve each and every single question, okay, without using the Kirchhoff's law. If you use Kirchhoff's law, it becomes very complicated to solve the circuits. Use midpoint potential and solve each and every single question, okay? So, guys, I think we need to start this particular chapter over here, okay? Okay, so from the scratch, from the basics, if you have not studied this chapter before, so this session is definitely for you, okay? Or if you have studied, then also this session is for you, because we'll be starting from the basics, we'll be starting from the scratch, and I'll take you to the level which you actually need in order to solve every problem pattern when it comes to your NEET, okay? So my dear people, let's basically start this particular session over here. The first topic that we need to discuss in this one, is basically, that is nothing but, we say, Biot-Savart's law, okay? When it comes to the magnetism, we say the first topic that we talk about is Biot-Savart's law, okay? Like when you have your electrostatics over there, the first topic is, that's what we say, the first topic over there is, we say, Coulomb's law. Over here you have Biot-Savart's law. Okay. Great, great, great, great, great, great. Just a second, let me fix up the lighting over here. Okay. So, guys, now let's start this particular session over here. Let me just show you the first topic that we need to talk about over here in this magnetic effects of current. That is nothing but we say Biot-Savart's law. Okay. Now, what does this Biot-Savart's law actually say? Or we say magnetic field due to a current carrying element. What does it actually mean? Listen to me very, very, very carefully. We are starting the session, all of you, with the Josh, with the high Josh, I must say. Let's suppose I say I have over here, this is a wire, okay? This is a wire over here, okay? And in this wire, we say, let's suppose current I is flowing. I current is actually flowing in this particular wire that I have over here. Now, what I am doing is that I'll take a magnetic compass, okay? This is a, let's suppose this is a magnetic compass, okay? I am taking a magnetic compass. I'll place it near to this wire. This wire is over here. I current is flowing in this wire. We are placing a magnetic compass over here near to the wire, okay? And when we saw that this needle of magnetic compass is a device which is used to detect the magnetic field, okay? So when we saw the needle of this magnetic compass, it starts deflecting. It starts deflecting over here. We place the magnetic compass at this particular point. Over here also it starts deflecting. What does that mean? I'll just write over here. If we place a magnetic compass, if we place a magnetic compass near to the current carrying wire, okay, current carrying wire, we say the needle starts deflecting. The needle starts deflecting. Sir, what does that mean? See, I am just saying simply I took a current carrying wire. I have a wire over here and I placed it over here, okay? And near to it, I am placing a magnetic compass. Magnetic compass is a device which is used to detect magnetic field, which is used to find magnetic field at any particular position, okay? So we say the needle starts deflecting. What does that mean? It means that, sir, magnetic field is being produced over here. It means that magnetic field is present at this particular point. So we say current carrying. So we say current carrying wire produces, we say magnetic field around it, okay? So my dear friends, I have a wire over here. In this wire, current is flowing. Sir, I took a magnetic compass, I placed near to the wire. And I observed that the needle of the compass is deflecting. What does that mean? That means, sir, magnetic field is present over here. Now, who is creating that magnetic field? We say, sir, this wire is creating that magnetic field. So can we say, sir, from now onwards, if in a wire, current is flowing, it creates the magnetic field around it 110%, sir. Okay. So this wire in which current is flowing creates the magnetic field around it. Now, if I say the simple question over here, from this wire, if we go at r distance, from the wire, if we go at r distance at this particular point, we say, sir, magnetic field is present. Can we find the value of that magnetic field? How much magnetic field is present? That value was given by Biot-Savart's law. So Biot-Savart's law tells us how do we find the magnetic field at a particular point because of a current carrying element over here. Okay. Now listen to me very carefully. Now I'll just write over here to find that magnetic field, if we have to find that magnetic field, okay, like, sir, what is a magnetic field? Magnetic field, like, sir, what is an electric field? Let me just tell you exactly over here. Just a second. Let's suppose we have a charge Q over here. Sir, we say around this charge, electric field is being produced. As simple as that. Now, let's suppose we have a magnet over here. Sir, around this magnet, we say magnetic field is present. Yes, sir. Let's assume it for a second. And if we place a piece of iron or a coin over here, it gets attracted. Like if we place a negative charge over here, it gets attracted. Similarly, sir, in this magnetic field, if we place a coin, it gets attracted. That's what we call the magnetic field in simple words. In simple words, as simple as that. Now, if we have to find the magnetic field at this particular point, because of this wire, we use Biot-Savart's law. We use Biot-Savart's law. Now, listen to me very carefully. How do we exactly find this magnetic field over here? Everybody of you, okay? I am starting from the scratch. I'll be showing you every single problem pattern which has the chance to come your examination. Now, listen to me very carefully, my dear friends. Let's suppose I have this wire over here. And in this wire, we say, sir, current I is flowing, okay? And we have to find the magnetic field at r distance because of this wire, okay? Sir, we know a current carrying wire produces a magnetic field. So, what does Biot-Savart's law say? Biot-Savart, okay, he was basically a physicist. He said, if you have to find the magnetic field at this particular point, what you guys are supposed to do is, you take a small current element over here. Call that current element, let's suppose a dl. I'm assuming that the length of the wire is capital L, and if we are taking a small current element over here, sir, what will be the length of that current element? We say, sir, that will be dl, okay? Now, first of all, he said, you find the magnetic field because of this small current element. I know the wire current is flowing in the entire wire, but I'm saying that you take a small current element and find the magnetic field due to this small current element. Now see over here, we say, sir, magnetic field, we represent magnetic field with B. Magnetic field due to we say small current element. Sir, magnetic field due to the small current element will be small because magnetic field due to the entire wire is large. We say, sir, magnetic field due to a small current will be small. As simple as that. So we say that magnetic field over here will be simply, sir, that will be dB. Sir, dB means small magnetic field. B means large magnetic field. So, sir, we say that dB, small magnetic field, is proportional to, listen to me very carefully. It is proportional to, sir, IDL. Sir, what is this IDL? IDL is basically the current element, small current element. Sir, DL is the length and I is the current in that particular element. Okay, I know I is the current in the wire, but over here in this element also current is I. So this current element is what we call the IDL, that is small current element. If we say only small element, then DL. If we say small current element, then we say IDL. Now you tell me one thing, sir, we say if this IDL is large, if this magnitude of IDL is large, we say, sir, magnetic field due to it will be large. As simple as that. And most importantly, sir, this Biot-Savart's law says that, sir, this magnetic field due to a small current element is proportional to IDL, okay? Now, we say, sir, this magnetic field dB is inversely proportional to R square, as simple as that. Sir, if you go away from the wire, if you go very far from the wire, we say magnetic field decreases. Like if we have magnet over here, at this distance, magnetic field would be large. But at this distance, magnetic field would be small. If you go away from the magnet, magnetic field will keep on decreasing, my dear friends. Now, we said dB is inversely proportional to R square. People, do not confuse yourself over here. dB is the magnetic field due to the current element. Okay? Okay. Now, listen to me. So, one more thing is over here. Sir, we say angle between this ideal. This is what we call the ideal, and angle between this ideal and this R is nothing but theta. Angle between ideal and this R is nothing but theta. And experimentally, it has been seen that, sir, this dB is also proportional to sine of this angle, sine of this angle. If you keep on increasing this angle, we say magnetic field will increase over here. Now, if we combine these three equations, we say, sir, dB is proportional to, simply we say, sir, IDL. Then we have sine of theta because dB is proportional to this, dB is proportional to this. Then we have over here R square. Now, if we replace this proportionality with a constant, we say, sir, dB is equal to, we replace with a constant, that is mu naught by 4 pi. And then we have, sir, IDL. Then we have sine of theta divided by R square. This is the magnetic field. This is the magnetic field due to a small current element at this particular point. So we say this is the magnetic field. We say due to a small current element at r distance, as simple as that. Okay, and this is what we call the Biot-Savart's law. So can we say from now onwards, Biot-Savart's law tells us, Biot-Savart's law or Biot-Savart's law helps us to find we say magnetic field due to a small current element, due to a small current element at a particular point, and that magnetic field will be equal to mu naught by 4 pi IDL sine theta by R square. Okay, as simple as that, where we say this mu naught is what we call the permeability of free space. Like you have epsilon naught in electrostatics. Epsilon naught is what we call the permittivity of free space. Over here, this mu naught is permeability of, we say, free space. Okay, so from now onwards, what is Biot-Savart's law? So that's why I said this is magnetic field due to a small current carrying element. So Biot-Savart's law helps us to find the magnetic field due to a small current carrying element. Is that clear, my dear friends? In the live chat, I just need to know. In the live chat, everybody of you, I just need to know in the live chat, is it clear with the fire symbols? Is that clear, my dear people? With the fire symbols, is it clear to each and everyone? And if you have not liked the session, like it as soon as possible, okay? Okay, that is mandatory. Marking the attendance is mandatory. Everybody of you. Everybody of you, mark the attendance in the live chat. Okay, great. So now, so this is basically the magnetic field due to a small current carrying element. Okay, now this is the scalar form. If we talk about the vector form, listen to me very carefully. We say vector form of Biot-Savart's law. Let's talk about the vector form of Biot-Savart's law. Listen to me very carefully. Sir, this dB we can write over here. This dB is equal to, we say, sir, mu naught divided by 4 pi. Mu naught by 4 pi. Then we have over here IDL. Then we say cross R. Then we have IDL cross R divided by, we say, sir, R cube. This is the vector form of Biot-Savart's law. What does vector form mean? Vector form means this will give you the value of magnetic field. Let's suppose if we have a current carrying wire over here. Sir, in this current carrying wire, you have to find the magnetic field at this particular point. we say this one. Now over here, you take a small current carrying element that is ideal. Because of this ideal, it will produce the magnetic field over here. So, sir, that magnetic field is having the magnitude as well as the direction, because magnetic field is a vector quantity. So this formula gives you the, we say, magnitude as well as a direction, I will tell you how to find the direction of the magnetic field. Just wait for a second. Okay. This will give you the magnitude as well as the direction. Okay. So this is the vector form of Biot-Savart's law. This is that form which tells you the magnetic field due to a current carrying element in we say vector form. We say its magnitude as well as its, we say, direction. As simple as that. Okay. Now, and this was basically asked in NEET 2020, I guess. Okay. This vector form of Biot-Savart's law was asked in NEET 2020, I guess. Now listen to me very carefully. If we have to find the direction of this magnetic field, okay, direction. How do we find the direction? How do we find the direction? How do we find the direction of magnetic field? Okay. Listen to me very carefully. Let's suppose we have a wire over here in which current I is flowing. We have a wire over here in which current I is flowing. And it produces the magnetic field over here. And we have to find the direction of that magnetic field. Listen to me very carefully. You have this thumb over here, okay? Place your thumb along the direction of current. Place your thumb along the direction of current. Current is going in the upward direction, okay, in this case. So I'm placing the thumb along the direction of current. And if I have to find the magnetic field at this particular point, I will curl my fingers at this particular point. If I am curling my fingers, it is going in the inward direction. It is going in the inward direction. Place your thumb something like this and curl it. It is going in inward direction. If it is going in inward direction, means over here magnetic field will be inwards. Okay, magnetic field will be inwards. So how do we find the direction of magnetic field? Let's suppose we have a wire over here in which current I is flowing. Okay, and you guys are supposed to tell me the magnetic field at this particular point because of the current. In this particular case, we say, sir, current is going in the downward direction. Place your thumb along the direction of current. Then curl your fingers. This is my right hand. Okay, this is my right hand. I'm not using my left hand. Use your right hand. We say, sir, curl your fingers at this particular point where you have to find the magnetic field. It is going in outward direction. So means at this particular point, magnetic field is, we say, outward. As simple as that. Sir, how do you write inward? Inward means cross and this dot means outward. This dot means outward. Is that clear, my dear friends? Right hand thumb rule. Is that clear, my dear friends? Simply place your thumb along the direction of current, then curl your fingers. That will give you the direction of the current. And if you have to find the direction of current, a magnetic field from this side, from the left side over here, how do you do it? Sir, this is my right hand. Place your thumb along the direction of current and then curl your fingers over here. It is going in the outward direction over here. So we say in that case, sir, magnetic field from this side would be outwards. As simple as that. I hope you would be able to find the direction in every single case from now onwards. Okay, my dear people, let's talk about the next concept we have over here. Let's talk about the next concept we have over here. That is magnetic field due to a finite current wire. Okay. See. What does Biot-Savart's law say? Sir, Biot-Savart's law says us the magnetic field due to a current carrying element. But if we have to find the magnetic field due to entire wire, sir, how do we find that? Listen to me very carefully. We say here, current I is flowing. Here I is flowing. Here I is flowing. Here I is flowing. We say through the wire. Here I is flowing through the wire. If current flows through the wire, can I say it produces the magnetic field? So it produces, we say, magnetic field. And we have to find that magnetic field at point P, which is at our distance from the wire. Sir, can we use Biot-Savart's law? Yes. We'll find the magnetic field due to a current carrying element over here, and then we'll do the entire derivation, and afterwards the value what we get, that's what I'm gonna write over here. See. Previously, Biot-Savart's law tells us the magnetic field due to a current carrying element. But over here, we have to find the magnetic field due to the entire wire. Sir, how much that will be? Listen to me very carefully, my dear friends. Listen to me very carefully, my dear friends over here. See, we say, sir, magnetic field due to this entire wire would be, sir, that is B is equal to. That is nothing but we say mu naught divided by 4 pi. Mu naught by 4 pi. Then we say, how much is the current flowing in this wire? Sir, that is I. Write I over here. Divided by, sir, where do we have to find the magnetic field? We say, sir, at R distance, write R over here. And then we say, sir, sine of. Listen to me very carefully. If I take this point, from this point to this end of the rod, this is one end of the rod, and this is another end of the rod over here. So we say this angle is what we call theta 1, and this angle is what we call the theta 2. Okay. So we say sine of theta 1 over here, plus we say sine of theta 2 over here. This will be the magnetic field due to this entire wire at this particular point. Okay. This is, sir, how do you get this? We have to do the entire derivation, and finally we get this result. I'm writing directly over here. Okay. So we say magnetic field due to this entire rod at this R distance from the wire is how much? Mu naught by 4 pi. Mu naught is the permeability of free space divided by 4 pi, and I divided by R, sine of theta 1 plus sine of theta 2. This is the magnetic field due to the entire rod. Okay. Due to the entire wire over here, we say. This is the magnetic field due to the entire wire over here. I hope this is clear to each and everyone, my dear friends. Now, let's suppose I give you the question something like this. See. Sir, we have a wire over here, and in this wire current is flowing, that is 2 ampere current. And we are supposed to find the magnetic field at this point, which is 4 meters away. This is 4 meters away. And this angle is theta 1, that is 30, theta 2 is 30. Sir, we know magnetic field is how much? B is equal to, we say mu naught by 4 pi. Then we have I by R, okay? I is the current in this one divided by R. And then we say, sir, sine of theta 1 plus we say, sir, sine of theta 2 in this case. Sine of theta 1 plus sine of theta 2 in this case. Okay, yes. So, can we write, sir, this B is equal to, we say, mu naught upon 4 pi. And what is the value of I over here? That is 2 in this case, sir. That is 2 ampere upon. What is the value of R in this case? That is 4, 2 by 4 over here. Then we say, sir, sine of, what is the value of theta 1, my dear friends? That is 30. We say, sir, 30 plus we say sine of 30 over here. Because theta 1 is 30, theta 2 is 30. And we can say, sir, this magnetic field is nothing but, sir, this will be sine 30 is 1 by 2 plus 1 by 2, it becomes 1. So 2 1s and this becomes 2 2s 4. Sine 30 is 1 by 2. So this is mu naught by 4 pi. This is 1 upon 2 and this is 1 by 2 plus 1 by 2. Because sine 30 is 1 by 2 and it becomes 1. And I can write over here, sir, 1 by 2 I can write as 0.5. And the value of this mu naught by 4 pi is 10 raised power minus 7. Remember this, my dear friends, from now onwards, okay? Like we have F is equal to K Q1 Q2 by R square. Over there, value of K is 9 into 10 raised power 9. Over here, value of this is 10 raised power minus 7. So we say, sir, this B is equal to, this will be 1 and this is 0.5. Instead of 1 by 2, I am writing 0.5 into, we say, 10 raised power minus 7, and this will be Tesla. We measure the magnetic field in Tesla. This will be the magnetic field in this particular case. Is that clear, my dear friends? Is that clear? Each and every one? I just need to know in the live chat with the fire symbols, everybody of you. Okay, let's move on to the next one. Magnetic field due to an infinite long wire. If we have a wire which is infinitely long, okay, we are supposed to find the magnetic field because of this infinitely long wire. In this particular case, you just tell me one thing. Sir, if we have an infinitely long wire and we are supposed to find the magnetic field at this point, now if I do one thing, if I join this wire, if I join this point with one end of the wire, can I join it something like this, sir? No. Why? Because the end of this wire is not over here, but the end of this wire is at infinity. So I cannot join this wire over here, but I have to join this wire. If I have to join this wire at infinity, means I have to make this line parallel. Over here also I have to make this line parallel in order to join it at infinity. This is the same case which I have told you in the electrostatics also. Now in this case, my dear friends, sir, can we say, sir, this will be nothing but this is theta 1 and this is nothing but we say, sir, theta 2. Yes. So clearly we can see over here, sir, theta 1 is equal to 90 degree and theta 2 is also equal to 90 degree over here. Yes, theta 1 is 90 and theta 2 is 90. Now, if we have to find the magnetic field due to this wire at this point, sir, we know the general formula. What is general formula? Let me just tell you. Sir, when it comes to the general formula, this is the general formula. Sir, mu naught by 4 pi, I by r, sine of theta 1 plus sine of theta 2. This is the magnetic field due to this wire at r distance. Okay. Now listen to me very carefully. Sir, we can use the same general formula. B is equal to mu naught upon 4 pi. Then we have I divided by r. Then we have sine of theta 1. We say, sir, sine of theta 1 plus sine of, we say, sir, theta 2. This is basically the general formula. So can I just write over here, sir, B is equal to, we say, mu naught upon 4 pi. Then we have I divided by r. And in this case, how much is theta 1, sir? That is 90. We say sine of 90 over here. Plus, what is the value of theta 2? We say sine of 90 over here. Okay. Sine 90 is 1, sine 90 is 1. So this is B is equal to, we say, mu naught upon 4 pi. And then we say I divided by r. 1 plus 1 is, we say, 2 over here. There are 2 1s and 2 2s. So magnetic field would come out to be mu naught I divided by 2 pi r. So we say this is the magnetic field due to infinitely long wire at r distance. Is that clear, my dear people? In the live chat, I just need to know. In the live chat, everybody of you, is that clear? Is that crystal clear? So this is the magnetic. See, simply, in case of infinitely long wire, we say theta 1 is 90 and we say theta 2 is 90. Directly remember it. Okay? Is that clear? Next, we have over here this. That is magnetic field due to a semi-infinite wire. Sir, what is semi-infinite? Semi-infinite means if we have a wire over here, this is a wire, okay? And from this end, it is going till infinity from one end. Like we have this. Sir, this is going till infinity from upper side. This is going till infinity from lower side. From both the ends, it is going till infinity. We say it is completely infinite wire. But when it comes to semi-infinite wire, we say it is going till infinity from one end and other end is finite. And we are supposed to find the magnetic field at this point at r distance. R distance, I'll just write, okay? R distance in this particular case, okay? Yes, sir. Yes, sir. Now, you guys tell me one thing, my dear friends. That is nothing but, see, if we have to mention the theta 1 and theta 2 over here, sir, in order to write the theta 1 and theta 2 over here, just take the line, and this will be something like this. Now, sir, if I have to join this point with this end is at infinity. So I have to make the line parallel, something like this. So we say this would be theta 1. And in this case, sir, theta 1 is 90 degrees. It is clearly visible to every one of us. Okay. Sir, when it comes to another angle, sir, the next angle is join this end with the another end of the rod. Another end of the rod is over here. Clearly we can see, sir, theta 2, this is the angle between this point and another end. Theta 2 is 0 degrees, okay? Because this line is parallel over here. So we say, sir, over here in this case, theta 2 is 0 degree. So in case of semi-infinite rod, we say semi-infinite wire in which current is flowing, we say theta 1 is 90 and theta 2 is 0 degrees. Now if we have to write the magnetic field, we say, sir, magnetic field B is equal to, write the general formula. Sir, what is the general formula? Mu naught by 4 pi. Then we have I divided by R. Then we say, sir, sine of theta 1 plus we say, sir, sine of theta 2. This is the general formula. Okay. Now, my dear people, sir, if this is a general formula, let me just write over here. This is the magnetic field due to a finite wire at r distance. Okay. And this is the general formula. Okay. Which is applicable to all the cases. Sir, what are the cases? This is the case number 1, infinite. This is the case number 2, semi-infinite. Now, write it over here, sir. B is equal to, we say, sir, mu naught by 4 pi. And then we say I divided by R. I is the current which is flowing in this one. R is the distance where we have to find the magnetic field. And then we say sine of theta 1. Sir, what is theta 1 over here? That is 90. We say, sir, sine of 90 plus. Sir, theta 2, what is the theta 2 over here? That is sine of 0 degrees over here. As simple as that. Now, sine 0 is 0. Sine 90 is 1. So, magnetic field would come out to be, that is mu naught I divided by 4 pi R. Mu naught I divided by 4 pi R. As simple as that. As simple as that. Mu naught I divided by 4 pi R. Okay. So this is the magnetic field due to a semi-infinite wire at r distance. Is that clear, my dear people? In the live chat, I just need to know if that is clear to each and everyone. If that is clear to each and everyone. Okay. You have this next question over here. You have this next question over here. Now you guys are supposed to tell me in this particular case, sir, magnetic field due to this wire at this particular point. Okay. And this angle in this case is given as alpha. This angle is given in this case alpha. And this distance from this rod to this point is basically R. This is the point P. Okay. We say to find magnetic field at point P. To find the magnetic field due to this wire in which I current is flowing at point P. This is going till infinity from one end. Can you guys tell me in the live chat? Can you guys tell me in the live chat? See. Listen to me very carefully. This is a semi-infinite rod, but over here this angle we don't have to take it 0. See, if we move on to the previous one, over here if this is a semi-infinite rod, sir, one end is going till infinity. That's why we took theta 1 is equal to 90 degree. Another end is over here in front of this point. So that's why we took the angle theta 2 as 0 degrees. Now, my dear people, listen to me very carefully in this case. Sir, if we have to join this end with one end, sir, it is going till infinity. So means in this case, theta 1 is 90 degree. Clearly we can see. We say, sir, theta 1 is 90 degree. Clearly we can see. Now, sir, join this point with another end of the rod. Another end of the rod is over here. One end is at infinity, another end is over here. And it is making heat alpha with this r distance. It is making angle alpha. So we say over here, sir, this theta 2 is alpha. Now, listen to me very carefully. Sir, if we have to write the magnetic field, we know the general formula, that is mu naught by 4 pi. Okay. And then we say, sir, I divided by r. And then we have sine of theta 1 plus we say sine of theta 2 in this case. Sir, we say this magnetic field B is equal to mu naught divided by 4 pi. And this is I divided by r. What is the value of theta 1 in this case? That is sine of 90. Sir, we say sine 90 plus. What is the value of theta 2? We say, sir, sine of alpha in this case. Sine 90 is 1. So we say, sir, this magnetic field would be mu naught by 4 pi. Then we say I by r. And then we say over here 1 plus sine of alpha. This would be the magnetic field in such case. This would be the magnetic field over here. This is the magnetic field due to this wire at point P, which is at r distance. Is that clear, my dear friends? Is that clear in the live chat? Let me know. Is that clear? Let me know in the live chat, guys. Great, great, great, great, great. With the fire symbols, every one of you. Okay, okay, okay, okay. Nice, nice, nice, nice, nice. Let's move on to the next one. Okay. Let me just give you the question something like this. This is a question which I have over here. The question is basically, this is the question. You guys are supposed to tell me the magnetic field, at point P. Okay? You guys are supposed to tell me the magnetic field at point P. We have a current carrying wire in which I current is flowing, and you are supposed to find the magnetic field at point P. But over here, this angle is not given, this angle is not given. In this case, this angle alpha is given, this angle beta is given. Can you tell me what is the value of magnetic field? What is the value of magnetic field at this particular point? What is the value of magnetic field at this particular point if alpha and beta are given in this case? Can you tell me, guys, in the live chat? See, let me just tell you over here. See, sir, when it comes to this upper triangle, if you take a look over here, let's assume this is theta 1 in this case. We don't know how much is theta 1. We are assuming, okay? It is not given in over here. We don't know theta 1. In previous cases, it was given theta 1 is the angle, theta 2 is the angle. But over here, we are assuming it is theta 1. Now, listen to me very carefully. We say, sir, this angle is 90. If we take a look at the upper triangle, sir, this is 90, this is alpha, this is theta 1. And we know sum of angles in a triangle is how much? That is 180 degree. Now we say, sir, that would be this angle is theta 1 plus this angle is alpha, okay, plus this angle is, we say, sir, 90, okay. Sum of all the angles in a triangle, sir, it is equal to, we say, sir, 180 degrees. We have studied this in 8th class. Now, sir, can we do one thing? Take this 90 over there, take this alpha over there. So theta 1 would be, sir, 180 minus 90 minus, we say, sir, alpha. Sir, 180 minus 90 is 90. So theta 1 would be, sir, 90 minus alpha. So we got the value of, sir, theta 1, that is 90 minus alpha. Now, can you find, let's assume this has theta 2. Can you find this theta 2, sir? This is also 90 in this lower triangle. Sir, from this triangle also, we can say, sir, theta 2 is 90 minus this beta, Now, use the formula. Sir, what is that? Sir, we know the formula B is equal to, we say, sir, mu naught by 4 pi. Then we say I by R. This is R and this is I. And then we say, sir, sine of, we say, sir, theta 1 plus, sir, sine of theta 2. This we have studied. This you have told us before. Now, in this case, we say, sir, this B is equal to simply mu naught by 4 pi. And this is I by R. And theta 1, what is the value of theta 1? 90 minus alpha. So this is sine of, we say, 90 minus alpha. Okay. And then we say sine of clearly 90 minus beta over here, because theta 2 is 90 minus beta. And we know, sir, sine of 90 minus alpha is cos alpha. So B is equal to mu naught by 4 pi. And this would be I upon R. Then we have, this is nothing but cos of alpha plus, we say, sir, cos of beta in this particular case. So this is the magnetic field. This is the magnetic field due to this wire at, we say, point P. Is that clear, guys? Is that clear? Okay. Let's talk about this question over here. Let's talk about this question. Can you guys tell me the answer of this question? Everybody, before I do it, you guys are supposed to solve it, okay? Before I do it, you guys are supposed to solve it. That is mandatory. That is mandatory. Before I do it, you guys are supposed to solve it. That is mandatory. Everybody of you. As simple as that. As somebody is writing in the comments in the chat, as simple as that. Yes. Okay. Now, let me just show you over here. Sir, can you find the, if I say, let's assume, if I say, sir, this is theta 1, if I assume this is theta 2, can you tell me the value of theta 1, sir? That is 90 minus alpha. Alpha over here is theta. Alpha over here is, sir, this 30. So that is 90 minus 30. Sir, what is this theta 2? We say, sir, this theta 2 is simply, that is 90 minus 60. We say, sir, 90 minus 60, as simple as that. Sir, how much this will be? Theta 1 is 90 minus 30, that is 60. Sir, this is nothing but theta 2 is 90 minus 60 is, we say, that is 30. Now, use the formula for magnetic field. B is equal to mu naught by 4 pi. Then we say I divided by R. Then we say sine of theta 1. We got the value of theta 1, that is 60. Sine of 60 plus sine of, we say, sir, how much? That is 30. Sine of 30, because theta 2 is 30 in this case. Okay. Now, over here, we can simply solve it. Put the value of sine 60. Put the value of sine of 30 over here, and you'll get the value. You'll get the answer in this particular case. Is that clear, my dear friends? Let me know in the live chat, everybody of you. Is that crystal and clear? Okay. Okay. Done. This would be root 3 by 2 plus 1 by 2, and then solve it. That's it. Okay. B is equal to, that is mu naught by 4 pi. Then we say I by R. Sine 60, we say, sir, root 3 by 2 plus we say, sir, 1 by 2 over here. Plus we say 1 by 2 over here. Plus we say, sir, 1 by 2 over here. Now, let's move on to the next question. You guys are supposed to tell me, I have got over here, this is a very good question. This is a very good question. This is a very good question in this case. Now see, we have got over here a square, okay? This square is made up of 4 wires. This is the first wire, okay? This is the first wire in which current is I. This is the second wire in this current is I. This is the third wire over here, current is I, and this is the fourth wire, current is I. You guys are supposed to tell me the magnetic field at this center. Find the magnetic field at the center. Because of this square, because of these 4 wires, you guys are supposed to tell me the magnetic field at the center. Length of the wire is basically L. It is given as L. See, in order to find the magnetic field, at this center, listen to me very carefully. We say here, this square is made up of 4 wires. Here, this square is made up of 4 similar. All of these wires are similar, identical. Similar wires, okay? So we say all of these 4 wires are similar or identical, okay? Now, if we find the magnetic field, because of one wire, we can find the magnetic field due to rest of the 4. Sir, listen to me very carefully. If I say, sir, this is the direction of current over here. This is the direction of current. Can you tell me, because of this, magnetic field at center will be in what direction? In which direction? Sir, you have told us one rule. That is nothing but place your thumb along the direction of current and curl over here. If you are curling over here, it is going in inward. So because of this wire, magnetic field over here is inward. Now, if we talk about this wire, sir, because of this wire, Magnetic field at center is also inward. Yes, sir. Now, because of this upper wire, if you place the thumb along the direction of this upper wire, along the direction of current, sir, that is also inwards. Because of this wire, magnetic field is inwards. Now, because of this wire also, my dear friends, you see clearly, place your thumb along the direction of current and curl your finger. This is also inward. So means in this case, we say, sir, magnetic field net due to all the wires will be, we say, sir, that is B1. Magnetic field due to first wire, plus we say, sir, magnetic field due to second wire, plus we say magnetic field due to third wire, plus magnetic field due to fourth wire. All of these are inverts. That's why I am adding all the magnetic fields over here. And all the magnetic fields will be similar. Now, let's find, I'll just write over here, let's find the magnetic field. Let's find a magnetic field due to one wire, Let's find the magnetic field due to a single wire. We got the magnetic field due to a single wire. We will multiply it with 4 and we'll get the magnetic field due to all the 4 wires. Let's take this particular wire over here. We'll find the magnetic field because of this wire in which current I is flowing. We are supposed to find the magnetic field at center. Listen to me very carefully. Sir, join one end of the rod with this point. Sir, join another end of the rod with this point. And from this point to this point, let's suppose this length is, we call R. My dear people, listen to me very carefully. It is something like this. We have a wire. At this point, R distance, we are supposed to find the magnetic field. And join this point with one end. This is θ1. So over here, this is θ1. Join this point with another end. Sir, this is what we call the θ2 over here. Okay. Now, in case of square, we say, sir, this angle and this angle, they are 45 because net is 90 degrees. This angle in the square is 90 degrees. You might have studied. So we say here, clearly we can see in this particular case, sir, θ1 is equal to 90 degrees. We say, sir, θ2 is equal to 90 degrees over here. Yeah, right. Someone is here. Everybody, welcome. Okay. All the people in the live chat, show some josh.
Exactly, guys. There has to be josh in the chat. What's up? How are you all doing? Yeah?
Waseems are in the house.
Yo.
How
is it going, guys? How's it going?
It's going awesome, huh? Where have you been?
Wonderful.
Where have you been till now?
Okay, so it's a long marathon today, by the way, right? I was discussing with Yawar sir like 2 hours back. He was like, he'll take 8 to 9 hours today. And I believe he'll take more than that.
We have to complete 2 chapters today.
What all chapters?
Magnetic effects of current and magnetism and matter.
Nice.
Both the chapters.
Should I be asking certain questions? Okay. I hope all of you have joined that test series which I gave you yesterday, right? That free test series. I hope you have enrolled in that. The free test series whose video I took yesterday. If not, do it right now. That's one amazing test series, people.
That's free, yeah?
That's completely free of cost.
Okay.
Completely free of cost. So that is particularly for the subject chemistry. In coming days, you will get one for physics, one for bio as well. There are 8 tests and all the tests I have created, okay? All the questions I have given to the team. Perfect. That's great. Shall you guys carry on? I'll see you in my next marathon. And you know what is the marathon? That is going to be thermodynamics, right? So who's looking better right now? By the way.
Who is more smart?
Who's smarter? Huh? Ignore my hair. Who's smarter?
Everyone in the live chat.
Yes, everyone. No, don't say both. Not the answer. Both is not the answer.
Okay.
No. You cannot. This is a bluff.
Wasim sir only, huh?
Someone is saying absolutely you, sir.
Okay. Now let me continue.
Chalo, you guys carry on. See you guys. Take care. God bless you all. Bye-bye.
İzbaş. Gdzie będziesz się? Mr. Izwina. Now see guys over here. See, in this particular case, sorry, not 90 degrees, I made a mistake. Theta 1 is equal to 45 degrees, theta 2 is equal to 45 degrees. Sir, we say theta 1 is equal to 45 degrees and theta 2 in this case is we say 45 degrees, okay? Total is 90, 45 plus 45 is 90 over here. And if we say, sir, this length is L, this length would be how much? We can simply say this would be L. Sorry, this is also L, this is also L. And this length will be till the center. This is, we say, sir, L divided by 2. Half of this length, that is L by 2. Now, if we use the formula B is equal to, sir, mu naught by 4 pi. And then we say I by R. Then we say sine of theta 1 plus we say, sir, sine of theta 2. This is the general formula we have been using till now. Now, in this particular formula, what we can write over here, my dear people, let me go a bit fast over here. Sir, B is equal to, we say, sir, mu naught upon 4 pi. Then we say I divided by R. Now, in this case, what is the value of R? R is the distance from that point till the wire. That is L by 2 over here. So we can say, sir, this is L by 2. And sine of theta 1 is 45 degree plus sine of theta 2, that is also 45 degrees I can write over here. Now we can say, sir, this magnetic field B is equal to, we say, sir, mu naught by 4 pi. And this is 2 1s, 2 2s. Let me just write it. So this would be mu naught I upon 2 pi L. And sine 45 is 1 by root 2. And this is 1 by root 2. 1 by root 2 plus 1 by root 2 becomes 2 by root 2 over here. This 2 and this 2 will get cancelled out. So we can write this is mu naught I divided by, we say, sir, root 2 pi into L. This would be the magnetic field due to one single wire. We can further simplify it. Just do one thing, multiply it with root 2 and divide it with root 2. Now, over here, my dear people, I can say in this case, just keep it as it is as of now. So this is the magnetic field due to one wire. Now, we can say, sir, magnetic field due to this wire, we got it, okay? If we have to find the magnetic field due to rest of the 4 wires, all the 4 wires are creating the inward magnetic field. So we say, sir, net magnetic field due to all four, okay? We say, sir, all the 4 wires will create the same magnetic field at the center because the length is same, distance is same, everything is same. So we say that would be simply, sir, B net is equal to, due to 1 wire, it is this much. Due to 4 wires, it is 4 times of, we say, mu naught I divided by a root 2 pi into L. Now, multiply with root 2 and divide with root 2. Sir, this root 2 and root 2, so it would be 4 mu naught I divided by root 2 into root 2 becomes 2. When you multiply root 2 with root 2, it is 2. And this would be pi and this is L. And in the numerator also, it is root 2. 2 1s and 2 2s. So, sir, B net, I can simply write over here. That would be 2 root 2. That is 2 root 2. This is mu naught I divided by pi into L. So this is the magnetic field. So this is the magnetic field due to the square at the center, due to all the 4 wires at the center. Is that clear, my dear people? Let me know in the live chat if that is clear to each and everyone, all the people out there. When I ask you to give me the signal in the live chat, it means that every student out there is supposed to send me the thumbs up or the fire symbol, whatever it may be, because I need to get the signal from each one of you. Okay? Great, great, great, great. So this is the magnetic field due to a square shaped wires, whatever you call it. Remember this expression, okay? Remember 2 root 2 mu naught I divided by pi L. 2 root 2 mu naught I divided by pi L. And because we have to solve a lot of questions on this one, and the second one I would want you guys to remember is this one. That is magnetic field due to infinitely long wire, that is mu naught I by 2 pi r. And magnetic field due to the semi-infinite mu naught I by 4 pi r. Okay? All these expressions you guys are supposed to remember because we have to solve out so many questions over here. This is the first question. This is one more question on this also. Now see, over here, we say, sir, this is an infinitely long wire. We have got one more infinitely long wire over here. This is infinitely long. This is infinitely long. Now, my dear people, in this particular case, listen to me very carefully. We say in this wire, 5 ampere current is flowing. Sir, in this wire, 2.5 ampere current is flowing. And distance between the two wires is 5 meter. You guys are supposed to tell me the magnetic field because of the both wires at this center. At this center. Find the magnetic field at the center due to the two infinite long wires. In this wire, 5 ampere current is flowing. In this wire, 2.5 ampere current is flowing. Every one of you, let me know in the live chat. Everybody. Every one of you, let me know in the live chat what is the answer over here. What is the answer over here? Everybody over here. My dear people, let me know. Everyone means everyone. Yes. See. We say, sir, magnetic field over here. Listen to me very carefully. When it comes to the direction, sir, because of this wire, place your thumb along the direction of current and curl your fingers. Magnetic field due to this wire is over here. We say, sir, inward. Now, sir, when it comes to the magnetic field due to this wire, place your thumb along the direction of magnetic field. This magnetic field is outward. Sir, magnetic field due to this wire, let's call that wire 2. This is wire 1. So B1 is inward. We say, sir, B2 is outward. Okay. Now, sir, we say over here, net magnetic field would be, because of this wire, magnetic field at this point is inward. Sir, let's call that B1. And because of the second wire, magnetic field at this point is outward. So we say B1 minus B2. If both the magnetic fields would have been in the same direction, then we would have added them. But we are subtracting because the direction is opposite over here. As simple as that. Now see, sir, magnetic field due to this wire, we say, sir, B1. Magnetic field due to infinitely long wire. How much is that? I just told you, when it comes to the infinitely long wire, magnetic field, this is semi-infinite. Magnetic field due to the infinitely long wire, that is mu naught I divided by 2 pi r. So I can write it over here. That is nothing but mu naught I divided by, we say, sir, 2 pi, and that is r. And in this case, we say, sir, current is flowing, that is I1, that is 5 ampere. Let's call this as I1. And then we say minus, we say, sir, mu naught. Then we have over here in this wire, sir, current flowing is I2. We say, sir, mu naught I2 divided by 2 pi into r, because this is also the infinitely long wire. Now, clearly we can see in this case, sir, this B1 is equal to, sir, mu naught by 2 pi r. Take this common, sir, mu naught by 2 pi r. And then we have over here I1 minus, we say, sir, I2. Sir, what is r? R is, see, distance between them is 2r. That is 5 meters. Sir, how much is this r? R will be 2.5. So this magnetic field, we call this as net magnetic field. This is not B1. This is net magnetic field. I can write this as B net. Okay. This is B1. This is B2. And this is, sir, B net in this case. So we say, sir, this B net would be simply mu naught by 2 pi. And r is how much? R is given as 2.5. 2.5. Okay. And then I1 minus I2. I1 is given as 5 minus I2 is given as 2.5. So if I just write it over here, see, 5 minus 2.5 is 2.5. And this 2.5 and this 2.5 will cancel out. So B net in this case would be simply, that is mu naught by 2 pi. Mu naught by 2 pi. Is that clear? Is that clear, my dear people? Is that clear, my dear people? Let me know in the live chat if this is clear to each and everyone. Okay, great. Let's move on to the next question. This is the next question on your screen. A straight wire of finite length carrying current I subtends an angle 60 degree at point P. The magnetic field is, see, it is something like this. Let me just show you. It is something like this. You have got a triangle something like this. Just a second, I'll make it. You have got a triangle something like this. And in this particular triangle, this is the angle made by this wire. This is a triangle, but this is the wire only. Okay, don't consider these wires. This is a length from this point to this point, and this is given as x and this is given as x. This is the wire only, and this is the angle 60 degree in this particular case. Okay, and this is the point P over here. You guys are supposed to find the magnetic field at this point P because of this wire. How much is the magnetic field because of this wire at this point P? Since current is flowing in this wire, so it will create the magnetic field. So we have to find the magnetic field because of this wire at point P. Okay, this is the question. This length is given as x, this length is given as x. Now, can you tell me the answer of this question? And if I join this point with this one, if I join this point with this one, we say, sir, over here, we say, sir, over here. This would be what we call R. This would be what we call R. At R distance at point P, you guys are supposed to tell me the magnetic field. Listen to me very carefully. Sir, if this is whole is 60 degree, how much theta 1 would be in this case? Let's call this as theta 1 and let's call this as theta 2, the next angle. So we say, sir, theta 1 is 30 and theta 2 in this case is, we say, sir, over here, we say over here 30. Because when you join this point with one end, it is making angle 30. When you join this point with another end, it is also making angle 30. Total is 60 degrees. And over here, listen to me very carefully. Can you find the value of this R? Because we are assuming this as R. We don't know how much it is. We know this distance X. How to find this R? Now from this particular triangle, this angle is given as 30 degrees. This angle is given as 30 degrees. Can you tell me the value of cos of 30 degree? Sir, cos 30 is nothing but, some people have curly black here, base upon hypotenuse. Base is how much? That is R. Hypotenuse in this triangle, this is base. This is hypotenuse. Don't say this is base because we are taking this as angle. So this would be base and this is hypotenuse. Hypotenuse is X. And cos 30 is root 3 by 2. So we say this is a root 3 by 2 is equal to R by X. And in this case, sir, R would come out to be, that is root 3 by 2 into X. Root 3 by 2 into X. This distance we got in terms of X, that is root 3 by 2 into X. I hope this is clear. Now, my dear people, can we use the general formula now? Sir, what is the general formula? B is equal to mu naught by 4 pi. Then we have I by R. Then we have, we say, sir, sine of theta 1 plus we say, sir, sine of theta 2 in this case. Sine of theta 1 plus we say sine of theta 2. How much is theta 1? That is 30. How much is theta 2? That is 30. How much is R? That is given over here. Now I can write, sir, B is equal to, we say mu naught by 4 pi. Then we say I divided by R. What is the value of R? That is root 3 by 2 into X. Sine theta 1 is 30, that is 1 by 2 plus sine theta 2, that is also 30. Now this 2 ones and this 2 twos 4. So how much it will come out to be? Sir, B is equal to, we say mu naught. B is equal to mu naught by 4 pi. Then we say I divided by, this is 2 pi root 3x. We say 2 pi root 3 into x, 2 pi root 3x. And then we say 1 by 2 plus we say 1 by 2. 1 by 2 plus 1 by 2 is 1. So this magnetic field would be mu naught by 4 pi. Then we say I upon, over here, I upon, we say 2 pi root 3 into x. Just a second. Mu naught by 4. Sorry. I made a mistake over here. Sorry. Just let me write it once again. See, this is mu naught by 2 pi into root 3x. Mu naught by 2 pi into root 3x, and this is I, and this would be 1, because sine theta 1 by 2 plus 1 by 2 is 1. So the answer would be simply mu naught I divided by 2 root 3 pi into x. 2 root 3 pi into x. Mu naught I divided by 2 root 3 pi into x. Option number 1. Is that clear? In the live chat, let me know, guys. Is that clear? Guys? Everyone, is that clear now? Okay. Okay, great. Okay, let's move on to the next question. Okay, this is the next question. See. In this case, we have a wire. The wire is from this point to this point, okay? The wire is from this point to this point. You guys are supposed to tell me the magnetic field at point P. Listen to me very carefully. See, this is not the wire. From this end to this point, it is not the wire. This is just a line. Wire is from this point to this point only. And you have to tell me the magnetic field at point P because of this wire. You have to tell me the magnetic field because of this wire at point P. How much is the magnetic field at point P because of this wire in which current I is flowing? Can you let me know in the live chat? See, how do we solve this particular question? Let me just do one thing. I'll take from this point to this point, I will join it with one end, okay? I'm joining this point with one end of the rod. Clear? And I call this angle as, listen to me very carefully, I call this angle as theta 1. Because when you join one end of the rod with the point P, we call that angle as theta 1. Let's suppose we have this point. If we join it with one end, we call this as theta 1. This point, we call this as theta 2. And my dear people, if we join the same point with another end of the rod, this is the another end of the rod, we call this angle as theta 2. Like if we join this point with another end of the rod, we call this angle as theta 2. Okay? And this angle has to be between R and that line. See, this angle is between R and that line. See, this angle is between that line and this is R over here. The next angle is also between that line and R over here. Means we are doing the 100% correct method. Okay? We are doing the right approach over here. Now see, how do we write the magnetic field in this case? We don't have to go in the much depth. I'll tell you the formula and directly remember it. We say, sir, over here, magnetic field would be. Magnetic field in this case would be. Sir, this is nothing but mu naught by 4 pi. And then we say, sir, I divided by R. I divided by R. This mu naught by 4 pi is a constant. Yes, sir. Sir, I is the current flowing in this wire. Yes, sir. R is the distance from that wire till the point. Perpendicular distance. This is the perpendicular distance. Now, my dear people, listen to me very carefully. Then we say, sir, sine of theta 1. Sir, what is the theta 1 over here? This is theta 1. Then we used to say, sir, plus sine of theta 2. But in this case, we say, sir, minus sine of theta 2 over here. Some minus sine. Why? Because we say, sir, when you see this rod is till over here, from this end to this end, the rod is present. So means if you are taking the magnetic field because of the entire rod, this is the entire angle, that is theta 1. So you have to minus theta 1 minus theta 2. What you are supposed to do is minus this theta 2 from theta 1. Then only, that's why we are subtracting from theta 1, that is theta 1 minus theta 2. Or simply, guys, if it is messing with your mind, what I'm trying to say is that rod is from this point to this point only. So that's why I did theta 1 minus sine of theta 2. Okay? We don't have to go in much depth over here. Just remember it as simple as that. As simple as that. Okay? Is that clear? Is that clear? Is that clear, guys? Is that clear, guys? Over here, rod is still here only. That's why we are doing theta 1 minus theta 2. Whole minus this much. Whole minus this much. Yes. Directly, you guys remember it over here. Now see, let's suppose current I is flowing over here. Let's suppose current I is flowing over here in this one. And the same current goes over here, that is I. And the same current goes over here, this I. You guys are supposed to tell me, we have a semi-infinite wire. We have another semi-infinite wire. They are meeting at this particular point. I current is flowing in the semi-infinite two wires. You guys are supposed to tell me the magnetic field at point B, which is at R distance from this wire and which is at R distance from this wire also. This angle is given as 45 degree. This angle is given as 45 degree. Can you tell me the magnetic field at point B? Can you tell me the magnetic field at point B? Because of these two semi-infinite wires. Can you tell me? See. Let me just show you over here. Listen to me very carefully, my dear people. We say in this particular case, sir, net magnetic field is equal to. This is wire 1. Sir, because of this wire 1, at this particular point, let's call the magnetic field B1. Sir, because of this wire 2, magnetic field at this is, let's call that, sir, B2. So we are adding B1 plus B2. Why, sir? Because magnetic field due to this, at this particular point is inward. Place your thumb along the direction of current, curl your fingers, it is inward. Sir, because of this wire, magnetic field at this point is also inward. That's why B1 plus B2. That's why B1 plus B2. Now let me just show you this magnetic field. We'll find magnetic field due to one wire and multiply it with 2 because they are similar identical wires. At this is also R distance, this is also R distance. This is 45, this is 45. So we say if we find the magnetic field due to 1, so we can multiply it with 2 and we'll get the net magnetic field. So we say wire 1 and wire 2 are similar. So they will create same magnetic field. Okay, they will create same magnetic field. Now let me just show you this case. I'll take it over here. Let me just show you over here. Listen to me very carefully. It is something like this. I have a wire over here, okay? And from this wire, this is the point which I am taking, and this wire is going till infinity. This wire is going till infinity. So it is going till infinity. And in this case, sir, this angle, if you join one end of the rod with this point, we are supposed to find the magnetic field at this point. This angle is given as 45 degree. Now, my dear friends, if you join this end with one end, This angle is given as theta 1 is 45. Now, if you join this point with another end of the rod, how you are supposed to do that? Sir, that will be if you take the rod line as parallel, because then only they will meet at infinity. And in this case, clearly we say, sir, theta 2 is 90 degrees over here. Now, this is R, this is R. Can you tell me, sir, how much is the magnetic field due to this wire at this point? Sir, that magnetic field is mu naught I divided by 4 pi R, 4 pi R. R is the distance at which we are supposed to find the magnetic field. And then we have sine of, what is the angle 1? That is 45 degrees plus, we say, sir, sine of second one is 90. Sine of 45 degree plus sine of 90 degree. So we say this B is equal to mu naught I divided by 4 pi R, and sine of 45 degree plus sine of, we say 90 degree. Sine 45 over here is 1 by root 2, and plus this sine 90 is 1 in this particular case. Okay. And this is the magnetic field due to one wire. This is the magnetic field due to this wire at this point. Similarly, sir, magnetic field due to this wire also would be another end. This is also 90 degrees. So this would be same. So we say magnetic field due to both. We can write over here magnetic field due to both would be, that is B net is equal to 2 times of, this is mu naught I divided by 4 pi R, then we say 1 by root 2 plus 1 over here. Is that clear, my dear people? Is that clear, my dear people? Let me know in the live chat if that is clear to each and everyone. Is that clear? Guys, if you have not liked this session, I want every one of you like it as soon as possible. Is it crystal and clear, guys? Is that crystal and clear, guys? Let me know in the live chat. Guys, like this session as soon as possible. If you have not liked the session, like it as simple as that. As soon as possible. Now see over here. Let me show you one more question in this particular case. Sir, this question over here on the screen is find magnetic field at the center. You guys are supposed to find the magnetic field because of this structure, okay? This structure is made up of six wires, okay? In this wire, current is flowing. In this wire, current is flowing. In this wire, current is flowing. In this wire, current is flowing. In this wire, current is flowing. This is what we call the hexagon. So you guys are supposed to tell me the magnetic field net at the center. How much will be the net magnetic field at the center because of this structure? How much will be the net magnetic field at the center because of this structure? That's you guys are supposed to tell me. Net magnetic field at the center. Now see, my dear people, in this case, see, sir, if we find the magnetic field because of one wire, okay, this is an identical, this wire is, they are having the same length, okay? Okay. So we say magnetic field due to all the wires at the center will be same because they are identical wires. And direction of that magnetic field is also same. See how? Let me just show you. Sir, if you place your thumb along the direction of this current, curl your fingers at the center, it is going in the outward direction. Means magnetic field due to this at this point is outward. Sir, magnetic field due to this. Place your thumb along the direction of current and curl your fingers over here. This is also going in outward direction. Now, magnetic field because of this wire at the center, it is also going in outward direction. Now, let's see because of this. Sir, magnetic field because of this at this particular point is also going in the outward direction. Okay. So magnetic field due to all the wires over here will be outward. So we say if we find the magnetic field because of one wire, we can find the magnetic field because of rest of the wires. Okay. We can find the magnetic field because of the rest of the wires. We will multiply it with the 6. So we say magnetic field due to one wire, Let me take this particular wire over here. Sir, we say in this particular case, this angle is 30 degrees and this angle is over here 30 degrees. Okay. So we say this is 30, this is 30. Now, listen to me very carefully. Sir, if this is 30, this is 30. Can you tell me from this triangle, sir, cos of 30 degrees, how much? See, this length is L. If the side of hexagon is L, this length is also L. But we don't know this particular length. This is the R. This is R. Let's find this R. Sir, cos 30 is how much? That is base by hypotenuse. That is R by L. And this would be root 3 by 2. So we say, sir, R is equal to L cos of 30 if you multiply it over here. So this R would be simply L cos 30 is, we say, root 3 by 2. L root 3 by 2. Okay. This is what we call the R over here. And we know theta 1, we know theta 2. So we can say magnetic field is mu naught by 4 pi. Then we say I divided by R. And R is how much? And then first we'll write the formula sine of theta 1 plus we say sine of theta 2. This is the general formula. So we say B is equal to mu naught by 4 pi. Then we say I upon, what is the value of R? That is L root 3 divided by 2. And sine of theta 1. Sir, we say, sir, theta 1 is 30, sine of 30. Plus we say, sir, sine of 30 because this is also 30. 2 1s and 2 2s over here. Sir, B will come out to be mu naught I divided by 2 pi root 3 into L. 2 pi root 3 into L. Then sine 30 is 1 by 2 plus we say, sir, this is 1 by 2. 1 by 2 plus 1 by 2 is 1. So magnetic field due to this wire would be, sir, mu naught I divided by 2 pi root 3 into L. 2 pi root 3 into L. 2 pi root 3 into L. Now see, in this case, sir, magnetic field, this is the magnetic field due to one wire. Due to rest of the 6 wires will be multiply it with 6. So now magnetic field due to all 6 wires would be, we say, sir, that is being net is equal to 6 multiplied by, this is because of one wire. So if you have to find the magnetic field due to 6 wires, that would be magnetic field, that is 6 into mu naught I, that is 6 into mu naught I divided by, we say over here, 2 pi root 3 into L. That is 2 pi root 3 into L. Further also you can simplify it, okay? Even if you multiply it with the root 3 and this would be, sir, root 3. Multiply and divide with root 3. Root 3 into root 3 becomes 3. So this is 6 mu naught I divided by, we say, 2 pi L. 2 pi L. Root 3 into root 3 is 3. And this would be root 3 in the numerator. 3 1s, 3 2s. This 2 and this 2 would cancel out over here. So this would be mu naught I or root 3 mu naught I divided by pi into L. This is the net answer over here. Is that clear? Is that clear, my dear people? Is that clear? With the fire symbols in the live chat, everybody of you, this is the final answer. After doing all the calculations over here. Is that clear, my dear friends? Okay, this is the magnetic field due to this particular structure over here. The magnetic field due to this particular structure over here. Now see, my dear people, listen to me very carefully over here. Listen to me very carefully over here. See, we have a wire, and in this wire current is flowing I. This is going till infinity from one end, and you guys are supposed to tell me the magnetic field at point P such that this point P lies along this wire. This point P lies along this wire only. See, this point is not over here, but it lies along the wire only. It lies along the wire only. And you have to tell me the magnetic field at this particular point because of this wire. Okay. Now see, remember in this particular case, that is nothing but we say magnetic field would be 0 over here. Whenever the point lies along the wire only, whenever the point is on the axis of the wire, we say magnetic field is 0. We say whenever the point lies along the wire, then we say magnetic field is 0. Magnetic field is 0 at that point, okay? Magnetic field is 0 at that point, because we cannot define the perpendicular distance over here. Or simply remember magnetic field is 0. Simply remember magnetic field is 0 whenever the point is along this axis. Now if I say, sir, we have this wire, this is semi-infinite. It is going till infinity from one end. Another end of the wire is over here. And we have another wire, that is second wire. It is also going till infinity from one end. You guys are supposed to tell me the magnetic field at point P because of both the wires. To find, we say magnetic field at P, we say because of both the wires. Because of both the wires. You guys are supposed to tell me the magnetic field at point P because of both the wires. Now, clearly you can see over here, sir, this point lies along the axis of this wire 1. So we say, sir, magnetic field at this point because of the wire 1 would be 0. Sir, we say magnetic field due to wire 1 is 0. Why? Because the point lies along its axis. And sir, this point for this wire 2 behaves like this behaves as a semi-infinite wire. Let me just show you. Sir, it is something like this. And this is our distance. Sir, this is point P. Tell me one thing. Sir, if you join this point with one end of the rod, that is going till infinity, so you have to make the line parallel. So we say in this case, theta 1 is, we say, sir, 90 degrees. Okay. And if you join this point with another end of the rod, that is over here, sir, that is at this point. So we say theta 2 will be 0 degrees. Okay. Because this end is in front of that point. That's why we're taking theta 2 as 0. Now, how much would this is exactly the case of semi-infinite wire. Sir, where is the semi-infinite wire? See, in case of semi-infinite wire, sir, one end is 90, one angle is 90, another end is 0, another angle is 0. Sir, magnetic field is mu naught I divided by 4 pi r. Similarly, we can say over here by using the same approach, magnetic field at this particular point. Sir, we say magnetic field at this, or just right over here, sir, B2, magnetic field due to this wire 2 at this point is nothing but mu naught I divided by 4 pi and r. Is that clear? Is that clear? And that would be outwards, and that would be outwards. Okay, that would be outwards. Okay, so net magnetic field, we can say, sir, B net is equal to, we say, sir, B1 plus B2. Sir, B1 is 0. This is mu naught I divided by 4 pi r. And this is outward. Is that clear, guys? Is it crystal and clear? Okay, this is the next question. There is a tsunami of questions today. That's why I told you every single question, every single pattern of question I will be showing you. Next question on your screen. Next question on your screen. All the people out there. Okay. Now, can you tell me in this particular case, what is the net magnetic field at the center? See, I say over here, this structure is made up of 6 wires. This is the first one, this is the second one, and this is the third wire, this is fourth, this is fifth, and this is sixth. So if I ask you to tell me the net magnetic field at the center, means you guys are supposed to find magnetic field because of the 6 wires. We say this structure is, we say, made up of we say 6 wires. We say 6 wires. Okay. Now listen to me very carefully. See, these 2 wires are very close to each other. Assume that over here I have shown you in order to make you understand, okay? But they are very close to each other. Now we say, sir, this wire 1, first wire. Sir, if we talk about this point P, we say, sir, this point P lies along the first wire only. So can we say in this particular case, listen to me very carefully. We say, sir, magnetic field due to we say wire 1 is 0. Why? Because this point lies along its axis. This point is along the axis, on the axis of this wire. Similarly, sir, magnetic field due to we say wire 2 is also 0. Why? Because this point is also along this axis of this wire. Sir, it does not look it is along its axis. See, it is along its axis. Why? Because I am saying that these 2 wires are very close to each other. So we can assume that this point is along the axis of this wire 2 also. So we say in this particular case, we say, sir, magnetic field due to this wire 1 at point P, magnetic field due to this wire at point P is 0 because point P lies on their axes, That's why. Now, sir, rest. It is this wire. This is a square, sir. Sir, we know because of the square, how much is the magnetic field? You just calculated it. Because of the square, how much is the net magnetic field because of the square? Sir, because of the square, net magnetic field at the center is 2 root 2 mu naught I divided by pi into L. Sir, same would be here also. Yes, same magnetic field would be in this case also. So we say, so B net would be due to the square. So that is, sir, magnetic field due to this one plus this one plus this one plus this one. So that magnetic field is how much? Sir, due to a square, it is 2 root 2 mu naught I divided by pi into L. Let me check it once again if I have not made any mistake. Mu naught I, 2 root 2 mu naught I divided by pi into L. Yes, that is absolutely correct. Is that clear, guys? Let me know in the live chat. Yes, you have to consider only 4 over here. Because due to the 2 wires, first and second, magnetic field would be 0 at center. Is that clear, guys? Okay, great. Now, let's move on to this question. Can you tell me the net magnetic field at the center? Can you tell me the net magnetic field at the center because of this structure? Can you tell me the net magnetic field at the center because of this structure? Every one of you. Guys, if you have not liked the session, like it as soon as possible, okay? That is mandatory. That is mandatory. What is the net magnetic field at the center? What is the net magnetic field at the center in this case? Over here, 2I current is entering this structure and 2I current is leaving this structure. Let me write the options over here. Option A is 2 root 2 mu naught I divided by pi L. Option B is root 2 mu naught I divided by pi. Option C is 0. Option D is mu naught I divided by pi L. Which option is the correct option over here? Which option is the correct option over here? A, B, C, D. All the people out there, let me know in the live chat. Every one of you. Maximum number of people are saying option number C. Option number C is the correct option. Net magnetic field at the center is 0. Absolutely great. Great, great, great. Net magnetic field at the center is 0. Let me show you how. Let me show you how. See, sir, clearly we can see in this particular case, magnetic field at the center would be because of this entire structure. So this entire structure is made up of first wire, second wire, third wire, fourth wire, fifth wire, and sixth wire. So this structure is made up of 6 wires. Now, we say, sir, magnetic field due to first and 4. Magnetic field due to first and fourth wire is 0. Is 0. At P. P is the center. P is the center. Okay. Why? Because this point is along the axis of this wire and this point is along the axis of this wire. Yes, sir. Yes, sir. 110%. Now see, now the magnetic field would be because of this second wire, third wire, fifth wire, and sixth wire. Listen to me very carefully. Sir, magnetic field because of this second wire. Listen to me very carefully. Place your thumb along the direction of current and curl your fingers at this point. So it is going in the inward direction. It is going in the inward direction. So magnetic field due to second is inward. And magnetic field due to third is also inward. Third is along, this is the direction of the current in the third wire. Now curl it, it is also inward. So we say over here in this case, sir, magnetic field due to second and third wire is inward. Okay. Yes, sir. Similarly, sir, when it comes to the magnetic field due to sixth wire, place your thumb along the direction of current and curl over here. It is going in the outward direction. So we say magnetic field due to we say sixth wire, and we say, sir, in this case also due to fifth wire, it is also outward. Due to this wire is outward. My dear people, magnetic field because of this and this is inward. Magnetic field because of this and this is outward. Can we say net magnetic field would come out to be 0 because they will cancel each other? So B net at center is 0. Is that clear? Is that clear, guys? Is that clear, guys? Is that clear, guys? I have shown you so many questions in this. I don't think now if any type of question comes to you from this portion of magnetism, I don't think you guys can, you guys will leave that question from now. I don't think so. Okay. Now we have this new topic. This new topic is magnetic field on the axis of a current carrying loop. Magnetic field on the axis of a current carrying loop. Guys, if you have not liked the session, as soon as possible, like it, okay? Now see. Till now, we were saying that we have a wire, and in this wire, sir, current is flowing. It is producing the magnetic field around it, okay? So this was a straight wire, straight conductor. What we will be doing right now is that we'll take a wire, but this wire is circular in shape. This is a circular loop, or we call it current carrying loop. Sir, this current carrying loop also creates the magnetic field. Yes, whenever the current flows in the wire, it produces the magnetic field. We say here current is flowing. Here current is flowing in the loop. Here current is flowing in the loop. So it will create the magnetic field. So it will create the magnetic field. Whenever current flows in the wire, be it loop, be it a straight wire, it will create the magnetic field. Now the point is, if we say, sir, current I is flowing in this particular loop. If we say, sir, current I is flowing in this particular loop, okay? So we say over here, let's suppose I is the current which is flowing in this loop. You guys are supposed to tell me the magnetic field at this point P. So I say to find the magnetic field at point P. We have to find the magnetic field at point P. Okay? We have to find the magnetic field at point P. Is that clear, people? Is that clear? Is that clear, guys? We have to find the magnetic field at point P. Now, that magnetic field at point P would be, listen to me very carefully, guys. You have to remember this general expression because we will be solving so many questions on this one. So that magnetic field at point P would be B is equal to, we say, sir, mu naught. Then we say, sir, I. Then we say, sir, R square upon. Sir, what is mu naught? Mu naught is mu naught. Sir, what is mu naught? Is permeability of free space. What is I? I is the current which is flowing in this wire, in this loop. Sir, what is R? R is the radius of the loop. R is the radius of the loop. And sir, what is this X? X is at what distance we are supposed to find the magnetic field. That distance at which we have to find the magnetic field from the ring, from the wire. So mu naught I into R square. Then we say 2 into, we say, sir, R square plus X square. 2 into R square plus X square. And then we say whole raised power 3 by 2. 2 into R square plus X square. Then we say whole raised power 3 by 2. This is the magnetic field. This is the magnetic field because of a ring. This is the magnetic field because of a ring at this distance at point P, which is at X distance from the center. Okay. Now, if I ask you the simple question over here, what is that, sir? If I say at center, how much is the magnetic field? Sir, at center, from point P, if you move towards the center, means you are decreasing X. Once you reach center, sir, at center, we say X is equal to 0. So we say, sir, at center, X is equal to 0. So we say, sir, this magnetic field B is equal to, that is mu naught I, and then we say R square upon, then we say 2 into, we say, sir, R square plus. And when it comes to the center, how much is the value of X? That is 0. And then we say 3 by 2. So this would be, sir, that is mu naught I into R square divided by 2 into this square, and this square will get cancelled. And then we say 2 into what remains over here, that is R cube. This R square and this cube will get cancelled because see, 2 are from the upper side and 2 are from the lower side. So it would come out to be mu naught I divided by 2R. So we say, sir, magnetic field because of a circular loop at the center is how much? Mu naught I by 2R. You have to remember it from now onwards. That is nothing but mu naught I by 2R. So we say at center. So at center, we say magnetic field is mu naught I divided by 2R. This is the magnetic field at center. This is the magnetic field at center. Okay, now. At center, it is not 0. Guys, why are you mentioning 0? Why are you saying 0? Magnetic field due to a ring at center is 0. But when it comes to the electric field due to a ring at center, that is 0. Magnetic field due to a ring is at center is not 0. Now see. Now we talk about if. Listen to me very carefully. Sir, magnetic field due to a circular loop at point P is how much? Mu naught I into R square, 2 into R square plus X square whole raised power 3 by 2. Okay. Can you guys see it? Is it visible to each and everyone over here? Is it visible, guys? Okay. Now listen to me very carefully. We say, sir, magnetic field due to a circular loop at point P is mu naught I into R square, 2 into R square plus X square whole raised power 3 by 2. Sir, at center it is mu naught I by 2R. Sir, the next case is what? Magnetic field due to a ring, which is magnetic field due to a ring very near to it. Listen to me, I'll just write over here. Magnetic field very close to the ring. Listen to me very carefully. Sir, let's suppose this is a ring over here. This is a ring. Let me make the ring over here. Let's suppose this is the ring I am having exactly over here. Okay. And this is the radius of the ring. This is the radius of the ring. Yes. And I am supposed to find the magnetic field at this distance, Okay, this is X. This is X over here. This is, sir, X. And this is what? This is R. This is the radius of the ring. This is R. Sir, we are supposed to find, if we say, sir, current in this case is flowing I, we have to find the magnetic field because of this ring, which is at that point, which is very close to the ring. Not very far from the ring, but very close to the ring. Sir, very close to the ring is that case in which X is much less than capital R. It is that close that this radius becomes very large in comparison to this X. So we say, sir, use general formula. That is how much? That is mu naught I into R square divided by 2 into, we say, R square plus X square whole raised power 3 by 2. Sir, when X is much less than R, in that case, we say, sir, if we see, X is very small. We are adding very small quantity to the very large quantity. If you square the very small number, if you square a very small number, it becomes more small. If you square a large number, it becomes more large. You are adding very small number to a very large number. It will not create any difference. So we can neglect this X over here. So we say, sir, this magnetic field would come out to be mu naught I into R square upon 2 into, then we say R square whole raised power 3 by 2. This 2 and 2 will get cancelled out in this case. So this would be mu naught I into R square. Then we have 2 into R cube. Now this R square and this cube will cancel out over here. Sir, B will come out to be mu naught I divided by 2R. Oh, sir, magnetic field due to a ring at the center is mu naught I by 2R. And magnetic field due to a ring very close to the ring. Very close to the ring is also how much? Mu naught I divided by 2R. Keep this thing in your mind also, guys. Mu naught I divided by 2R. This mu naught I divided by 2R. Mu naught I by 2R. Now see, sir, next case, if we take over here, We say very far from the ring. This is the next case we are taking in this one. Very far from the ring. Sir, what is that? Listen to me very carefully. See, let's suppose I'll take this ring over here. Okay, this is the ring over here. And this is the radius of the ring. This is the radius of the ring. Okay. And in this particular case, we are finding the magnetic field at very far from the ring. This is R, and this is X over here. And in this case, we can clearly see this R is very, very small, much, much smaller than X. So we say R is much, much smaller than X. Now use the same formula to find the magnetic field in this case. We say, sir, this magnetic field would be mu naught I into R square upon, sir, 2 into R square plus X square. Over here, what is small? We say R is very small. So we can neglect this R and we can write, sir, X square whole raised power 3 by 2. 2 and 2 will get cancelled. So this is mu naught I into R square upon, and this will be 2x cube, 2x cube. So this mu B is equal to mu naught I into R square upon, we say 2x cube. So this is the magnetic field. This is the magnetic field. This is the magnetic field. Just a second. This is the magnetic field. This is the magnetic field due to a ring, due to a loop, we say at very far distance from the ring. Is that clear, my dear people? All these expressions, is it clear to each and every one? Is it clear to each and every one? Is it clear to each and every one? Is it clear to each and everyone, guys? I'll give you the break at 8 o'clock. Okay, it's been only 2 hours since we started. Break will be at 8 o'clock. Okay, cool. Now, if I ask you to tell me, can you make the graph between magnetic field versus R? See, we say, sir, over here, if we just make the graph, we say, sir, graph between magnetic field, we say versus R. R is the distance at which we are finding the magnetic field, or magnetic field versus X. B versus X. See. Let me just tell you in this particular case, how do we make the graph between B versus X? Listen to me very carefully. We say, the graph would be something like this. Listen to me very, very, very carefully. This is B and this is X. Sir, when it comes to the magnetic field, listen to me very carefully over here. Sir, when it comes to the magnetic field at center of the ring, that is B is equal to mu naught I divided by 2R. B is equal to mu naught I divided by 2R. We say, sir, at center, we say B is equal to mu naught I divided by 2R. Okay. And we say very close to the ring, that is X is much, much less than R. We say magnetic field is how much? Mu naught I divided by 2R. This is also we got over here. Magnetic field very close to the ring. And magnetic field very far from the ring, that is R is much, much less than X. B is equal to, sir, mu naught I into R square divided by 2x cube. This is the expression we recently got. Now, clearly you can see over here, sir, at center, listen to me very carefully. Mu naught is constant. Sir, I is the current flowing in the wire, it is also constant. 2 is constant. And radius of the ring is also constant. We say, sir, this is nothing but constant. Sir, this is also, we say, sir, constant very close to the ring. And in this case, sir, B is inversely proportional to the X. X is variable. So we say over here, B is inversely proportional to the X cube. So if we have to make the graph, listen to me very carefully. Sir, this is X is equal to 0 over here means center. As you go away from the center, X will increase. At center, X is equal to 0. Sir, when it comes to the center, we say magnetic field is constant. So graph would be something like this straight line. Till what? Sir, when X is much less than R, means very close to the ring, If we make the ring over here, it would be something like this. See. From center to the close to the ring, sir, graph is constant. Why? Because magnetic field is constant. And then when you move very far from the ring, B becomes inversely proportional to the X. Sir, the graph in that case would be something like this. This is a rectangular hyperbola. So we say, sir, B is inversely proportional to X cube. B is inversely proportional to X cube, because when you have a ring, from both the sides magnetic field is present. That's why I made the graph from this side, I made the graph from this side. Is that clear, my dear people? Let me know in the live chat, everybody of you. Is it clear, guys? Is it clear, guys? Is the graph crystal and clear? Everyone, I want all of you to let me know in the live chat, is it crystal and clear? Very close to the ring, magnetic field is constant. At the center also magnetic field is constant. That's why straight line. Over here, constant graph. And then you have inversely proportional to the X cube. Okay. This is a very good question. Very good question. See, in this case, you are given a ring, okay? And in this ring, current is flowing. And if current is flowing, its radius is capital R. You guys are supposed to find the magnetic field at P, which is at X is equal to, we say, how much is this? That is the root 3R. Find the value of magnetic field at point P, which is at root 3R distance from the center. We say to find the magnetic field at P, to find the magnetic field at P. How much is this point P far from the center? That is root 3R. In this case, you guys are supposed to tell me the magnetic field. You guys are supposed to tell me the magnetic field. At this point P, you guys are supposed to tell me the magnetic field, okay? Which is at root 3R distance from the center. Which is at root 3R distance from the center. X is equal to root 3R. R is the radius of the ring. See. If we have a ring, and because of that ring, we have to find the magnetic field at point P. We know, sir, general formula. What is that? B is equal to mu naught I divide into R square divided by 2 into, we say, sir, R square plus X square whole raised power 3 by 2. Okay. So this is the magnetic field because of this ring at point P. This is the magnetic field because of this ring at point P. Okay. Yes, sir. Magnetic field because of this ring at point P. Now, what is the value of X over here? Here, we say X is equal to root 3R. Because at this distance only, we have to find the magnetic field. Now, put the value of X as root 3R. So, we say, sir, B would come out to be mu naught I into R square divided by. And then you have 2 into, this would be R square plus. Instead of this X, what is the value of X? We say, sir, a root 3 into R. Root 3 into R, its whole square. Why? Because this X square. And then you have 3 by 2. Now, can we simplify this further? We say, sir, B is equal to, so this would be mu naught I into r square divided by, sir, this is 2 into, this is r square, and this is root 3 whole square. Sir, this root and square will get cancelled out over here, and r will be having square. So this would be simply 2 into r square plus 3r square. It would be something like this, because root and square will cancel out over here, and whole raised power 3 by 2. Whole raised power 3 by 2. Now, if we move on to the next slide, I can write it over here. Mu naught I into r square, I can write over here. Sir, we say, sir, this would be mu naught I into r square upon, we say 2 into r square plus 3r square is how much? We say, sir, 4r square. So I can write over here that is 4r square, and this is 3 by 2. This is 3 by 2. Listen to me very carefully. I'll give you the exact feel. Sir, can we write it something like this? B is equal to mu naught I into r square divided by 2 into. So this would be 4r square whole raised power. This is 3 by 2. Can we write it something like this? 1 by 2 into 3. Yes, sir. 3 into 1 becomes again 3 by 2. Now, what is 1 by 2? We say, sir, value of root is 1 by 2. Means if I am mentioning 1 by 2 over here, it is nothing but root. So root of 4r square, it is something like that only. So if we write it something like this, B is equal to mu naught I into r square divided by, we say 2 into, sir, this will be 4. This is 4 root. This is 4r square root whole cube. This is whole cube. Now see, 4 root is 2, and this square and this root will get cancelled out, or this 2 and this 2 will get cancelled out. So it remains, sir, 2r, and over here it has whole cube, because this is under root whole cube. Now, can we write it something like this? This is B is equal to mu naught I into r square upon, we say, sir, 2r cube. That is 2 into 2 is 4. 4 into 2 is 8. Okay. So we say, sir, this is nothing but 8 into 2 is 16. So we say 16r cube. This is the final answer over here. Okay. No, this is not the final. So this square and this will get cancelled out over here. So what remains in this case? So we say B is equal to, so we can write in this case that is mu naught I divided by 16r. This is the answer in this case. This is the magnetic field at point P. This is the magnetic field at point P because of this ring, which is at x is equal to root 3r distance. Is that clear, guys? Is that clear? Is that clear? Okay. And if you write this in terms of B naught, okay, given the magnetic field at center is B naught, we say at center, we say magnetic field B is equal to B naught. And we know what is the value of magnetic field at center? Mu naught I divided by 2r. This is we got recently. Now from this equation, if you take this equation, we say, sir, from equation number first, we say, sir, this B would be simply mu naught I divided by, and we can write this is 16r. So you can write 2 into, we say, sir, or something like this, 8 into 2r. 8 into 2 is 16. Now mu naught I by 2r. Mu naught I by 2r is B naught. So you can write B is equal to B naught divided by 8. This is the actual answer. And this is a JEE problem. Okay. Sometimes you need to solve the bigger problems also. Okay. I know it has a mathematical calculation. If you want to leave it, you can leave it. Okay. This type of problem cannot come in NEET, but still you should have the practice. If you want to leave it, you can leave it. Okay. If you want to leave it, you can leave it. But this is a very good question. Is that clear, guys? Give me the signal in the live chat. Is it clear to each and everyone? Okay. Now we have magnetic field due to a segment of ring. Sir, what is a segment of ring? Listen to me very carefully over here. Let's suppose I say, what is this? Sir, this is a complete ring. Sir, this is a complete ring. This is what we call the complete ring. Complete ring. Okay. This is what we call the complete ring. Cool. This is what we call the complete ring. And if I just cut this ring over here, something like this. Sir, what is this? This is what we call the semicircular ring. This is what we call the semicircular ring. This is what we call the semicircular ring. And my dear people, if you cut some part of the ring, that is something like this. Some part of the ring. This is what we call the segment of the ring. This is what we call the segment of the ring. Half of this is semicircle, complete it is circle, and some part of this is segment of the ring. Okay, or we say an arc. Now this is the center. This is the center. From center to this point, this is the radius. From center to this point, this is also the radius r. Now we are taking the same segment and placing over here. And in this case, we say, sir, current I is flowing. Current I is flowing. I is the current which is flowing in this one. I is the current which is flowing in this one. And this is the radius r. This is the center. This is the center of the segment. Okay, this is the radius r. So we have to find here we say current I is flowing. I is flowing in the segment. So we say whenever current I flows in the segment, we say it will produce magnetic field. It will produce magnetic field. So it will produce, we say, magnetic field. It will produce magnetic field. Listen to me very carefully. Sir, I current is flowing in this segment or in this wire. It will produce magnetic field. And we have to find the magnetic field at point P. We have to find the magnetic field at point P. So I write over here to find the magnetic field at P. Listen to me very carefully. I'll tell you the general expression in this case. Sir, we say magnetic field at point P would be. See, sir, this is the radius. If you join this with one end, this is, we say, sir, R. If you join this point with another end of this segment, this is also radius r, and in between them this is the angle which is what we call theta. This is the angle between two radius. Now say this magnetic field would be, listen to me very carefully, that is mu naught I divided by 2r. Sir, I is the current in this one, r is the radius, and then you say, sir, this theta, what is theta? Theta is the angle between over here these two radius, and divided by, we say, sir, 2 pi. This is the general expression. I want you guys to remember this as simple as that. This is the magnetic field because of this segment at point P. Sir, how much? Mu naught I by 2r, theta by 2 pi. Mu naught I by 2r, theta by 2 pi. Now, if I tell you over here, we have a semicircle. Sir, in case of a semicircle, listen to me very carefully. This is the point at which we are supposed to find the magnetic field. Current I is flowing in this one. Sir, from this point to this point, this is the radius. Now join this point with another end of this one. This is also the radius. Sir, angle between these two is what we call theta. And in this case, it is, sir, 180 degrees. Clearly, sir, this angle is over here 180 degrees. So means in semicircle, it is mentioned over here, theta is 180 degrees. Sir, in semicircle, theta is 180 degrees or pi. We call it pi also. Now, if we have to find the magnetic field, we use the general formula, that is mu naught I by 2r, theta by 2 pi. Because for a segment, we consider it a general formula. So we say, sir, this magnetic field would be mu naught I divided by 2r. We say theta upon 2 pi. Now in this case, theta is 180 or we say pi. So magnetic field would be mu naught I divided by 2r, and theta is, sir, pi divided by 2 pi. Pi and pi will get cancelled. 2 into 2 is 4. So magnetic field would be mu naught I divided by 4r. Is that clear, my dear friends? Is that clear? Is that clear, my dear people? Everybody over here? Champ. Hey, champ. Some champs are over here to discuss the politics of Parepura. Huh? Chalo. Everyone, is that clear, my dear people over here? So this is the magnetic field due to a semicircular ring at the center at point P. Cool. Okay. See, now the question is how to find the direction in this case. See, I'll tell you how to find the direction. Let me just tell you. Direction of magnetic field. Let's suppose this is the ring or this is the arc you have over here. And at this particular point, you have to find the magnetic field at point P. And in this case, let's suppose current I is flowing over here. Okay. Now, what I want you guys to do is that I want you guys to, this is your right hand. This is your right hand. Now, curl your fingers along the direction of current. Okay. Use this method always and you will get the correct answer. Curl your fingers along the direction of current and thumb is pointing inwards. You have to see the direction of thumb. Curl your fingers along the direction of current and thumb will give you the direction of magnetic field in this case. Okay. We say curl your fingers in the or along the direction of current. Gives the direction of magnetic field. In this case, you curl your fingers along the direction of current and thumb is pointing inwards. So that will give you the direction of magnetic field over here. And in this case, it is inwards. As simple as that. And if the current was flowing something like this, let's suppose current is flowing something like this, then at this particular point, sir, curl your fingers along the direction of current, thumb is pointing outwards. So we say over here, magnetic field is outwards. Is that clear, guys? Is that clear, guys? See, in case of a straight wire, I told you the rule. Place your thumb along the direction of current and then curl at that point where you have to find the magnetic field. But in case of these structures, circular rings, curl your fingers along the direction of current. Thumb will give you the direction of magnetic field. That's it. That's it. Remember these two rules. You don't have to use the another rule. Okay. That's my rule. Okay. Use these two rules and you'll get the answer in every case. I'll tell you how, I'll show you how to solve each and every question by these methods only. Now, let's suppose you have this ring. Sir, we know because of the ring at center, magnetic field is mu naught I divided by 2r. If the radius of this is r. Now, we will find the magnetic field at the center with what formula? With this general formula, sir. Mu naught I by 2r theta by 2 pi. Because over here, sir, this is the segment. This is the general formula. Let me just show you, my dear people, in this case. Sir, what is the general formula? As we know, Sir, magnetic field B is equal to, we say, sir, mu naught I divided by 2R. We say theta by 2 pi. Now you just tell me one thing. In case of a circle, how much is this angle? Complete cycle. We say, sir, this theta is 2 pi. That is 360 degrees. So we say over here theta is 2 pi. That is 360 degrees. So we say, sir, this magnetic field would come out to be mu naught I divided by 2R, and theta, instead of theta, can we put up 2 pi over here? Yes, divided by, we say, sir, 2 pi. 2 pi will get cancelled out. So magnetic field would be mu naught I divided by 2R. See, compare it. Exactly similar. Now, if I give you the question something like this, this is what we call the chord. Sir, in case of the chord, if we have to find the magnetic field at point P, so I said to find in this chord, sir, current I is flowing. We have to find the magnetic field at point P. So we say to find magnetic field at point P. To find the magnetic field at point P. Listen to me very carefully. Sir, we say this, join this point with one end of the chord. This is called the radius R. Sir, join this with another end of the rod. This is also called the radius R. Angle between these two is 90 degrees over here. Now use the general formula. Sir, how much is the general formula in this case? B is equal to, we say, sir, mu naught I by 2 pi, and then, mu naught I by 2R, and then we say theta upon 2 pi. So we say B is equal to mu naught I divided by 2R, and theta in this case is 90. 90 is how much? That is pi by 2. So we call it pi divided by 2. This is in radians, this is in degrees. So we say this would be pi divided by 2 into this 2 pi. Pi by 2 divided by 2 pi. So this pi and pi will get cancelled. 2 into 2 is 4. 4 into 2 is 8. So magnetic field would be mu naught I divided by, that is 8R. That is 8R. Is that clear? Is that clear, everybody over here in the live chat? Is that clear? Is that clear, every one of you? Let me know in the live chat with the fire symbols, each one, everyone. Everyone means everyone. Okay. So you guys have to remember this also. Magnetic field due to a chord is mu naught I by 8R. Magnetic field due to a complete circle at center is mu naught I by 2R. Magnetic field due to a semicircle is mu naught I by 4R. These are the statements which you are supposed to remember, as simple as that. This is magnetic field due to a segment, that is mu naught I by 2R, theta by 2 pi. Mu naught I by 2R, theta by 2 pi. Okay. Now let's move on to the questions, and this is the question number 1. I know this question looks very difficult, but it is very simple. If you know the concept, this question is very simple. It looks difficult, but it is very simple. You guys are supposed to tell me, find the magnetic field at center O of the loop shown in the figure. Over here, you have to find the magnetic field at center O. Okay. Now, due to this entire complete structure, because of this complete structure, you guys are supposed to tell me the magnetic field at center. Solo it before I do it, guys. Solo it before I do it. Everybody of you, I want you guys to solo it before I do it. And if you have not liked the session, I want all of you to like it as soon as possible. Okay? Everyone means everyone. Everyone means everyone. All of you over here, like it as soon as possible. It is 279 likes right now. I want you guys to make it 300 plus. Let's see, can you make it in next 10 seconds? I want to see, will you guys make it in next 10 seconds? I'm waiting. Now see, my dear people, my dear beautiful friends over here. See, in this particular case, we have to find the magnetic field at the center. Listen to me very carefully. Sir, this structure looks very, very complicated, but it is very simple actually. See, sir, over here, this is the first one. Let's call this as first, number one. So magnetic field at center will be because of this wire, okay? And this wire is actually a cord. This is a cord, okay? And this is what we call the second. Magnetic field at this wire will be, sir, this is a straight wire. At center, it will be magnetic field. And this one is the third wire. And this third wire is what we call the semicircle. Now, magnetic field at third will be the magnetic field due to this semicircle will be at center. And this is what we call the fourth one. This one. This is also a straight wire. And then this is the fifth one. This one is also a cord. This one is also a cord. This semicircle has radius 2r. This small cord has radius r. And this bigger cord has radius 4r. And then you have this structure, that is the sixth structure. This is a wire. Now you guys tell me one thing in this case. Sir, we can clearly see that magnetic field due to this straight wire 2, 6 and 4. We said 2, 6, 4 is 0 at center. Why? Because this point is along this wire, this point is along this wire, and this point is along this wire. So we know whenever the point is along the wire, magnetic field is 0 because of that. Now magnetic field would be because of first, third and fifth. Listen to me very carefully over here. So we say, sir, net magnetic field in this case would be magnetic field because of first wire plus magnetic field because of third wire plus magnetic field because of fifth wire, that is the cord. Now see, sir, magnetic field because of first wire, that is a cord. Let's go over here. See, sir, when it comes to the cord, we know magnetic field because of the cord at center is mu naught I by 8r, where r is the radius. Come over here. Sir, in this case, magnetic field because of this cord at center, the radius in this case is given. This cord, bigger cord, is having the radius 4r. So we say it would be mu naught I divided by 8r. Sir, what is the formula? 8r. And we say, sir, 8. And instead of r is how much? That is 4r. I'll write 4r. So done with the magnetic field of this one. Then we have plus. Sir, magnetic field because of semicircle. Let's move over here. Sir, magnetic field because of semicircle is how much? Mu naught I by 4r. Let's come back. Sir, magnetic field because of semicircle is mu naught I divided by 4. And what is the value of r for this semicircle? It is 2r. So we can clearly say this is 2r. And then we say plus. Sir, magnetic field because of this cord at the center, that is how much? We say, sir, mu naught I divided by 8r. How much is the radius of this small cord? That is r. So we say 8r. Okay. Is it clear, guys? Is it clear? Let me know in the live chat, everybody of you. Is it clear? Is it clear? Now, in this particular case, we can further simplify it. We can write, sir, this magnetic field net would be, sir, mu naught I divided by, see, over here it is 8 into 4 is 32r. 32r plus, sir, in this case, mu naught I by 4 into 2 is 8r. We say, sir, mu naught I divided by, we say 8r. Then we say plus, over here, mu naught I by 8r. We say, sir, this is mu naught I divided by 8r. Now, in this case, mu naught I by r, mu naught I by r, mu naught I by r, you can take these common over here. So this would be mu naught I divided by R. And what remains over here? 1 by 32 plus 1 by 8 plus 1 by 8. Okay. And if you simplify this, this would be 9 by 32. Mu naught I divided by R into 9 upon 32. So this would be the net magnetic field. And what is the direction of the magnetic field? See. Curl your fingers along the direction of current. Thumb is pointing outwards. Thumb is pointing outwards. And in this case also, curl your fingers along the direction of current. Thumb is pointing outwards. In this chord also, curl your fingers along the direction of current. Thumb is pointing outwards. So all the magnetic field are outward. So we say that's why we edit them, because they are in the same direction. So this is also outward. Is that crystal and clear? Is that crystal and clear? Guys, let me know in the live chat. Everybody of you. Everyone means everyone. Great. See, this question looked very difficult, but it is actually very easy. Over here, magnetic field is only because of three wires. This one, and this one. Okay, this is chord, this is semicircle, this is chord. That's it, my dear people. That's it. Okay, one more question. Simple question over here. This was asked in NEET 2018. Why is one not a chord, one a segment? Segment is some part of the ring, bro. When we talk about the segment, means some part of the ring. This is not a segment, this is a chord. See, this is a complete circle. If you cut it, see this much, this is what we call the chord, okay? From this point to this point. And if you take the segment in this one, segment means cut it something like this. This is the segment. Segment means it's only some part of the ring. From this point to this point, it becomes chord. Now see, we have this question over here. Charge Q is uniformly separate on a thin ring of radius R. We have over here a ring. On this ring, the radius of the ring is R. We say, sir, Q charge is present on the ring. The ring rotates about its axis with a uniform frequency F. Now this ring is rotating. Let me just make it something like this. This is the ring over here. Okay. And this is the axis of the ring. Okay. And this ring is rotating about this axis. And the radius of this ring is given as, R. And Q is the charge present on this ring. Now, when it is rotating, we say, sir, over here, in this case, this charge is basically rotating over here on this ring. Now, listen to me very carefully. Sir, over here, when this charge rotates, charge moves, so current is produced over here. So we say in this case here, current is produced in the ring. The current is produced in the ring. And we know, sir, whenever current flows in the ring, it produces the magnetic field. And we have to find the value of that magnetic induction at the center. We have to find the magnetic field at the center. So we say I is produced in the ring. How? See, this is a charged ring. If it is rotating, means charge is moving. If charge is rotating, means current is being produced. And we have to find the magnetic field produced by this ring at center. So we say, sir, magnetic field at center is. So we say, let me just write it something like this. We say, sir, magnetic field at center due to the ring, due to the ring. So that would be, we know due to a ring, magnetic field at center is how much? Mu naught I by 2R. Mu naught I by 2R. Now in this case, current is not given in the question, but what is given is frequency. Listen to me very carefully. Sir, we say current is nothing but charge upon time. Current is Q by T. So we can write over here, if sir, current is Q divided by T. And we know, sir, frequency means 1 upon time period. Sir, time period is in how much time it will complete one cycle. So frequency is inverse of time period. So put it over here. Sir, in this case, sir, time period would be 1 upon frequency. Now put it in this equation. Current would be nothing but Q upon. Instead of this time period, we can write 1 by frequency. Now take this in the numerator. It becomes Q into F. Okay. Now this current Q into F. Can you put it in the equation number 1? Yes, sir. I say put I is equal to QF in equation number first. So we say magnetic field is equal to, sir, mu naught I by 2R. So we say mu naught I, instead of I, we say Q into F divided by 2R. This is the answer in this case, mu naught Q into F by 2R. Mu naught QF by 2R. See, in this question, frequency was given. That's why, and charge was given. That's why we were supposed to find the magnetic field in terms of Q and charge. Let me just write it. It is important. Here, in the question, we say charge and frequency is given. Charge and frequency is given. So we have to find the magnetic field in terms of charge and frequency only, not in terms of current. Is that clear? Is that clear? Is that clear, guys? Is that clear, my dear people? Is it clear? Okay, very good question over here. Can you tell me the magnetic field at the center? We have got two semicircular rings over here. This one and this one, bigger one. You guys are supposed to tell me the magnetic field at the center. Current is flowing something like this, okay? Direction of current. See the direction of current over here. I say, in this case, find the magnetic field at the center. Listen to me very carefully. Sir, current in this straight wire would be something like this, and in this straight wire would be something like this. Now, because of this straight wire, current at this point would be 0. Sorry. Magnetic field at this point would be 0. Why? Because this point lies on the axis. Because of this straight wire, magnetic field at the center would be 0. Why? Because this point lies on the axis of this wire. So let's call this as first, let's call this as second. Here we say magnetic field will be due to this bigger semicircle and smaller semicircle. We say, sir, that is first, and we say, sir, second. Magnetic field would be first because of first and because of second. Listen to me very carefully over here. Listen to me very carefully over here. If I tell you over here, my dear friends, if I tell you in this case, sir, net magnetic field would be, listen to me very carefully. Sir, net magnetic field would be, see, because of this semicircle, what is the direction of magnetic field? Sir, because of this semicircle, direction of magnetic field at center is, curl your fingers along the direction of current, thumb is pointing outwards. So because of this, sir, magnetic field at center is outwards. And when it comes to the second semicircle, sir, because of second semicircle, magnetic field at center is inwards. Magnetic field at center is inwards. Curl your fingers along the direction of current, thumb is pointing inwards. So because of this, magnetic field at center is B2, and because of this, magnetic field at center is B1. Why am I subtracting these? Because this B2 is, we say, sir, inward, and this B1 is, we say, sir, outward. This B1 is outwards. Both the magnetic fields are in opposite. That's why I'm subtracting. Now, write it. Sir, B net in this case is B2. That is magnetic field due to this smaller semicircle, which has got the radius of R, Sir, magnetic field due to a semicircle, how much, what is the formula? Sir, formula is mu naught I by 4R. So I can write over here, sir, it would be nothing but mu naught I. I is the current in this one, divided by 4 into R. And what is the R in this case? That is R only. So this is R. Then we say minus. Sir, magnetic field due to this bigger semicircle is also mu naught I divided by 4R. But what is R in this case? R in this case is 2R. So I can simply say this is nothing but 2R. So now it becomes 4 into 2 is 8. So this is nothing but mu naught I divided by 4R minus mu naught I divided by, sir, 8R. Sir, why did you subtract B2 minus B1? Why not B1 minus B2? You can do that also, that will give you the correct answer, but that will be negative. See, B2 in this case is more, B1 in this case is less, because it is 4 divided by 4, it is divided by 8. So this is less than this one. That's why higher minus lower. So we say, so this is nothing but mu naught I by 4R minus mu naught I by 8R. It would be, if you subtract them, it would come out to be mu naught I divided by 8R. Okay, so this is net magnetic field, and this would be simply, we say, sir, inwards. Is this clear, guys? Is this clear, guys? Is that clear, guys? Is that clear, guys? Is that clear, every one of you? All the people, let me know in the live chat, guys. Let me know in the live chat, guys. Is it clear to each and everyone? Okay. Now, this question. This is something like this, okay? Current is flowing something like this. This is I and this is I. These are the two semicircles. This is the bigger one, and the smaller one is from the lower side. And the smaller one is from the lower side. And the smaller one is from lower side. You guys are supposed to tell me, in this case, the net magnetic field at center. This bigger semicircle has the radius 2R. This smaller semicircle has the radius R. Bigger one has the radius 2R. The smaller one has the radius R. Bigger one has the radius 2R. Smaller one has the radius R. Can you tell me the net magnetic field at the center, everybody over there? Everybody over there, all the people out there. Now, net magnetic field at the center would be, listen to me very carefully. Let's call this as first, let's call this as second. So net magnetic field in this case would be here. We say magnetic field is due to first semicircle, bigger one, and second semicircle, that is the smaller one. Okay, yes. Now, sir, in this case, net magnetic field, we can write, sir, B1 plus B2. Why, sir, you are adding over here? See why. See, in this case, magnetic field due to bigger one is inward. Okay, this is, sir, inward. How? curl your fingers along the direction of this current and thumb is pointing inwards. So magnetic field is inwards. Now, when it comes to this semicircle, sir, curl your fingers along the direction of this current and thumb is also pointing inwards. So this is also inward. Both the magnetic fields are in the inward direction. So we are adding them. So in this case, we say, sir, B net is B1. Magnetic field due to a semicircle is how much? We say, sir, mu naught I divided by 4R. And 4R is over here. That is 2R. This is 4 into, we say, 2R. Then we say plus magnetic field because of this is how much? Mu naught I divided by, we say, sir, 4R. So we say in this case, net magnetic field is, see, 4 into 2 is 8R and 4 into this is, we say, sir, mu naught I divided by 8R plus mu naught I divided by 4R. You can further simplify it and get the answer. Is that clear, my dear people? Is that clear? Okay. Is that clear? Okay. 3 by 8, we say, sir, mu naught I divided by R. If you saw, take the mu naught I by R out, 1 by 8 plus 1 by 4, it becomes 3 by 8. Okay. And net magnetic field is also inward, and this is also inward. Inward magnetic field we represent with cross. This is also a very good question over here. There are so many questions left. That's why I told you there will be the tsunami of questions in the today's class. There will be the tsunami of questions in the today's class. Now, let me just make the figure or diagram over here. The structure is something like this. This is an arc and this is one more arc. And this is a structure something like this. This is a structure something like this. This is a structure something like this. This structure something like this. And in this case, you guys are supposed to tell me the magnetic field. You guys are supposed to tell me the magnetic field at this point. Okay. And this angle is given as theta. This is one arc. In this arc, current is flowing I. And in this case, current is flowing I. Okay. Current is flowing I. And listen to me very carefully. This distance from this point to this distance, these are the two. So this is A. And from this end to this end, the distance from this end to this end, this is given as B. See, over here we have this arc in which I current is flowing. Over here we have bigger arc in which I current is flowing. And you guys are supposed to tell me the magnetic field at point P such that this point P is at A distance from the smaller arc and this point E is at B distance from the large arc, bigger arc, from this bigger arc. This is at B distance. This is at B distance. And we have to find the magnetic field at P. We say, sir, to find magnetic field at P due to two arcs. Due to two arcs. We have to find the magnetic field at point P due to two arcs. Now listen to me very carefully in this case, my dear people. See. Which formula should I use over here? Let's call this as arc number first and let's call this as arc number second. See, when it comes to the first arc, sir, what is the direction of magnetic field at center? Look, curl your fingers along the direction of current. Thumb is pointing inwards. So we say, sir, in this case, we say B net is equal, sir, this is B1. This is B1. So this B1 is, sir, inwards. Then, sir, magnetic field because of the smaller arc over here, this is outwards. Okay. So we can say over here, just write it something like this. Sir, because of this smaller arc, it is B2. Because of this bigger arc, it is, sir, B1. Why are you subtracting, sir? Because in this case, we can clearly see that. Okay. Plus. Sorry. I made a mistake. So we say, sir, because of this bigger arc, it is inward. Okay. This will be in subtraction. Okay, subtraction. B1, B2 minus B1. Sorry. Sir, because of this. Curl your fingers along the direction of current. This is inwards. Okay. And in this is outwards. Why am I making the mistake over here? B2 is because of this one and B1 is because of that one. Because of that one, magnetic field is inwards, and because of this one, magnetic field is outwards. Is that clear? Guys? Is that clear, guys? Because of this arc, magnetic field is inwards. That is B1. Okay. Because of this smaller arc, magnetic field is outwards. How do you find it? Curl your fingers along the direction of current. Thumb is pointing outwards. So magnetic field because of small arc is outwards. Now, let me just tell you how to find the net magnetic field. Sir, net magnetic field is B2 minus B1. Listen to me very carefully. B2. Sir, B2, this is an arc. Sir, if we have an arc and we have to find the magnetic field because of it, how do we find? What is the formula? See, because of an arc, I'll tell you what is the formula. This is the formula, sir. That is, because of this arc at point P, at center, magnetic field is mu naught I divided by 2r theta upon 2 pi. Same formula we'll be using over here. Same formula. Sir, this is nothing but we say because of this arc mu naught I divided by we say sir 2r, and then we say theta upon 2 pi. And in this case, if I just write, sir, B is equal to this mu naught I divided by 2r theta upon 2 pi. This is the general formula because of the arc. Now see, how do I write it over here? We say, sir, B2. B2 is the magnetic field because of this smaller arc. How do I write it, sir? Mu naught I divided by 2r. Now see, sir, r, this is the smaller arc. R means this radius. R is given how much? That is a. R is given as a. So 2 into a. And then theta. In this case, how much is this angle? This is given as theta only. So I write theta upon. We say, sir, 2 pi. Okay. So I can write it something. Oh, okay. Sorry. Then we say, sir, minus. B1, that is magnetic field because of this first arc. Sir, magnetic field because of first arc will be how much? We say, sir, that is also use the same formula mu naught I divided by, we say, sir, 2r. In the first arc, we say r is how much, sir? B. So we say, sir, this is nothing but B and theta upon 2 pi. Now we can write over here. See, sir, this would be mu naught I into theta upon 2 into 2 becomes 4 pi a minus, in this case, it is nothing but mu naught I into theta upon 2 into 2 is 4 pi b. Now what comes common? Sir, mu naught I by 4 pi, mu naught I theta by 4 pi. In this case, we say, sir, mu naught I theta by 4 pi. This is same. So this comes as common. So what remains over here? 1 upon a. And what remains in this case? 1 upon b. Now further you can simplify it, mu naught I into theta by 4 pi. And if you do the cross multiply, b minus a upon ba. B minus a upon ba. This is the net magnetic field. This is the net magnetic field at the center because of the two arcs, mu naught I theta by 4 pi, b minus a into ba. Now let's check for the options over here. Mu naught I into theta upon 4 pi, b minus a upon ba. Option number B. Mu naught I theta by 4 pi, b minus a upon b into a. Is that clear, guys? Is that clear, guys? Option 2 is correct. Option 2 is correct. Is that clear, guys? Every one of you, if you are not like the video, like it as soon as possible, okay? And I am giving you the break exactly at 8 o'clock, okay? Now, let me just write over here. Break till we say, sir, 8:40 p.m. dinner time. Break till 8:40. Okay, this is for you people. All the people, guys, if you have not liked the session, like it as soon as possible. So break is till 8:40. You guys have dinner. I'll also have the dinner over here. Okay, we'll be back at 8:40. Guys, till then, chill. All right, people. Welcome back to the session. Welcome back to the session over here. So, you guys are done with the dinner? Okay, so you guys are done with the dinner. One of the student was actually saying, why did I do B2 minus B1? Because B2 is more. Okay, because of this we say magnetic field is more. We say because of this magnetic field is more. Okay, and because of this magnetic field is less. Why? We say, sir, this A mu naught I by 2A, this A is less than B, this A is less than B. So we say if this A is less, its magnetic field would be more. Okay. Am I audible and visible properly? Am I audible and visible properly? Now we have got the next question over here on the screen. I want everybody of you to basically solve this particular question over here. Okay. In this case, you guys are supposed to tell me the magnetic field at the center over here. What is the magnetic field at the center due to this entire structure? And this structure in this case is made up of, we have a wire, okay? This wire is coming from infinity and this wire is also till infinity. So this is semi-infinitely long, and we have this circular shaped wire over here. And in this particular case, we are supposed to find the net magnetic field at the center. Listen to me very carefully. We say over here magnetic field at center would be because of this first wire, that is semi-infinite wire, because of this wire, okay, circular wire, and then because of this wire, that is we say the semi-infinite wire number 2. This is 1, 2, and this is 3 over here. Okay. Now in this case we say, sir, magnetic field due to we say magnetic field due to wire 1. We say magnetic field due to this wire 1 at point O, at center is 0. Why, sir? Can anybody of you tell me in the live chat why magnetic field due to this semi-infinite number 1 is 0 at center? Can you tell me in the live chat, guys? Why magnetic field due to this semi-infinite wire 1 at the center is 0? Can you tell me in the live chat? Because yes, because this point is on the axis of this wire. This point O, center, is on the axis of this wire 1. That's why we say magnetic field at this point, because of this wire 1 is 0. Okay, yes. Now, sir, we say in this case, sir, magnetic field net will be, sir, magnetic field due to first wire, that is B1, okay, plus magnetic field due to this third wire, okay, or we say, sir, magnetic field due to this second wire is this one. Then we say plus magnetic field due to this third wire. Now, in this particular case, listen to me very carefully. We say, sir, net magnetic field would be, sir, magnetic field due to first is 0, okay, then we say plus magnetic field due to second wire. This is infinitely long. If you place your thumb along the direction of current and curl your fingers at this point, it is going in the inward direction. So this magnetic field is inward. And sir, because of this ring, magnetic field at center would be curl your fingers along the direction of current. Thumb is pointing inwards. So this is also inwards, okay? So this magnetic field is also inwards and this magnetic field is also inwards, okay? Now, sir, because of this semi-infinite wire, magnetic field is how much? I have told you when it comes to the magnetic field because of the semi-infinite wire, let me just show you once again over here. Let me just show you once again over here. Sir, the semi-infinite wire, this is the semi-infinite wire. That is mu naught I by 4 pi r. This is the magnetic field because of the semi-infinite wire. And let me just put up this over here in this case. We say, sir, it is mu naught I divided by 4 pi. And this is, we say, at what distance you are finding the magnetic field? That is r. So this is the magnetic field because of second wire at this point. Then we say, sir, plus magnetic field because of this. As this is not a chord, this is not a semicircle, but this is the, we say this is the third part of the circle over here. Okay, this is see, if you join this, it becomes complete circle, and if you remove this fourth part from the circle, then what remains is this part over here. And in this case, if you check this angle, this is theta. Over here, we say, sir, theta is 3 pi divided by 2. This angle, if you see, if I take this structure over here, join the center from this point to this point, this is r, and between these two, this is what we call theta, and theta is 3 pi by 2. And use the general formula for a segment. Sir, what is the formula for segment? See, we know, sir, formula for segment is mu naught I divided by 2r. Then we say theta upon 2 pi. And in this case, how much is theta? That is 3 pi by 2. So we say, sir, net magnetic field in this case would be, that is mu naught I divided by 2 pi r. Okay, then plus mu naught I divided by 2r. Then we say theta by 2 pi. What is the value of theta in this case? We say, sir, that is 3 pi by 2. This is 3 pi divided by 2. Okay, and then you have theta upon 2 pi. And this pi and pi will get cancelled out over here. We say, sir, this would be mu naught I divided by 2 pi r. Then you can say plus, and in this case, it would be mu naught I divided by, and this is 3 times of mu naught I divided by 2 into 2 is 4, 4 into 2 is 8, then it will be 8r, then it would be 8r. Is that clear, my dear people? Is that clear, my dear friends? Is that clear, my dear friends over here? Is this clear? Is this clear, guys? Okay. You can keep it as it is, or you can further simplify this also and you'll get the answer. Okay. Okay, great. Let's move on to the next question. This is the next question over here. And I say in this case, find the magnetic field at point O. At this center O, you guys are supposed to tell me the magnetic field. What is the magnetic field at point O? What is the magnetic field at point O? And the ones who have not liked the session yet, like it as soon as possible. Everyone. All the people out there, can you tell me the value of magnetic field at point O? In this case, we say in this case, we say magnetic field is because of 1, 2, and 3. This is a semi-infinite wire. This is a semicircular wire. And this is a semi-infinite wire. And see, because of this, sir, we say over here magnetic field is produced in this case, okay? And in this case, because of this, see, we say over here, because of this magnetic field at the center is, we say inwards. Because of this also magnetic field is inwards, okay? See, because of the upper wire, place your thumb along the direction of current, curl your fingers, it is pointing inwards. And because of this also magnetic field is inwards. Because of this also magnetic field is inwards. So I say, sir, in this case, net magnetic field is magnetic field due to first, that is this semi-infinite wire, plus magnetic field due to this second, that is a semicircular ring. Then plus magnetic field due to third, this is a semicircular wire. This is inwards. This is inwards, this is inwards. Now, how do we find the value of this magnetic field because of this? Sir, we know because of semi-infinite wire, it is mu naught I divided by 4 pi, and this radius is R. Okay? And at R distance, we are finding this is a semi-infinite wire. Then we say, sir, plus magnetic field due to the second one. Sir, magnetic field due to this is nothing but mu naught I divided by, we say, 4R. Because of the semicircular ring, magnetic field is mu naught I by 4R. Okay? Yes, sir. Then we have this wire. This is also the semicircular wire. This radius is also R over here. So it will be mu naught I divided by 4 pi R in this particular case. And we can write over here, sir, this is mu naught I by 4 pi R. Mu naught I by 4 pi R, that is 2 times of mu naught I divided by 4 pi, and this is R. Then we say this is plus over here mu naught I divided by 4R. This mu naught I by 4R. Further, you can write it, sir, this B net would be something like, see, mu naught I by 4R, you can take this common, mu naught I divided by 4R, you can take this common, and what remains inside is, in this case, it would be mu naught I by 4R, it would be 2 upon pi, 2 by pi, then plus, we say 1. This is the net magnetic field over here. Mu naught I by 4R, 2 by pi plus 1, and this would be, we say, inwards. This would be inwards. Is this clear, guys? Is this clear, guys? Let me know. Last question. Which one? Which one? Which one? Which one? Which one are you talking about? This is the mu naught I by 2 pi R. Okay. Mu naught I by 4 pi R. 4 pi R. This is 4 pi R. 4 pi R. Okay. Let me just change it over here. This is a mistake. Okay. This is 4 pi R. This is 4 pi R. Now is it clear? Now is it okay? Now is it okay? Cool. Now, can you guys find the magnetic field at the center in this particular case? We have this semi-infinite wire and we have this semi-infinite wire over here. Okay. And then you have a ring-like structure, something like this. And you know, sir, this angle in this case, this theta is equal to 3 pi by 2. This angle is theta is equal to 3 pi by 2. What is the magnetic field at the center? What is the magnetic field at the center in this particular case? What is the magnetic field at the center in this particular case? See, we have got a wire over here. We have got another wire over here, circular shaped wire. We have got another wire which is semi-infinitely long. And because of this entire structure, we have to find the magnetic field at the center. Now, my dear people, if I say over here, sir, when it comes to the net magnetic field, it would be magnetic field due to the 1 plus magnetic field due to the structure 3 plus magnetic field due to the structure 2 over here. Sir, when it comes to the magnetic field due to this wire 1 at point O, it would be, sir, 0 simply. Why? Because this point lies on the axis of this wire. This point lies on the axis of this wire. Then plus, sir, magnetic field because of this. As in the previous question also I told you, use the segment formula over here, general. That is how much we say, sir, mu naught I divided by 2R. Then we say theta upon 2 pi. This is the formula that you will be using. Then we say plus. Sir, B2 is how much in this case? Sir, magnetic field due to this wire at this point is also 0. Why? Because this point lies on the axis of this wire. Now, my dear friends, can I write it something like this? B net is equal to. So we say, sir, mu naught I divided by 2R. And what is the value of theta in this case, sir? This theta, this angle, theta is equal to 3 pi by 2. So we say, sir, this is 3 pi divided by 2 into this 2 pi. This pi and pi will get cancelled out over here. So net magnetic field in this case would be 3 mu naught I divided by 2 into 2 is 4, 4 into 2 is 8, that is 8R. This is the net magnetic field at the center. Is that clear? Is that clear, guys? This is the net magnetic field at the center. Is that clear, guys? Now we have the Ampere circuit law. Now we have the Ampere circuit law. Guys, give me the signal in the live chat if everything is crystalline clear. And if you have not liked the session, like it as soon as possible. Now we have the Ampere circuit law. Ampere circuit law. What does Ampere circuit law mean? Listen to me very carefully. Listen to me very carefully. I say, sir, it is used to find the magnetic field. Magnetic field. Sir, Ampere circuit law is simply used to find the magnetic field. As simple as that. Okay? Yes, sir. Now, let's suppose we have a wire over here. We have a wire over here. And in this wire, current I is flowing. Okay? And we have to find the magnetic field at R distance because of this. Okay? We have a wire. Let me just make it over here. Let's suppose we have an infinitely long wire. Okay? And in this infinitely long wire, I current is flowing. And we have to find the magnetic field due to it at R distance. Okay. You'll say, sir, we know the formula. Biot-Savart's law helps us to find the magnet. That tells us to find the magnetic field at R distance. But I'm saying that we don't have to find the magnetic field using Biot-Savart's law. We have to use the Ampere's law. We say find magnetic field at P. Find magnetic field at P using Ampere's law. See, if this is an infinitely long wire, sir, we know because of the infinitely long wire, magnetic field is nothing but, sir, mu naught I divided by 2R divided by 2 pi r. Sir, we know this. But over here, this is the formula, this is the value which we have got previously by Biot-Savart's law. But we have to find the magnetic field over here by using Ampere's law. Listen to me very, very, very carefully over here. See, sir, in order to use the Ampere's law, in order to find the magnetic field at this particular point using Ampere's law, the first point is we say draw an Amperean loop. Draw a loop, which is what we call the Amperean loop. Okay? Let me just make it something like this. Draw a loop, that is what we call the Amperean loop. Amperean loop. So what is the first thing you guys are supposed to do? Draw the Amperean loop. A lot of people feel this is a difficult concept. Give me only 5 minutes and I'll make it butter for you. Now see, we say, sir, we'll draw an Amperean loop such that that loop should pass through that point at which we have to find the magnetic field. If I say, sir, this is the current, at this point you have to find the magnetic field. Is this loop correct? No. This loop should pass through that point. Then only we say this loop is correct. Then only we say this loop is correct. Okay. Same is the case over here. So we draw an Amperean loop such that it passes through the point. What is the first thing? Draw the Ampere's loop, okay, such that it passes through that point, such that it passes through that. Okay, yes, sir. Now, the next is my dear friends, then we say, sir, Because of this, at this particular point, magnetic field is B. Yes, sir, magnetic field is B. What I want you guys to take is, take a small element over here. Take a small element over here. That is a DL. Take a small element DL. Okay. First is draw an Ampere's loop. Then we say, sir, take a small element of this loop. Okay. Let's suppose length of this loop is, we say L. Take a small length, that is what we call the DL over here. Okay. And we say magnetic field at this particular point is B. Now, what you will do is that you will take this magnetic field B and you take its dot DL, B multiplied by DL, and then you do this close integration. You do this close integration. This is how we apply the Ampere's loop. This is how we apply the Ampere's law. Don't use your mind. Where does that come from? Where does this come from? Just follow me, whatever I'm saying. In order to find the magnetic field at this point, first is draw the Ampere's loop. Then take a small element DL and mention the magnetic field at this point because of this wire is B. Then take B into DL. Multiply this B and this DL. Then take their close line integral. Take the integration sign over here. So close a line integral B dot DL and make this equal to, listen to me very carefully, make this equal to mu naught times mu naught is permeability of free space, into I enclosed, mu naught times of I enclosed in the loop. This is the Ampere's law. This is the Ampere's law. What does Ampere's law say? Ampere's law says that if you have to find the magnetic field at a point, draw the Ampere's loop first. Yes, sir. Then mention the magnetic field at this point because of this wire. Let's call that B. And take a small element DL, small length element DL. Then multiply B into DL and take its integration, close line integral B dot DL. Make it equal to mu naught times of I enclosed. I enclosed is the current enclosed in this loop. This is what we call the Ampere's law. Sir, you said by using the Ampere's law, you can find the magnetic field due to an infinitely long wire. Yes. Let me just tell you how. See, let's take a small current element over here, DL, and magnetic field at this point is B. Now apply Ampere's loop. We say apply Ampere's law. Sir, what is that? Closed line integral B dot DL is equal to mu naught times of I enclosed. Listen to me very carefully. How much is the enclosed current in this loop? That is I. So we say over here, this is nothing but integral B dot DL. Sir, because of this wire, magnetic field at this r distance is B. Take this out. Okay, this is constant. Take this out. So it will be integral DL. And then it will be mu naught times of I enclosed. In this loop, how much is the enclosed current? That is, sir, I. Now we can write this is B, line integral DL, closed line integral DL. Sir, what is this DL? Listen to me very carefully. Sir, this is DL. This is another DL, DL. If you add all of these DLs, what will you get? You'll get the complete circumference of this one. So we say integral of DL is nothing but 2 pi and r. R is the radius. This 2 pi r is the circumference of this ring. So we say integral DL. Instead of integral DL, we say, sir, this is nothing but 2 pi and r. Then you have mu naught times of I. Now from this, can we write, sir, B is equal, take this over here. So it would be mu naught I divided by 2 pi into r. So this is what we call the magnetic field because of the infinitely long wire. Clearly you can see that we know magnetic field because of this infinitely long wire is mu naught I by 2 pi r. Is this clear, my dear friends? How you guys are supposed to apply the Ampere's law? First and the foremost thing is, at that point, draw a Amperean loop. Second is take close the line integration of B into DL, make it equal to mu naught times of I enclosed, and then you'll get the value exactly. Is this clear, guys? Is this clear? Guys, give me the signal, because a lot of people feel this is difficult. Give me the signal in the live chat if this is clear to each and everyone. Everybody of you. I need to know in the live chat. I need to know in the live chat if this is clear to each and everyone. If this is clear to each and everyone. All of you, I want all of you to give me the signal. Okay, great, great, great. Now, in this case, you guys are supposed to apply the Ampere's law. One more point I just need to tell you in this case. What is that? We say if B and magnetic field and DL are in the same direction, if magnetic field and DL are in the same direction, then take I enclosed as positive. And next point I just need to write over here, if magnetic field and DL are in opposite direction, if magnetic field and DL are in the opposite direction, then take I enclosed as negative. Let me just tell you the meaning of this one. See, in this case, I have given you the question. In this case, I have given you the question. Listen to me very carefully. You guys are supposed to apply the Ampere's law over here. Sir, what does Ampere's law say? Integral, closed line integral B dot DL is equal to mu naught times of I enclosed. Listen to me very carefully. Sir, first and the foremost thing over here is I enclosed in this case is enclosed current is that current which is inside the Ampere's loop. Over here, Ampere's loop is given. Sir, enclosed currents are I1 and I2. I3 is out of the Ampere's law, Ampere's loop. So this is not the enclosed current. So we say it is I1 and I2 over here. Okay, done. Now listen to me very carefully. Sir, if we have to apply the Ampere's law, we say closed line integral B dot DL is equal to mu naught times of I enclosed. Sir, I enclosed is I1 and we say, sir, I2. So I say I1 and I'll write I2. Now the question is, shall I put plus over here or minus? Shall I put plus over here or minus? Now come over here. If B and DL are in the same direction, then take I enclosed as positive. If B and DL are in the opposite direction, then take I enclosed as negative. Come over here once again. Let me just tell you, because of this wire, current is flowing in the upward direction. So because of this current, magnetic field at this point is, place your thumb along the current, magnetic field at this point is in the same direction. Let's call that B1. This magnetic field is because of I1. Now tell me, the direction of this DL is also opposite. It is given. In every question it will be given. The direction of DL is in this direction. And B is also in the same direction. So means this B1 is the magnetic field because of I1. So we say, because of this I1, this is the magnetic field, and this magnetic field and DL are in the same direction. So we take its current as positive. So this will be positive. And sir, when it comes to this one, sir, this current is in the downward direction. Place your thumb along the direction of current. Thumb is pointing in this direction. So means we say, sir, direction of B2 is in the downward direction. So means this DL is in the upward direction, B2 is in the downward direction, so they are opposite, so we take current I2 as negative. I know you got the confusion over here. That's why I will be showing you this question separately. Let's suppose we have, this is the Ampere's loop, this is the current flowing over here, and in this case we say this is the direction of DL. This is the direction of DL. You guys are supposed to apply the Ampere's law over here. Sir, Ampere's law says B dot DL is equal to mu naught times of I enclosed. In this case, I enclosed is I. So we say integral B dot DL is equal to mu naught times of. Now the question is, do I have to take this I as positive or negative? See, because of this current, magnetic field at this is, we say, sir, in this direction. Okay, it is something like, it's in 3D. Okay, so sir, DL and B are in the same direction, so we say positive I. If I say, sir, this question over here, this is the current flowing something like this, and this is the direction of DL. You guys are supposed to apply the Ampere's law over here. Sir, once again, integral closed line integral B DL is equal to mu naught times of I enclosed. Now the question is, do I have to take I enclosed, I as positive or negative? See, sir, place your thumb along the direction of current. In this case, magnetic field is in this direction. So we say this is the direction of a magnetic field that is over here. Sir, clearly B and DL are opposite. So we take, in this case, minus of I over here. So this would be minus mu naught times of I. Is this clear, guys? When we are supposed to take positive current, when we are supposed to take negative current. Is this clear? Is this clear? Guys, let me know in the live chat. Give me the signal, guys. That's why over here, I took plus I1 minus I2 in this question. Plus I1 and minus I2 in this question. Okay, can you tell me the answer of this particular question over here? Can you tell me the answer of this particular question over here? What is the answer of this particular question over here? Everyone? What is the answer of this particular question over here? What is the answer of this particular question? All the people out there. Which current should I take, positive and negative? That's what I'm trying to ask over here. Which current I should take, positive or negative? See. In this case, this is the loop. This is the loop, Ampere's loop. And this is the direction of, we say, DL. And this is the I1. This is the I1. I1 is cross. Cross means the current is going inwards in the board. This is I1 over here, okay? And I2 is also cross. I2 is also cross. And I3 is dot. I3 is dot. And I4 is dot. Means I3 is the current coming out. I4 is the current coming out. I3 is the current. I2 is the current going in. I1 is the current going in. My dear people, if I have to use the Ampere's law over here, sir, we say closed line integral of BDL is equal to mu naught times of I enclosed. The first question is, which one is the enclosed current? Sir, I6 is out of the loop, so it is not enclosed current. Remove it. Sir, I5 is not in the loop, so remove it. So which currents are inside the loop? We say I1, I2, I3 and I4. So we say over here, sir, closed line integral BDL is equal to mu naught times of. Now see, sir, which current? I1, I2, I3, I4. I'll just write, sir, I1, then I'll write I2, then I'll write I3, and then I'll write I4. Now we have to see which current is positive and which current is negative. See, because of this, see over here, let me just show you in this case. Sir, because of this current, see, because of this current I1. Sir, because of this current I1, the magnetic field at this point is, see, how do you find the direction of magnetic field? Place your thumb along the direction of current. As current is going inwards, it is crossed. Place your thumb inwards. So curl your fingers over here. Sir, this is the direction of magnetic field. I call this as B1. Now B1 and BL, clearly they are in the opposite direction. So means I1 we have to take negative. I hope this is clear, guys. Now, let's come on to this one. Sir, I2 is also inwards. It is going in the inward direction. You have this thumb. Place this thumb along the direction of the current and then curl your fingers. So because of I2, magnetic field is in this direction. This is B2. Clearly B2 and DL are in the opposite direction. So minus I2. Okay, clear, sir. Now let's talk about I3. Sir, I3 is the dot. It is coming out. This current is coming out. Now, if we have to check magnetic field because of this, see, place your thumb along the direction of current as it is going out, so thumb is out. Now curl fingers, okay? Curling fingers is something like this, so this will be magnetic field due to this I3, that is B3. Clearly DL and B3 are in the same direction, so we take it positive. Now, let's talk about, we say, sir, I4. I4 is also out. So we say because of this is the magnetic field, we say B4. So we say DL and B4 are in the same direction, we say positive. Guys, is this clear? This is the concept people feel so much difficult. Only because of the direction, sir. What is this? What is that? I have told you just two things. Place your thumb, in case of a straight conductor, place your thumb along the direction of current, curl your fingers. Second, in case of a circular rings, curl your fingers, thumb gives the direction of current. That's it. No other concept. If you see the book, it will confuse you. Just keep the book aside. Just follow my methods. That's it. Is this clear to each and everyone in the live chat? I just need to know. Is this question clear? Is this question clear or unclear? Clear or unclear? Clear or unclear? Everybody of you? And guys, if you have not liked this session, like it as soon as possible. Okay, next question. Okay, these are the 4 questions. Now, can you tell me the answer of this one? The first one, second one, third one, fourth one. Can you tell me the answer of these questions? See, in this case, let me show you this question over here. When it comes to this particular one, this is the direction of DL. Okay, this is the DL. And this is the current coming out. Sir, current is coming out. Let's solve the A part over here. Sir, current is coming out and DL will be in the same direction. Okay. So B will be in the same direction. So we say closed line integral B DL is equal to mu naught times of, we say, sir, I1. And this I1 will be positive. And we will not take this I2 in I enclosed. Why? Because this is outside of the loop. So B and DL are in the same direction. That is this one. Let's solve this particular question. Fourth one. Let's solve option number D. Fourth one. See, in this particular case, this is the direction of DL. This is the direction of DL. I hope this is this visible, guys? This is the direction of DL in this case. So we say closed line integral B dot DL is equal to mu naught times of. Now see, this is the current I over here. Sir, because of this current, place your thumb along the direction of current, magnetic field would be in the same direction. Okay. So because of this current, this dot current, magnetic field and DL are in the same direction. So we take I1 as positive. This is plus I1. This is I given, so we say plus I. Then we say in this case, sir, current is positive. So current is outwards. In this case, this is sir DL. So sorry, this is sir B. This is sir B. B and DL are in the opposite direction. Then we say minus I in this loop. Then come on to this loop. Sir, in this loop also, current is going inwards. Curl your fingers. So this is the direction of magnetic field and this is the direction of DL. DL and B are in the opposite direction, so minus I. And in this case also, it would be minus I. It would be minus I. Why? Because sir, over here, we can clearly see that current is outwards. So magnetic field because of this would be in this direction. And this is the direction of DL. They are opposite, so it would be minus I. So this is the fourth part of the question. Is this clear, guys? Is this clear? Yes, yes. A lot of people are writing the correct answer. Plus I1, then minus I2, minus I3, minus I4. Is it clear, guys? Is it clear? First of all, tell me, is it clear or not? Is it clear or not? Everybody. Then only I will move forward. Every one of you. Is this clear, guys? I'm waiting for everybody's comment over there. Great. Done with the Ampere's law. Now we have magnetic field due to a hollow cylinder. Sir, what does hollow cylinder mean? Let me just show you what is hollow cylinder. We have a bottle over here. This is what we call the hollow cylinder, okay? Assume there is nothing inside the bottle. Assume there is nothing inside the bottle. Now, if I take this fluid out of this bottle, it becomes hollow cylinder, okay? So that's what we call the hollow cylinder. And in this hollow cylinder, listen to me. And what is the solid cylinder? In solid cylinder, we say mass is present inside also, okay? That is a solid. Sir, this is a hollow cylinder. Means inside nothing is present, only air. Now over here, this is infinitely long hollow cylinder. And in this hollow cylinder, listen to me very carefully. Listen to me very carefully. In this hollow cylinder, we say, sir, current is flowing over here. But the current is flowing through its surface only, Sir, why current is flowing through its surface only? Because it is hollow. Inside this cylinder, nothing is present. No matter is there. It is air only. Current cannot flow through air. It has to flow through this matter, through this one. It is flowing through the sides, walls of the cylinder, walls of this. You consider it as a wire, cylinder, whatever it may be. Okay. So we say in case of hollow cylinder, okay, suppose this is the cylinder, okay, bigger metal cylinder. Current flows through the surface only. So current flows through the surface only. And we say if current flows through the surface only, so current inside is equal to 0. Inside this cylinder, current is 0 because nothing is present inside. Current cannot flow through the air. So current has to flow through this, sir. Now listen to me very carefully. If current is flowing through the hollow cylinder, we know, sir, whenever current flows through a wire, it produces the magnetic field. Same is the case over here. So we say it produces the magnetic field. It produces the magnetic field. We say it produces the magnetic field. So we say it produces the magnetic field over here. Now listen to me very carefully. Listen to me very carefully, my dear people. it produces the magnetic field over here. Now we have to find the magnetic field. To find the magnetic field at the first one is, sir, if this is the center of this one, central axis, first of all we have to find the magnetic field outside of this cylinder at r distance, outside of this cylinder at r distance. Second one, we'll find the magnetic field on the surface, that is capital R, where capital R is the radius. Third one is we are supposed to find the magnetic field inside, that is at small r distance. Okay, to find the magnetic field, we say, sir, outside, we say, sir, inside, we say, sir, and on the surface, Okay, yes. Now, you guys tell me one thing over here, my dear people. That is nothing but, if I say, sir, you have got this as a cylinder, and you are looking it from very far distance. Sir, from very far distance, this huge cylinder will look like as a line only, as a wire only, simple wire only. Yes, sir. If I say I have a sapphire in my hand, okay, big sapphire, big ball, and you are looking at this ball from very huge distance, large distance. From very large distance, it will appear to you as a small point. Similarly, if you have a cylinder, okay, big pole, from very large distance, it will appear to you as a wire only, okay, thin wire only. So we say from very, very large distance, it appears as a infinite wire only. Why infinite? Because this cylinder is infinitely long. So we say magnetic field outside would be same as magnetic field because of infinite wire. We say magnetic field outside would be same as magnetic field because of the infinite wire. Okay, as simple as that, So we say, sir, this magnetic field outside would be, that is mu naught I divided by 2 pi into r, because from very large distance it appears to you as a we say that is the simple wire only. Okay, infinitely long. Now if I say, sir, at surface, can I say, sir, this r is variable. If you keep on decreasing this r, decreasing, once you reach surface, sir, at surface, this small r becomes equal to the capital R. So we say this small r becomes equal to the capital R. So we say, sir, this magnetic field on surface would be nothing but mu naught I divided by, we say, sir, 2 pi. Instead of small r, I can write the capital R over here. And when I talk about inside, sir, inside the cylinder, sir, inside the cylinder, we say current is 0. If no current flows inside the cylinder, we say, sir, if there is no current, there is no magnetic field. So we say magnetic field inside would be 0. Magnetic field inside is 0. And if somebody asks you to basically draw the graph, if somebody asks you to draw the graph between, if somebody asks you to draw the graph between magnetic field and this small r, listen to me very carefully. Sir, when it comes to inside, magnetic field is 0. Sir, magnetic field is 0 means inside. At this particular point, r is equal to 0. As you keep on moving towards right, r increases. So we can clearly say over here, sir, r is 0 at this particular line. Okay, at this particular line, r is 0. When you come out, r increases. So from center to surface, we say, sir, magnetic field is 0. So we can say, sir, from center to surface, magnetic field is 0. That's why I made it on this line only. And when you reach r is equal to capital R, at r is equal to capital R, magnetic field has some value, that is mu naught I divided by 2 pi r. So That is the value. And when it comes to outside, sir, outside magnetic field is inversely proportional to R. So it would be something like this. It would be something like this. It would be something like this. This is inside. This is inside. Magnetic field is 0. And we say, sir, this is outside. Magnetic field is inversely proportional to R. Okay, outside it is inversely proportional to R. Is this clear, guys? Is this clear, guys? And by the way, this was the question which was asked in NEET 2021. NEET 2021. This graph. What is the graph between magnetic field versus R, small r, in case of a hollow cylinder? Is that clear, my dear people? Let me know in the live chat. Is that clear? Is that clear, my dear people? In the live chat over here. Is that clear, guys? Okay. Let's move on to the next one. Now we have over here magnetic field due to a solid cylinder. Sir, solid cylinder is that cylinder in which matter is present inside also. So we say over here, sir, current is flowing through the cross section. Current is flowing through the cross section in this case. Current is flowing through the cross section. So I just write over here, in case of a solid cylinder, in case of a solid cylinder, we say current flows, through the cross section of the cylinder. We say current flows through the cross section of the cylinder. Okay, we say current flows through the cross section of the cylinder. Now see, over here, sir, current is present inside also. So magnetic field will be also inside. Okay, you cannot say magnetic field is 0 in this case. Now listen to me very carefully. We say to find magnetic field, so it will produce magnetic field. To find magnetic field, we say outside, we say surface, we say, sir, inside. Okay, these are the points where we have to find the magnetic field. Sir, when it comes to the outside, sir, from very large distance, if you see a solid cylinder or a hollow cylinder, both will appear to you as a thin wires. Okay, thin wires. So we say magnetic field formula outside would be same for the solid cylinder like this, because from very large distance both appear to you as a thin infinite wires. So we say magnetic field outside would be mu naught I divided by 2 pi the small r, where small r is the distance at which you are basically finding this magnetic field. Clearly you can see, sir, B outside is inversely proportional to small r. Okay. And sir, when it comes to the surface, at surface, we say R is equal to capital R. So magnetic field at surface would be mu naught I divided by 2 pi, and this is capital R. Okay. And when it comes to, sir, inside, sir, in this case, inside current is present. So you cannot say magnetic field inside would be 0. So we say, sir, magnetic field inside is simply, that is mu naught I into R, divided by, we say 2 pi into capital R square, where R is the distance, listen to me very carefully, where R is the distance inside from this, see, R is variable. R is this much also, R is this much also. This is small r. Okay, this is small r. So small r inside, and this is the radius. This is the radius. where capital R is the radius and small r is the distance at which you are finding the magnetic field inside. Okay, just remember these formulas directly over here. This is inside, this is the surface, this is the surface, and this is, we say, outside. These are the three formulas that you people are supposed to remember over here. Okay, now if somebody asks you to draw the graph between magnetic field if somebody asks you to draw the graph between, we say, sir, magnetic field versus R in case of a solid cylinder. Now listen to me very carefully. Sir, when it comes to magnetic field outside, it is inversely proportional to R. Clearly you can see over here. Sir, magnetic field outside B is inversely proportional to R. And sir, on the surface, it is mu naught I by 2 pi R, constant. And sir, when it comes to inside, magnetic field is directly proportional to R. Sir, B in is directly proportional to R. So we say, sir, B in is directly proportional to R. Listen to me very carefully. Sir, at this particular point, we say R is equal to 0. Now, from center to surface, that is inside, from center to surface, B is directly proportional to R. So clearly we can say graph would be the straight line. B is directly proportional to R, and this is inside. This is inside. Okay. And this would be basically R is equal to capital R. This is the surface. And outside the surface, B is inversely proportional to R. So graph would be something like this. So B is inversely proportional to small r, and this is outside. This is outside. This graph is also very, very important. Very, very important. Inside it is directly proportional to R. Outside it is inversely proportional to R. Is that clear, my dear friends? And this graph was unfortunately asked in, we say, NEET 2020. The graph for hollow cylinder was asked in NEET 2021, and this was asked in NEET 2020. Is that clear, guys? Let me know in the live chat. Give me the signal in the live chat if this is clear to each and everyone. Give me the signal in the live chat if this is clear to each and everyone. Okay, we have a question. We have a question over here. Okay. Last time also I told you don't make this chat as that platform, okay? I don't want to use that word. Okay, now listen to me very carefully. We have a question over here. A long straight wire of radius R carries a steady current I. The current is uniformly distributed in its cross section. Okay, means it is talking about the solid cylinder. It is talking about the solid cylinder. We have a wire, okay, and this wire is something like this. This is the wire. Okay, this is the wire, or this is a cylinder, whatever you call it. And Through this cylinder, current I is flowing, and it is saying current is flowing through the cross section, means it is a solid cylinder. The current is uniformly distributed its cross section. The ratio of magnetic field. Now, if I just tell you in this case, this radius is given as A. The ratio of magnetic field B and B dash at distance A by 2. We are supposed to find the magnetic field at A by 2 distance, that is inside. And we are supposed to find the magnetic field at 2A distance, that is outside. Okay. We are supposed to find the magnetic field inside, that is B. And we are supposed to find the magnetic field outside, that is B dash. We have to find the ratio. We are given a wire over here. This is a solid cylinder. Current is flowing through the cross section. So we have to find the magnetic field inside. We have to find the magnetic field outside because of it. And we have to find its ratio. Divide them and you'll get the ratio. Now, when it comes to inside, listen to me very carefully. Sir, we know inside formula is B is equal to mu naught I divided by mu naught I into R divided by, we say 2 mu naught I into R divided by 2 pi R square. Mu naught, just a second, mu naught this I, mu naught I divided by mu naught I into small r, then we have 2 pi into capital R square. Okay. This is the magnetic field because of the solid cylinder inside. Now over here B is equal to mu naught I. And when it comes to this R, what is the value of R inside? That is A by 2. R means A by 2 over here. At what distance you are finding? So that is A divided by, I'll write the 2 over here. Then you have this 2 pi into R. R is how much? R is the radius of this one. And that is A. That is A square. I'll write A square, capital R square, A square. Now this A and this square will get cancelled out. So magnetic field inside would be mu naught I divided by 4 pi A. Now let's find the magnetic field outside. Sir, for outside we know the formula. What is that? That is mu naught I divided by 2 pi R. And we say, sir, this B outside B dash is nothing but mu naught I is the current, that is 2 pi. When it comes to R is what? For outside point, small r is 2A. So that is nothing but, we say 2A. So it would be mu naught I divided by 4 pi into A, 4 pi. Sir, inside it is mu naught I by 4 pi A. Outside it is mu naught I divided by 4 pi A. It is same. So can I say over here B upon B dash? This is what we were supposed to calculate. That is mu naught I divided by 4 pi A upon, instead of this also I can write mu naught I divided by 4 pi A. This and this will get cancelled. So 1 upon 1. 1:1 is the ratio over here. So option number C. Is that clear, guys? Every one of you? Is this clear to each and every one? Let me know in the live chat. We are moving to the next topic now. That is magnetic force. Is this clear to each and every one, guys? Yes. Okay. Great, great, great. Now let's talk about the magnetic force. What is this magnetic force all about? See, it is mentioned on the screen. We say if we have a magnetic field over here, let's suppose we have a magnetic field over here, and we are representing this magnetic field with cross. Cross means it is going inside, and in this region magnetic field is present, and this magnetic field has a direction which is inside. It is going inside the board. Okay, I can also make outside the board, that is with the help of dot. Now if we place a charge inside this magnetic field, something like this, okay, and we give it some velocity, let's call that velocity v. We are not just placing the charge inside the magnetic field, but we are giving it some velocity v inside the magnetic field. So we say whenever a charge is placed in a magnetic field and given some velocity v, sir, magnetic force acts on it. We say magnetic force acts on it. Like I have told you, if we have electric field E, and if we place a charge inside this electric field, sir, electrostatic force acts on it, that is Q times of E. But over here, if we have magnetic field B, if you place the charge Q inside it and give it some velocity, so we say magnetic force will act on it. Sir, if we do not give the velocity to it, will the magnetic force act? We say no, magnetic force would be zero. Sir, over here, if the charge is at rest, will still electric force act? Yes. So now that's what is mentioned over here. If a charge is placed in a magnetic field, and is given some velocity v, some velocity is given to it, okay, some speed is given to it, we say magnetic force acts on it. Now the question is, how much will be that magnetic force? We say, sir, that magnetic force will be Q V B sine of theta. Sir, what is Q? Q is the charge. What is V? V is the velocity. What is B? B is the magnetic field. And this is the theta. Theta is the angle between V and B. Okay. I say where Q is the charge. Q is the charge. And then we say V is the velocity. Okay. B is the magnetic field. And theta is the angle between V and B, velocity and magnetic field. Theta is the angle between velocity and magnetic field. And you can also say, sir, as this magnetic force FB is equal to QVB, then we say sine of theta. You can also say in the vector form, it is Q into V cross B. Q into V cross B. Okay. This would be the force in vector form. Sir, V cross B is VB sine theta. A cross B is AB sine theta. Similarly, it is VB sine theta over here. Is that clear, my dear friends? Write it. If we say velocity is 0, we say, sir, magnetic force in that case would be 0. Okay? Yes, sir. Now the question is over here. If I say, let's suppose, let's suppose the magnetic field is in this direction. Magnetic field is in the forward direction. Okay. And this is the charge which is also moving in the forward direction. This is the magnetic field. And this is the charge which also moves in the same direction. In this case, you can see, sir, theta is equal to 0 degrees. angle between magnetic field and velocity is 0 degrees. And if I ask you to tell me how much is the magnetic force, you say, sir, Q, V, B, sine of 0 degrees over here. Why? See, over here you have magnetic field, you have you have charge placed in it, and it has got velocity also. But still, in this case, magnetic force is 0. Why? Because angle between V and B is 0 degree. They are in the same direction, parallel. So we say sine 0 is 0. Magnetic force in that case would be 0. Okay? So we say in that case, magnetic force would be 0. Now, if I say, let's suppose something like this. You have got this magnetic field in the forward direction. And this is the charge which is moving in the backward direction, V. And if I ask you to tell me the magnetic force in this case, you say, sir, magnetic force will be QVB sine of. What is the angle between V and B over here? Sir, V is in the backward direction velocity. Magnetic field is in the forward direction. We say, sir, it is 180 degrees. So it will be sine of 180 degrees. So we say sine 180 is also 0. So magnetic force would be 0 in that case. Is this clear to each and everyone, guys? Now, this was basically the case number 2. This was basically the case 2. And this was basically the case 1. Case 1. Now, let's talk about the case 3. Let's talk about the case number 3. Let's talk about the case number 3. You have this magnetic field, something like this. You have this magnetic field, something like this. This is B. Okay. Now, listen to me very carefully. And you have this charge over here. You have this charge over here. Thanks, bro. Why they were my attention? You guys want some tea? You guys want some tea? Sir, is HCV problem practice after session enough for board preparing NEET students? HCV is not for NEET students, guys. Just focus on the previous year questions and the questions which I show you in the sessions. That's it. And NCERT, okay. Whatever the questions are mentioned in the NCERT, be it examples or the questions, you can solve those. No. Not now. We'll take a break at 11. It's 10 o'clock right now. We'll take the break at 11 o'clock. I am showing you the tons and tons of questions, okay? And I'm not leaving any single topic. We'll be completing both the chapters today. The point is you guys stick in this particular class till the end and we'll kill it. Okay. No. It's not noon chai. Minkan kuch chai noon chai. Okay. I'll send you all the PDFs today for capacitors, for current, as well as for the magnetism. Don't worry about that. You'll get the PDFs by tomorrow, that's for sure. Now see, let's suppose this is the case 3. Over here you have got the magnetic field, you have got the charge in it, and this charge is moving with a velocity v. And clearly, can you tell me what is the angle between, how much is the angle between velocity and magnetic field? You say, sir, 90. How? Magnetic field is in the inward direction and velocity is in the forward direction. How much is the angle? 90. Sir, this is forward velocity and this is inward. Angle is 90. And how much would be the force in this case? Magnetic force would be QVB. Then we have sine of 90 degrees. So we say magnetic force would be QVB. Sine 90 is 1. That is QVB over here. Okay. Next we have, this is done. This is also. Motion of a charged particle in magnetic field. Motion of a charged particle in magnetic field. Placed perpendicularly. Let's suppose you have got a magnetic field over here. This is the magnetic field you have got. Okay, this is the magnetic field B. Now we say you are sending a charge inside this magnetic field, something like this. Listen to me very carefully. When you are sending the charge inside this magnetic field, something like this, we say here theta is equal to 90 degrees. Means charge is entering the magnetic field perpendicularly, because theta is equal to 90 degrees between magnetic field and velocity. Whenever the charge enters the magnetic field perpendicularly, remember this, whenever the charge enters the magnetic field perpendicularly, it follows or it moves, it follows the circular path. It follows the circular path. So means whenever the charge enters the magnetic field perpendicularly, it follows, we say, the circular path. It follows the circular path. It moves in a circle, and this circle has a radius r. Remember this from now onwards. Whenever the charge enters the magnetic field perpendicularly, then which path does it actually follow? We say, sir, it moves in a circle, it does the circular motion, so it follows the circular path. Now you guys tell me one thing. We say over here, if this charge follows the circular path, we say one force will act over here on it. That force is what we call the centripetal force. Whenever any particle performs the circular motion, we say centripetal force acts on it. So we say centripetal force acts on it. Centripetal force acts on it. Whenever the charge moves in a circle, it follows the circular path, we say centripetal force acts on it. And that centripetal force, Fc, is equal to, we say, mv square divided by, we say, r, where m is the mass of the charge, v is its velocity, and r is the radius of that circle. R is the radius of that circle. Okay. Now, sir, you recently told us whenever the charge enters the magnetic field, one more force acts on it. That is nothing but, we say, sir, what? That is magnetic force. So we say over here also, magnetic force acts on it. We say magnetic force acts on it. So what is the value of that magnetic force? Sir, the value of that magnetic force, you recently told us, QVB sine of theta. And in this case, sir, theta is 90 degree. So force would be, sir, F is equal to QVB, because sine 90 is 1. Okay. Now I say here, this centripetal force is equal to, sir, magnetic force. Sir, in this case, we say centripetal force is equal to the magnetic force. Okay. Now, when it comes to the centripetal force, what is the formula for centripetal force? That is mv square by r. Okay. So we say, sir, this is mv square divided by r, where r is the radius, is equal to, sir, what is the value of FB? FB in this case, mv square by, we write capital R. We say, sir, when it comes to this is R. And what is the formula for FB? That is magnetic force QVB. Okay. Don't say why centripetal force is equal to the magnetic force. I have given you the explanation so many times before also. Centripetal force is not the real force. Okay. This centripetal force is being created because of the magnetic force only. That's why both are equal. Now see over here. Sir, this square and V will get cancelled out over here. So what remains in this case is, we say, sir, this would be MV by R is equal to, sir, QB. Now over here you take it over there. So R will come out to be MV divided by QB. So this is the value of R. This is the radius of that circular path. This is the radius of that circular path in which that charge actually moves. Now, if I ask you radius, to find the radius in terms of kinetic energy. See, we got the value of radius. It is in terms of, we say, MVQB. But we have to find that expression of radius in which kinetic energy is present. Listen to me very carefully. Sir, we know kinetic energy is equal to 1 by 2 mv square. Okay. If we have a mass, it is moving with the velocity v, its kinetic energy is 1 by 2 mv square. Now multiply with m and divide with m. So this kinetic energy will come out to be 1 by 2m. Okay. M into 2 is 2m. And this would be m square into v square. This is m square into v square. M into m is m square and v square upon 2m. Now take it over there. So it will be 2m. Then we have kinetic energy is equal to, we say, m square v square. Instead of these squares, take the root over there. So we say mv is equal to under root of 2mke. So this mv is equal to under root of 2mke. Now call this as equation number first. We say put mv in equation number first. I want you guys to put this equation in the first, put this mv in equation first. So when you do that, you can write this radius is equal to, see, instead of this mv, can I just write, sir, under root of 2mke? Yes, sir. So we say this is under root of, we say this is under root of 2mke divided by, we say, sir, qb. And this is the formula for radius in terms of kinetic energy. This is the formula for radius in terms of kinetic energy. Once this was asked in AIPMT. This is the formula for radius in terms of, we say, QBMV, and this is the formula of radius in terms of kinetic energy. This is the formula in terms of velocity. This is the formula in terms of kinetic energy. You can say it something like that. Is that clear, guys? Is that clear, everybody in the live chat? Okay, one more thing I just want to tell you. This is the equation number first. As we say, sir, radius is equal to mv divided by qb. Can you find the value of velocity over here also? What is the velocity of the charge? Take it over there. So this will be, sir, r qb divided by m is equal to velocity v. So this is the formula for velocity. This is the velocity with which charge is moving, This is the formula for velocity with which charge is moving. Okay. Now if I ask you the time period, Sir, what is time period? See. Time period is nothing but, if I tell you over here in this particular case, this charge is performing the circular motion. Sir, in how much time it will complete one cycle or one circle? That's what we call the time period. I say it is the time in which it completes, we say one cycle. It is the time in which it completes one cycle. That's what we call one time period. Now listen to me very carefully over here, my dear people. Sir, this time period, we know one formula, velocity is equal to distance upon time. Now over here, we say, sir, time is equal to distance upon velocity. Now if this charge is moving in the circle, this circle has radius r. Okay. Now, can you tell me what is the distance of this complete circle? Because if it is completing this one cycle, means it is completing the circumference. Yes, sir. So we said this distance is nothing but 2 pi r. If this is completing one cycle, means distance it is completing how much? 2 pi r. And velocity we recently got. So we say, sir, this time period is equal to, that is, distance is how much? That is 2 pi into r upon velocity is how much? That is q b r divided by m. R and r will get cancelled. We can take this in the numerator. T is equal to 2 pi m divided by cube b. 2 pi m divided by qb. This is the value of time period in that case. Is this clear, guys? Is this clear to each and every one? All these expressions are important over here. This one, and this one also. Okay, this is a motion of a charged particle placed perpendicular in uniform magnetic field. Is this clear to each and every one, guys? Let me know in the live chat. Let me know in the live chat if this is clear to each and every one. All the people out there, guys. Everybody. Guys, make sure you like this session, okay? I'll be sending you the PDFs of the capacitors as well as for this. Capacitor, current, electricity, and magnetism, both. All the 3 chapters, don't worry. Don't worry about that. Chill scenes, guys. Okay? Now see. Over here in this particular case. See, guys, listen to me very carefully over here. Now see. This was the question asked in NEET 2019. An ionized hydrogen atom and alpha particle. When it comes to the ionized hydrogen atom, it is nothing but, ionized hydrogen atom is nothing but, we say it is nothing but, it is one proton. Okay, it is one proton. And one proton has the charge E. Charge on a proton is E. Charge on 2 protons is 2E. Ionized hydrogen atom means proton. Simply remember it. And then we have an alpha particle. When it comes to alpha particle is made up of, we say, 2 protons and it is made up of 2 neutrons. And if I ask you how much is the charge on alpha particle, sir, we say neutron has no charge, it is neutral. Proton has charge E, so 2 protons has charge 2E. So alpha particle has charge 2E, ionized hydrogen has charge E. Now, in this question, it is given ionized hydrogen atom, alpha particle with the same momenta enters the constant magnetic field B. We have got a constant magnetic field over here. This is the constant magnetic field in this case. Now, over here it is saying that the ionized hydrogen atom enters this constant magnetic field, okay? And it is also saying that, sir, this is the magnetic field, okay? This is the magnetic field B. So we say hydrogen atom enters this constant magnetic field and alpha particle enters this constant magnetic field. Now we know, sir, both are having the charge. This has charge E, alpha particle has charge 2E. So this will perform the circular motion. We know when a charged particle enters the magnetic field, it performs circular motion. This will also perform the circular motion. Now this will have the radius. This will also have the radius, okay? And we are supposed to say this will be the radius of hydrogen atom. This will be the radius of alpha particle. We are supposed to say what is the radius of, we say radius of hydrogen upon radius of alpha particle in this case. This is what we are supposed to find in this particular case. Listen to me very carefully. Sir, when it comes to the formula for radius, we say radius is equal to mv divided by qb. mv by qb. Sir, what is momentum? Momentum is nothing but P is equal to mv. The formula for momentum is P is equal to mv. If you have a mass, it is moving with some velocity v, it will have momentum P is equal to mv. Now over here in this question, it is saying that ionized hydrogen atom and alpha particle have same momentum. Both have got same momentum. So we say, sir, both have got mv same, alpha particle as well as hydrogen atom. Sir, magnetic field is also constant. So we say this is same for both. If this is same for both, so we say R is inversely proportional to the charge Q. Yes, sir. Now, radius only depends upon charge in this particular case. So when we talk about radius of hydrogen atom, it is 1 upon charge. Charge on ionized hydrogen atom is how much? That is E. So this is 1 upon E. Sir, when it comes to the radius of alpha particle, it is nothing but 1 upon 2E. And when we write RH divided by R alpha, it would be simply 1 by E upon 1 upon 2E. So it would be 2E divided by E. Will cancel 2 by 1. So answer is 2 is to 1. So which option is correct over here? We say, sir, 2 is to 1. Is that clear? Is that clear, guys? Is that clear, guys? This 2 is to 1. Now, charge is projected at an angle theta. Let's suppose you have got the magnetic field something like this, okay? You have this magnetic field. It is in the forward direction. Now over here, you are sending the charge something like this, okay, with a velocity v. This is the charge q. You are sending the charge q with a velocity v. It is making an angle theta. Sir, what is the previous case that you showed over here? Listen to me very carefully. We say motion of a charged particle placed in a magnetic field placed perpendicularly. You are sending the charged particle perpendicularly inside. Magnetic field is inwards. Charge is moving in the forward direction. Angle between the two is how much? We say 90 degrees. So that's, we say, perpendicular case. But right now, my dear people, we are sending the charge at an angle theta. It is not making 90 degree angle. This is magnetic field, this is V. Now we say over here, Sir, this has two components, this velocity. First one is v cos of theta, and the second one is we say v sine of theta. V cos of theta and v sine of theta. Now over here, sir, we say whenever the charge enters the magnetic field at an angle theta. Theta can be anything, okay, but not 90 degrees. At an angle theta, then it follows helical path. Then we say it follows helical path. Which path it will follow? It will follow helical path. Sir, what is helical path? Helical path is something like this. This is what we call the helical path. Okay. Helical path means the charge is moving in circle, but at the same time it is also moving forward. Sir, what is the circular path? Circular path is this one, okay? It is only moving in circle. It is not moving forward. But what is helical path? It is completing the circle as well as at the same time it is moving forward. That's what we call the helical path. Now over here we say when it comes to the radius of this circular path, we say, sir, radius would be simply, we know formula for radius is mv divided by qb. In this case, listen to me very carefully, sir. The velocity and magnetic field are in the same direction. We said this v cos theta will not contribute force because of v cos theta is 0. Because whenever this velocity and magnetic field are in the same direction, force is 0. So it will not contribute to its motion. So we say over here, sir, this radius would be simply m. Instead of v, we put over here v sine theta. And divided by, we say, sir, qb. Okay, divided by qb. Now, my dear people, listen to me very carefully. Just in case of radius, you have to write, instead of velocity, you have to write r. You have to write v sine theta. Okay. And one more thing I just need to tell you in this case. That is nothing but when it comes to the time period. So what is the value of time period? So time period over here, in case of circular path, it was 2 pi m by qb. Over here, in how much time it will complete one cycle. One cycle is one circle, completing one circle. That will be same. That is how much it was over here? 2 pi m by qb. That is 2 pi m divided by qb. In this case, no velocity term is there. So that's why time period would be same. But when it comes to the radius, you have velocity over here. It will be v sine theta. Okay. It will be v sine theta. Okay. Because magnetic force due to the v cos theta, it would be 0. So v sine theta will contribute to the magnetic force. We say v sine theta will contribute to magnetic force. Because of v cos theta, magnetic force is 0. Why? Because this is along the magnetic field. Force on a wire, is this clear, guys? I say when it comes to the charge which is placed at some angle inside the magnetic field, it will follow the helical path. And second, the radius of these circles are r is equal to mv sine theta by qb. Instead of v, you write v sine theta. That's it. But time period remains same. Is this clear, guys? Session duration will be 8 hours, okay? 8 hours is the duration of the class. Now see. Force on a wire placed in a magnetic field. Force on a wire placed in a magnetic field. Let's suppose we have a magnetic field over here. This magnetic field is, we say, sir, inward magnetic field, okay? And in this inward magnetic field, we are placing a wire. This is a wire which is placed inside this magnetic field. In this wire, current is flowing, let's suppose I. This is a wire, okay? We say current is flowing I. And listen to me very carefully. And let's suppose the length of the wire is L. Length of the wire is L. We say whenever a wire carrying we say current I is placed in a magnetic field, force acts on it, okay? Previously I told you, whenever we place a charge inside a magnetic field, force acts on it and that charge should be moving with some velocity. But over here, when we place a wire inside the magnetic field, we say force acts on it. And that force will be how much? We say, sir, that force is simply I L B. Then we have sine of theta. Sir, what is I? I is the current flowing in the wire. Sir, what is L? L is the length of the wire. I write over here where I is the current in the wire. I is the current in the wire. We say L is the length of the wire. And then we say B is the magnetic field. And what is this theta, sir? We say, sir, this theta is the angle between we say L and B, where theta is the angle between L and B. And in this case, sir, this is the length, and B is inward. Sir, angle between length and magnetic field is 90 degrees in this particular case. So we can write this equation first as from equation first C. We can write this F is equal to, what is the formula? Sir, ILB, we say sine of theta. We can write this as F is equal to I into, we say L cross B. Sir, this is the force in vector form. This is the force on a rod in vector form. This is the force on the wire in vector form. Okay, that is L cross B is LB sine of theta, where theta is the angle between length and magnetic field, If I ask you the question over here, let's suppose I ask you the question, I have got a magnetic field over here. This is the magnetic field over here, that is B. And inside this magnetic field, I have placed a semicircular wire. The radius of this is R. And current, we say I is flowing inside this wire. You guys are supposed to tell me the magnetic, you guys are supposed to tell me force on the wire. Find force on the wire. Okay. Find force on the wire. Let me know the answer of this question in the live chat. I'll give you the break at 11 o'clock. Find force on this wire. Sir, when it comes to the force, we say, sir, force is F is equal to I L B. Okay. Sine of theta. Sine of theta. In this case, sir, angle between, listen to me very carefully. Sir, length of this is how much? See which length we are going to take. We'll take the effective length. What is effective length? Take this point, one end of the wire, another end of the wire, and join these two. Sir, this much is R, this much is also R. So how much is the length between these two ends? Sir, that is 2R. So we say this is what we call the effective length. That is 2R. We don't have to take the length of the entire wire, but we have to take effective length, that is 2R. So we say, sir, this force is nothing but, we say I. I is the current in the wire. Sir, L. Instead of L, I can say, sir, this is 2R. Okay. Then B. B is the magnetic field. Sine theta. Angle between length and magnetic field, sir, that is 90 degrees. So sine of 90. So force will be IB2R. This is the force. And one more important thing I just need to tell you in this case, the direction of the force. See, how to find the direction of force? Place your fingers along the direction of this. Let me just write it over here. I say direction of force. See, how to find the direction of force? First, I say place your fingers along length. Okay, place your fingers along length. Then curl towards magnetic field. Curl towards magnetic field. Let's suppose we say I have a rod over here. Okay, in this rod, current I is flowing and the length of the rod is L. This is the magnetic field inward. Sir, place your fingers along this rod and curl it towards the magnetic field. Thumb is pointing in this direction. So we say this is the magnetic force over here. This is the magnetic force over here. Okay. Is that clear, guys? Now see, let's move on to the next one. Over here, listen to me very carefully. Force on I2. Okay, now see over here. Let's suppose, so I told you, if we place a wire in a magnetic field, force acts on that wire. That force is equal to ILB sine of theta. Okay, ILB sine of theta. Similarly, now the question is, if I have two parallel wires, this is force between two parallel wires. We call it force between two parallel wires. See, let's suppose we have over here a wire. This is a wire, okay? And this is, we say, let's suppose this is, we say, infinitely long. This is, we say, infinitely long. Listen to me very, very, very carefully. This is infinitely long and this is infinitely long in this case. Now, my dear people, I need to tell you something. If I say, sir, in this wire current I1 is flowing, And I have placed one more wire over here, which is at R distance. And in this particular case, current I2 is flowing. Now, we are supposed to find how much will be the force on this wire because of this I1. So that is force between two parallel wires, or force on I2 wire due to I1 wire. Sir, will this wire create force on this one? Yes. We said to find force on I2 wire due to I1 wire. Sir, this wire will create force on this wire. We need to find that force. Listen to me very carefully. Sir, if we say, sir, because of this wire, at this point, magnetic field will be there. So we say, place your thumb along the direction of current and curl your fingers over here. We say, sir, magnetic field will be inwards. Sir, this is the magnetic field because of this wire. Okay. So wire 1 is creating the magnetic field over here. Wire 1, I1 is creating magnetic field near, we say, sir, near I2. So if wire 1 is creating magnetic field B, so in that magnetic field we are placing I2 wire. So obviously it will experience force. Why, sir? Because I just told you, whenever we place a wire in a magnetic field, it experiences force. As simple as that. Same is the case over here. Same is the case over here. Same is the case over here. Sir, if we place a wire inside a magnetic field, it will experience force. Where does this magnetic field come from? Because of this one. My dear friends, this I1 wire creates the magnetic field over here. And in that magnetic field, we have placed another wire. That's we say I2. And how much will be that magnetic field? That magnetic field would be simply, listen to me very carefully. That is, we say, because of infinitely long wire, magnetic field at R is mu naught I divided by 2 pi into R. And I in this wire is I1. Now, if we have placed this wire I2 in that magnetic field, it will experience force. As I2 is placed in that magnetic field, so it experiences force. And what is the value of that force? We say the value of that force will be, listen to me very carefully, the value of that force will be ILB sine of theta. Sine theta is 90 degree over here. So we say the length of this wire is L. Length of this wire is L. Now we say, listen to me very carefully, sir, this F is equal to I. I means if we have placed this wire in this magnetic field, so instead of this I, we write this I2. So we say, sir, this is I2. Then we have length of the rod, that is given as L. So I'll write this as L. And then we have, sir, this magnetic field. Listen to me very carefully. How much is this magnetic field? Mu naught I1 2 pi R. Mu naught I1 divided by 2 pi R. So this will be mu naught into I1 divided by 2 pi into R. So we say this force is nothing but mu naught I1 I2 divided by 2 pi R into, we say, L. Just keep this in your mind. So this is the force due to one wire onto another. So we say this is the force because of I1 on I2. This is the force because of I1 on I2. Now if I ask you over here, force per unit length. Force per unit length. Sir, what is the force per unit length? What does that mean? That means force on the unit length of the rod. Force on the unit length of the rod. Sir, we say over here, If we take a unit length over here, on its unit length, how much force will act? This is the force on the entire rod. But on the unit length, how much force will be? Sir, that is force per unit length, F by L. So that will be F divided by L is equal to this entire length, this entire force divided by L. That is mu naught I1 divided by I2 upon, we say 2 pi R, and this is L divided by L. L will get cancelled out. So we say force per unit length would come out to be mu naught I1 I2 divided by 2 pi R. Mu naught I1 I2 divided by 2 pi R. Is this clear, guys? This will be the force per unit length. Okay. And this will be the force on entire wire. This is the force on the entire wire I2 due to I1. Is that clear, guys? Is that clear? Let me know in the live chat. Is that clear, guys? And how to find the direction of that force? See, place your fingers along the direction of this wire and curl it towards magnetic field. Thumb is pointing in the left, so this will be the direction of magnetic force. This will be the direction of magnetic force. Is that clear, guys? Okay. Now see, let's solve this particular question. Guys, if you are not like the session, like it as soon as possible. Now see, listen to me very, very, very carefully. Over here, we have got, let me just show you, let me make the figure. We have got a wire something like this. We have got a wire something like this. We have got a wire something like this, okay? And this is the wire C, this is the wire B, and this is the wire A. Sir, what is this? This doesn't look like a wire, it is the dot. This is a wire which is coming out of the board, out of the plane, okay? It is not like this is along this plane, but this wire is coming out of the plane, something like this. This is also coming out of the plane. And in this wire, current I is flowing. In this wire, current I is flowing. In this wire, current I is flowing. Same current is flowing in all the three wires over here. And in this case, this distance is given as a D. Okay. This distance is also given as a D, small d. This distance is given as small d, and this distance is also given as small d. You guys are supposed to tell me the net force on wire B because of these two wires. As we know, when the two wires are placed parallel to each other, we are supposed to find the net force in that case. Okay? We are supposed to find the net force in that case. Listen to me very carefully. Over here, I told you, whenever we have two parallel wires, sir, they apply force on each other. This wire attracts this wire towards itself. You can clearly see over here. See, this force is towards this wire. This is the force on this wire because of I1. Force on I2 because of I1. Same is the case over here. If you take a look over here, my dear friends, we say, sir, we are supposed to find force on B because of C and because of A. We know, sir, this force will be something like this. Let's call this as F. This is the force because of C on B. Similarly, this wire A will also attract this wire towards itself with the same force F. Why same force? Because the distance between these two is D. Distance between these two is also D. In this current is I. In this also current is I. That's why the force will be same. Okay. Now, and this is, now listen to me very carefully. One force is in this direction, another force in this direction. Sir, their net will be, this angle is 90. So their net will be, net force is simply under root of 2 into F. Because whenever the angle between two forces is 90, we say, sir, net force is root 2 of F. Net force is root 2 of F. And in this particular case, we are supposed to find force per unit length. As you say force, what is force per unit length? Force on unit length. This is force per unit length. This is complete force on the rod. So this is force per unit length. Mu naught I1 I2 divided by 2 pi r. Now you guys tell me one thing. Sir, we have to write net force will be, sir, under root of 2. What is the value of F? F is the force on this wire because of this, or force on this wire because of this. Anyone you can write, it's one and the same thing. Sir, what will be that value? Sir, mu naught I1. I1 is the current in any one wire. I1 is the current in this wire. That is I. I2. I2 is the current in another wire. That is also I. So means I into I is I square. Divided by 2 pi r. R is the distance between them. How much is the distance between them? That is D. Okay. Mu naught. Which angle is mentioned? Okay. So we say, sir, net force in this case will be, that is mu naught I square divided by 2 pi D, and we have, sir, root 2. We have this root 2. Now what I want you guys to do is, let me just write over here, sir, F net is equal to mu naught I square divided by 2 pi D, mu naught I square divided by 2 pi D, and we have this root 2. What I want you guys to do is multiply with root 2 and divide with root 2. Sir, this root 2 into root 2 becomes 2. So you can write mu naught I square. Root 2 into root 2 becomes, sir, 2. Okay. So this is 2 upon, this is 2 pi D into this root 2. 2 and 2 will get cancelled. It will be mu naught I square divided by pi D root 2. Which option is matching? Mu naught I square pi D into root 2. Option A. Is that clear, guys? Let's talk about magnetic dipole. Listen to me very carefully. Let's talk about magnetic dipole. Is the previous question clear or unclear? Let me know, guys, in the live chat. Is the previous question clear or unclear? I have already explained the direction over here. In this case, direction will be towards this wire. See over here, I have told you when it comes to the force on this wire, it is towards that wire. Similarly, same is the case over here. Use the same logic and you will get the direction. Okay. Now see, magnetic dipole. Sir, what does magnetic dipole actually mean? Do you guys know what is electric dipole? Similarly, we have the magnetic dipole. Okay. Sir, when it comes to the electric dipole, we were having the charge minus Q. We were having the charge plus Q. Okay. Whenever you have two equal and opposite charges separated by some distance d, this is what we call electric dipole. This is what we call electric dipole. Okay. And we know this electric dipole has a dipole moment P. And this dipole moment was equal to the charge multiplied by distance between them. This we have already studied. Charge multiplied by distance between them. Same is the case over here. We have the magnetic dipole. Sir, what does magnetic dipole mean? Magnetic dipole means you have minus M, you have over here plus M. Sir, what is this minus M? Minus M is the pole strength. You'll get to know after some time. And the distance between them is, let's suppose, D. This is what we call the magnetic dipole. Like you have the charge minus Q, you have the charge plus Q. Similarly, you have the minus M, you have the plus M. Distance between them is D. This is what we call the magnetic dipole. And over here also you have magnetic dipole moment M. And that magnetic dipole moment is equal to, sir, pole strength. Okay, that is M. How much is the pole strength? Multiplied by distance between them. Okay, this is the magnetic dipole. Sir, give us the actual feel of magnetic dipole. I say, go to the shop and buy a bar magnet over there. We have a magnet, that bar magnet, okay, rectangular in shape. Go to the market and shop. I'll be teaching the moving coil galvanometer also. Wait for some time. Galvanometer is here, guys. Every topic I have mentioned, wait for some time. This is the galvanometer, moving coil galvanometer. Wait for some time. Let me first complete rest of the topics. This is my sequence. I have arranged the topics according to my way only. Wait. Chill. Solenoid will also show. Don't worry. Wait. Now, see over here. See, sir, when it comes to the magnetic dipole, I say you go to the market and you buy a bar magnet over there. And that bar magnet, okay, that you have seen, go to the market and buy that rectangular shaped bar magnet. And we say this bar magnet has, this is what we call the north pole, and this is what we call the south pole over here. Okay, this bar magnet has north pole and we say exactly south pole. Okay, so we say this is minus M, this is exactly plus M over here. Okay, is that clear, guys? Now, sir, we say, what is this M? This M is nothing but pole strength of this pole. Okay, this is south, this is north. This is south, this is north. Minus M we represent with south pole. This is north pole. So we say over here in this particular case, this is basically a bar magnet. This is bar magnet. And From this point to this point, this is what we call the distance between them. Let's call this as a d. And this is what we call the magnetic dipole. If you go to the market, over there, if you buy a bar magnet, this bar magnet has a pole strength. Okay, this is another pole, this is one pole, this is another pole. So we say it has a pole strength. That is represented by, we say minus m and plus m. We say that is represented by minus m and plus m. Is it clear, guys? Like you have electric dipole. Okay. So when it comes to, sir, magnetic dipole moment. Sir, magnetic dipole moment we represent with m, that is equal to, we say pole strength. Multiplied by distance between them. Pole strength multiplied by distance between them. Sir, this magnetic dipole moment is equal. Pole strength is how much? We say, sir, m, and distance between them is, sir, d. And the direction of this magnetic dipole moment is from minus m to plus m. Direction of magnetic dipole moment. We say dipole moment is from minus m to plus m. It is from minus m to plus m. From minus m to plus m, the direction of magnetic dipole moment will be there. Okay. See, it is exactly like we have an electric dipole. Similarly, in magnetism, we have a magnetic dipole. Sir, we represent magnetic dipole with a bar magnet. Bar magnet is magnetic dipole, and this bar magnet has a pole strength. This is one pole, this is another pole. Like you have south pole of the magnet, you have north pole of the magnet. So we say over here, this is the pole strength and this is the pole strength. And it also has a magnetic dipole moment that is from, we say, this minus m to plus m. This is from minus m to plus m. Okay. So simply, this minus m is nothing but south pole and this is nothing but north pole. If you go to the market, if you buy a bar magnet, this is south pole, this is north pole. This is the strength of south pole, this is the strength of north pole. As simple as that. Now, if I, let's suppose, take a bar magnet over here, and this bar magnet has got a pole strength of m. If you cut this magnet along its length, cut along length, now finally it would be something like this. Sir, what will happen to the pole strength? Sir, we say pole strength in this case will be halved. Okay? Over here it was m. Over here it becomes m by 2. Why? Because you have basically splitted this into two parts. Okay? So this is m by 2, m by 2. And now, if I ask you what is the magnetic dipole moment over here, you say, sir, that is pole strength multiplied by distance between them, that is m into L. And when it comes to the over here, sir, what is the magnetic dipole moment of this one? Say, sir, that is pole strength. Pole strength is m by 2. And the distance between the poles is how much? That is, we say L. So we say ml divided by 2. For this also it is ml divided by 2. Now, if I have a magnetic dipole something like this, and if you cut it along breadth, so it will be something like this. Over here, if I say this length is, let's suppose, L, sir, this length will be L divided by 2. This length will be L divided by 2. But when it comes to the pole strength, sir, pole strength remains same over here. Okay. This pole strength remains same if you cut it along breadth. Okay. Because the width is same. But when it comes to the magnetic dipole moment of this magnet, so we say it is nothing but simply, we can say it is nothing but, sir, this is M into pole strength multiplied by distance between them. This will also have pole strength M. Okay. So we say M into L by 2. This also has magnetic dipole moment. M is equal to M is the pole strength and then it will be L by 2. Okay. And most importantly, guys, let me just tell you one more thing. We say magnetic monopoles do not exist. Magnetic monopoles do not exist. Even if you cut this in two pieces, you'll say, sir, if you cut this in two pieces, let's suppose this is plus M, this is minus M from this side. Say, sir, this is minus M from this side. Okay. And this is plus M. Sir, if you cut this in two pieces, now plus M will be over here and minus M will be over there. No, magnetic monopoles cannot exist, do not exist. So we say even if you cut it in two pieces, this one and this one, you say, sir, this will be having plus M from this side and it will make minus M from this side automatically over here. Okay, so we say this becomes one magnet separately, and if we say, sir, this is over here minus M, then it will create plus M from this side, and separately these becomes the two magnets. Because magnetic monopoles do not exist. Is that clear, my dear friends? Is this clear, my dear friends, still over here? Okay. Let's take a break. Okay. Break till 9:25. Sorry, 11:25. Okay, guys. Break till 11:25. Okay, guys. Back to basics. So, let's move on to this particular question we have over here. See, in this case, a bar magnet of length L, we are given a bar magnet, okay? This is the bar magnet and it has length L and a magnetic dipole moment M. It has got the magnetic dipole moment M, okay? So we say this M is equal to M into L, small m. What is small m? Small m is basically the pole strength, okay? Small m is the pole strength. Strength of the south pole and strength of the north pole over here. We say it is M into L. So we say a bar magnet of length L have magnetic dipole moment capital M is bent in the form of an arc, is bent in the form of an arc. We have bent this in the form of an arc, okay? So this bar magnet, we have bent it something like this. In the form of an arc, we have bent it something like this, okay? So length of this remains same, that is L only. And let me just tell you, it is making the angle of, we say 60 degrees over here. We say 60 degrees over here. This angle is nothing but, we say 60 degrees. It is nothing but 60 degrees, okay? So the new magnetic dipole moment of this arc will be, we have to find M dash in this case. See, initially when it was like a straight rod. In that case, magnetic moment is M into L. When we bent it in this shape, its magnetic moment is what we are supposed to find out. And this distance is given as R. This is given as R over here. Okay, this is given as R. Now listen to me very carefully. If I take a straight line from this point to this point over here, listen to me very carefully. And if I join this from this point to this point, now see over here, the first and the foremost thing is we are supposed to calculate this magnetic moment of this bent rod over here, bent bar magnet. If I say, sir, this is R and this is 30 degrees and this is also 30 degrees. Sir, this is R. Sir, which component of this, what will be? This will be, see, this line is the component of, which component is this? We say, sir, if this is R, this is 30. We say, sir, this is R cos of 30 degrees. And this is the cos component. This one will be the sine component, that is R sine of 30 in this case. Similarly, if this is R, this will be its cos component, okay? And we say, sir, this will be its sine component. This is also R sine of 30, okay? And if I have to mention the poles over here, sir, this will be minus M and this will be plus M in this case. Like over here, this is minus M and this is plus M. In this case, this is minus M and this is plus M. If I ask you to tell me the pole strength over magnetic dipole moment over here, you say, sir, just a second, guys. I don't know what has happened to this.
हेलो मैं गई स्ट्रीम स्टक अत क्या गो वीडियो फ्रीज ना कहीं ना मैं कोर स्टूडेंट ना करान और ये टेक्स्ट वल्ला वो क्या एक ना OBS मज ते फ्रीज ना कैमरा ते गो फ्रीज कैमरा तो ना तुलनी कैमरा तो तुलनी क्या वनो ना वायर ना गस कहाँ लूज है ना ये क्या दलील वो नेट पर 80% ना तेम कम ही थोड़ा हाँ हाँ ठीक ठीक एक बाव या तो कहाँ छा वनकन जिंदा आसे वल अदा यह कैमरा स्टक ऐसा पाई मैं करा ना अत चेंज अत मैं करा अत मैं त्रा ना नॉर्मल कैमरा अमुक लैपटॉप करा मैं स्विच OBS मज सह चल मगर यह गोमुत कैमरा स्टक कद कर ऑन ऑफ वशा पाई अमुक प्लग कुछ सेकंड Luta, lagu massage. Oh, chalewa. Okay. Guys, is it clear now? Is it clear now? Is it clear now? Yes. Yes. Back to basics, okay? Now see, my dear people over here, listen to me very carefully. Listen to me very carefully. See. So we say this magnetic moment, when we bend this, the new magnetic moment will be simply, sir, pole strength is M only, okay? And in this case, we say distance between the two poles is L. And over here, what is the distance between the two poles? You say, sir, that is R sine theta plus R sine theta. That is simply 2R sine of, we say, how much? That is 30 degrees. Okay, 2R sine 30. This will be the pole strength. Sir, magnetic moment of this dipole is how much? Sir, pole strength is M multiplied by distance between them. Okay, that is R sine 30, R sine 30. That is 2R sine 30. This is the distance between this plus M and minus M over here. And I can write that over here. That will be nothing but, just a second. That will be nothing but, see, that will be nothing but, we say, in this particular case, that is M into 2R sine 30. We say, sir, M dash is equal to M into 2R sine of 30 is 1 divided by 2. 2 and 2 will get cancelled. M dash is equal to M into R over here. Now the question is, sir, we don't know the value of this R. How to find the value of this R? See. This angle over here is given as 60 degrees. 60 degree means pi by 3. 60 degree means pi by 3. Let's take a look. What is the length of this arc, length of this dipole, that is L? What is this radius, that is R? How much is this angle, that is pi by 3? It is something like this. This is L, and this angle is over here pi by 3, and this is R. Can we say, sir, over here angle is equal to arc upon radius? Sir, we have studied this. Okay, so we have studied this. Angle is equal to arc upon radius over here. So we say angle is how much? Sir, that is pi divided by 3. Sir, arc is how much? Arc is, sir, L divided by radius is how much? Sir, radius is R in this case. And now, can we do one thing? Take this R over here. Take this 3 over here. So R will be, sir, 3L divided by pi. As simple as that. Take this R over here. This is 3L divided by pi. Now, what we can do is put the value of this R over here in equation first. So we say put R in equation number first. So we will get the value of this M dash is equal to M. Instead of R, we can write 3L divided by pi. 3L divided by pi. Okay. So it will be, sir, M into L 3 by pi. What is the value of M into L? Sir, M into L was the dipole moment initially when it was a straight dipole. So we say, sir, this M dash is equal to, instead of M into L, we write, sir, M 3 divided by pi, or 3M divided by pi will be the new dipole moment, and that is option B over here. Is this clear?
Is this clear, guys? Is this clear to each and everyone? Let me know in the live chat. Video is not clear. Why is not the video clear? I can see everything is clear. Everything is clear. Increase the video quality. Everything is clear, guys. Now let's move on to the next. Let's move on to the next one. That is magnetic field due to a magnetic dipole on its axis. Listen to me very carefully. Let's suppose this is minus q charge over here, and this is minus q charge over here, and this is plus q charge over here. Listen to me, let me show you over here. Let's suppose we have minus q charge over here and we have plus q charge over here. Okay, this is the distance between them. Now, sir, this is what we call the electric dipole that we have studied. Now, we say, sir, because of this electric dipole, sir, it will create electric field. Sir, at this distance, let's suppose at this distance, x distance, this is the point which is called the perpendicular bisector. This is the point which is what we call the perpendicular bisector, and electric field at this point is k p divided by x cube, where p is the dipole moment of this dipole. Okay, that is from negative charge to positive charge. Why I am showing you this over here? Because I have to relate it in the magnetism also. And because of this electric dipole we have studied at this distance, x distance, okay, x is from the center, sorry. So we say at this x distance from the center, we say, sir, magnetic field at this point will be, electric field at this point will be 2kp divided by x cube, okay. This was the axial point, and this was the perpendicular bisector point. Now, sir, electric field because of this dipole at general point, which is making an angle theta, and this is x distance. Sir, we say electric field here was, that is kp divided by x cube under root of 3 cos square theta plus 1. 3 cos square theta plus 1. Sir, when it comes to an electric dipole, we say, sir, because of the electric dipole at this perpendicular bisector, electric field is kp by x cube. Sir, because of this dipole on the axis, electric field is 2kp by x cube, where p is the dipole moment, k is the constant. And, sir, when it comes to the general point, sir, at general point, electric field because of this dipole is kp by x cube under root of 3 cos square theta plus 1. Now let's come on to the magnetic dipole. That's our topic. Sir, when it comes to the magnetic dipole, listen to me very carefully. Sir, this will be minus m. Over here we have minus q. Over here we have minus m. And this is south pole. And we have over here plus m. Distance between them is, we say, sir, let's suppose d, whatever it may be. And we say, sir, when we have a magnetic dipole, it creates the magnetic field. Like electric dipole creates electric field, magnetic dipole creates magnetic field. First and the foremost thing, we'll find the magnetic field because of the magnetic dipole at x distance at this point, like this, perpendicular bisector. Listen to me very carefully. We say, sir, magnetic field will be at this point. See, over here electric field is kp by x cube. Magnetic field will be exactly similar. Listen to me. Sir, over here in electrostatics we have k. K is equal to 1 by 4 pi epsilon naught. But in magnetism we have constant, that is mu naught divided by 4 pi. Over here we write 1 by 4 pi epsilon naught. Over here we write mu naught by 4 pi. And then we say it has the dipole moment, magnetic dipole moment from minus m to plus m. Over here it has electric dipole moment from minus q to plus q. So this will be, sir, m, okay, m. Like you have p, you have m, divided by, sir, how much is this distance? This is x cube. That is mu naught by 4 pi m by x cube. Mu naught by 4 pi m by x cube. Mu naught by 4 pi m by x cube. Similarly, sir, if we take this axial point, this is the perpendicular bisector. Sir, if we find the magnetic field at the axial point, we say, sir, magnetic field at axial point will be, it will be 2 times of, over here you have 2, over here you have 2. You have k, instead of k, we write over here mu naught by 4 pi, okay? Then you have p. P is the dipole moment, over here you have m. M is the dipole moment, okay? And then you have divided by x cube, and you have this x cube, where x is this distance from the center of the dipole till over here. So this is the magnetic field on the axis of the dipole. This is the magnetic field on the perpendicular bisector of the dipole. And then you have the general point. This is what we call the general point. General point means it is not the axial point. It is not the perpendicular bisector. Let's suppose it is making an angle theta over here. Okay, it's making an angle theta. And we say, sir, magnetic field will be, sir, at general point, how much it is? We say, sir, over here, electric field is kp by x cube. So we write mu naught by 4 pi. Okay. Then you have m divided by x cube under root of same, that is 3 cos square of theta plus 1. I hope this is crystal and clear to each and everyone. Sir, we have a magnetic dipole. Magnetic dipole means bar magnet. Bar magnet creates magnetic field around it. First is, we are supposed to find magnetic field at this point, perpendicular bisector at x distance. So that is equal to mu naught by 4 pi m by x cube. Second is, we have to find the magnetic field at the axis, that is 2 times of mu naught by 4 pi m by x cube. Then you have to find magnetic field at general point. So that is how much? We say mu naught by 4 pi m by x cube under root of 3 cos square theta plus 1. This is what we call general point. This is what we call the general point. Is this clear to each and everyone, guys? Let me know in the live chat. Give me the signal. All of you. Everyone over here, give me the signal. Great. Now we have torque on a magnetic dipole placed in an external magnetic field. Here also we'll understand, we'll learn it, we'll relate it with the electrostatics. Let's suppose I have the electric field over here. Listen to me very carefully. I have basically taught you this before. That's why I am again mentioning it over here, because it will give you the exact field. Now, in this electric field, I am placing a dipole. Which dipole? Electric dipole, minus charge and positive charge. We know, sir, on this positive charge, sir, force will act in the forward direction. On this, force will act in the forward direction. On this, force will act in the backward direction. Sir, these two forces will rotate the dipole. So we say, sir, torque is being produced over here. And the dipole moment is, sir, P, and electric field is, sir, E. Angle between these two is theta. This is electric field in the forward direction, and dipole moment is from negative charge to positive charge. So we say, sir, torque over here is P cross E. The value of torque is P cross E, or the value of torque is P E sine of theta, where P is the dipole moment, E is the electric field, theta is the angle between P and E. Now, listen to me very carefully. Similarly, if we have over here magnetic dipole B, and we have placed a bar magnet inside this magnetic dipole, okay? Or we say we have placed a magnetic dipole. Magnetic dipole is minus M and magnetic dipole is plus M over here, okay? Now, whenever we place a magnetic dipole inside the inside the magnetic field, on this plus M force acts in the forward direction, on this minus M force acts in the backward direction, magnetic force. Remember it exactly. So these two forces will try to rotate the dipole. They will rotate the dipole. So when they will rotate the dipole, we say torque is produced. Sir, torque is produced whenever there is rotation, there is torque. Whenever there is rotation, there is torque. We say, sir, over here, torque is produced because of rotation. Torque is produced because of rotation. And that torque will be in this case. Listen to me very carefully. Over here, torque is P cross E. Torque is P cross E. P is the dipole moment, E is the electric field. Same here will be, sir, M cross B. M cross B. Sir, what is M? M is the dipole moment. That is from negative minus M to plus M. And sir, B is the magnetic field. B is the magnetic field. Angle between magnetic field and M is theta. So we can further write this as tau is equal to, we say MB sine of theta. M cross B is MB sine theta, where theta is the angle between M and B, where theta is the angle between M and B. So we say torque on a magnetic dipole placed in external magnetic field, tau is equal to, we say, MB sine of theta. This is the torque on a magnetic dipole whenever you place it in the magnetic field. If you place a magnetic dipole inside a magnetic field, sir, it will rotate. So torque is produced. So that torque is MB sine theta. Let's suppose if I say you have this magnetic field in the forward direction, something like this, and you have placed the dipole something like this. This is the magnetic dipole, bar magnet. This is minus M and this is plus M in this case. So dipole moment is from minus M to plus M. This is M. And magnetic field is in the forward direction. Angle between these two in this case is, over here, theta is 90 degrees. Clearly we can say magnetic field forward, dipole moment is from minus M to plus M. Theta is equal to 90 degrees. Now in this case, we have to find the torque. Torque is equal to MB, we say sine of theta. Theta over here is 90. Sine 90 is 1. In this case, torque will be MB. Torque will be MB. Okay. And this is what we call the maximum torque. This is what we call the maximum torque. And if I say, sir, let's suppose this is the magnetic field. And inside this magnetic field, you are placing a dipole. And dipole is something like this. This is M and this is, sir, minus M and this is plus M. And dipole moment is from, we say, minus M to plus M. Over here, angle between M and B, we say that theta is equal to 0 degrees because both are in the same direction. In this case, sir, torque will be MB, we say sine of theta. Theta is 0 degrees, sine 0 is 0. So we say torque in this case is 0. It is obvious this dipole will not rotate in this one, but this dipole will rotate. That's why torque is produced. That's why torque is produced. It is like, sir, on this force will be in the forward direction, on this force will be in the backward direction. These two forces are pulling the dipole. So they will not rotate the dipole at all. Is this clear, guys, till over here? Is everything clear till over here? Let me know in the live chat, everybody of you. Is it crystalline clear to every one of you in the live chat, guys? I need to know in the live chat, guys. Is this crystal clear? I'm waiting for your response, every one of you in the live chat. Everyone means everyone. If this is crystalline clear, let me know in the live chat. Then comes basically the next topic. That's what we call the potential energy of a magnetic dipole. Potential energy of a magnetic dipole. It will take 1 or 1.5 hours now. And we are done with this. Potential energy of a magnetic dipole. Listen to me very carefully. Let's suppose we have a magnetic field over here B. Okay, we have a magnetic field over here B. And inside this magnetic field, we have placed this dipole that is minus M, and this is basically plus M. Cool? Yes, sir. Now listen to me very carefully. I say, sir, you have to rotate this dipole from this angle to this angle. So you have to rotate this dipole from this angle to this angle. Okay. You have to rotate this dipole by an angle of, we say, theta. Something like this. Now, I say, I have told you this before also. If I have to rotate this dipole, do I have to do some sort of work? Yes, sir. I have to do the work done and rotate this dipole. Now we say, sir, my work done in rotating the dipole, will be stored as potential energy of the dipole. Will be stored as potential energy of the dipole. Or I say, my work done means external work done, will change the potential energy of the dipole. Let's suppose I say I have a block over here, okay, and on the surface its potential energy is 0. If I raise it to some height, let's call that height h, and if I place it over here, how much potential energy it will have? Sir, U is equal to mgh over here. Initially on the surface it was having potential energy 0. At the surface h, at the height h, its potential energy is mgh. So I lifted the block from the surface till height h, then only potential energy got stored as mgh. So I say, sir, my work done changed the potential energy of this block. At this point, its potential energy was 0. When I lifted it from the surface till the height h, its potential energy increased from 0 to mgh. So that's what we say. By doing the external work done, its potential energy changed. Same is the case over here. If I have a dipole, if I rotate this dipole by theta, so by doing the external work done, the potential energy of the dipole will change. Sir, that's what I will write over here. Potential energy of the dipole, or that is work done by external agent, will change the potential energy of the dipole. Work done by external agent will change the potential energy of the dipole. That's what we say. W external is equal to delta U. W external is equal to delta U. Is this clear? Now, if my work done in rotating the dipole will be stored as its potential energy. So if I do the work done in rotating the dipole, we say potential energy will be stored in the dipole. How much that potential energy will be? listen to me very carefully. We say that potential energy will be, we say, sir, U is equal to, sir, minus M dot B. U is equal to minus M dot B. Or we say U is equal to minus M dot B is MB cos of theta. MB cos of theta, where theta is the angle between M and B, Let me just tell you a simple thing over here, which I have taught you in electrostatics. Sir, I have this electric field over here, okay? I have this electric field over here. And inside this electric field, you have a dipole. Sir, you place this dipole inside this electric field. And if you rotate this dipole, it is something like this. If you have this negative charge, this positive charge. Now, if you rotate this dipole over here, sir, potential energy will be stored in this electric dipole. And that potential energy is U is equal to minus PE cos of theta. PE cos of theta, where P is the dipole moment, E is the electric field, theta is the angle between P and E. Same is the case over here in magnetism. If you have a magnetic field, you place a magnetic dipole in that magnetic field. Now, potential energy over here will be minus MB cos theta. M is the dipole moment, B is the magnetic field, theta is the angle between M and B. Okay? Theta is the angle between M and B. So I say over here, U is equal to minus MB cos of theta. In case of electrostatics, we have minus PE cos theta. I say where M is the magnetic dipole moment, and B, we say, is the magnetic field. I'm going a bit fast, guys, over here. The reason is we have studied this before already in electrostatics. Okay? So we say, sir, if you place a dipole in magnetic field and if you rotate it by doing external work done, so means you are changing its potential energy. So external work done is equal to change in potential energy, or you are storing its potential energy. How much that potential energy will be? M dot B or minus MB cos of theta. And if I just recall these, if I just say over here, if you have a magnetic field, if you place a bar magnet inside this magnetic field, sir, it will rotate. Sir, if there is rotation, there is torque. Torque will be produced. How much that torque will be? Sir, MB sine of theta. MB sine of theta. As simple as that. Guys, is it clear till over here? Let me know in the live chat if this is clear till over here. Is this clear, guys? All the people out there, let me know, guys. Great. You have this question. Can you solve it? This was asked in NEET 2016. See, a bar magnet. Okay. The energy required to rotate it by 60 degree is W. Now see. We have a magnetic field over here. Okay. This is the magnetic field. And inside this magnetic field, we have a bar magnet. This is minus M and this is plus M, or bar magnet or magnetic dipole, whatever you call it. This is minus M and this is plus M. Now, you are rotating this by an angle of 60 degree. You are rotating this by an angle of, we say, 60 degree. Okay. My question to you is, how much energy will be used in rotating it by 60 degree? That is given over there, that is W. The energy in rotating it by 60 degree is given as a W. If we have dipole, if we are rotating it by 60 degree, means we have to use our energy. We have to do work done. How much that energy is, that is W. Now the torque required to keep the magnet in this position is, if we keep this magnet in this position only, we have to find the value of torque, how much torque we should apply. See, sir, just simply we say work done is equal to change in potential energy in this case. Sir, when it comes to the work done, first of all, sir, we say this is U final minus U initial. We say, sir, this work done is equal to, listen to me very carefully, U final is the final potential energy. Sir, when theta is 60 degree, that is minus MB cos of 60 degree. Because potential energy is minus MB cos theta. Then we have this minus, and then you have this minus MB, we say cos of 0 degree. Okay. And this we can write over here, minus MB cos 60 is 1 by 2 minus MB divided by 2 minus, and this would be plus, minus into minus plus, cos 0 is 1. So this is plus MB over here. This is W. So further we can write over here, this W is equal to, we say, MB divided by 2. Because we say, sir, minus MB by 2 plus MB. So it will be MB by 2. Listen to me very carefully. I know you got confused over here. Sir, we have a magnetic field. Inside this, we have a bar magnet. Now, if we rotate this bar magnet by 60 degree, how much energy we have to use? It is given as W. And what is the value of W? Value of W is MB by 2. So we say this is the energy used in rotating the dipole by 60 degree. Okay, fine. Now if I ask you, the questioner says that if you have to keep this dipole here only, okay, how much torque you need to apply? See, if you keep the dipole here, sir, this magnetic field will rotate it something like this, okay? It will rotate it something like this. It will create the torque. Now, if we want to keep this magnet in the same position, what do we have to do? We have to apply the torque in the opposite direction. And that torque should be equal to this torque. Then only it will remain over here only. Again, I am saying, I want you guys to keep this dipole in this position only when it reached at 60 degree angle. Sir, this magnetic field will now try to rotate it, because I have told you, whenever we place a dipole in a magnetic field, it rotates. So it will try to rotate it. But we don't want it to get rotated. We have to keep this dipole in this position only. So we'll apply the torque in opposite direction. Okay. That torque should be equal to this torque. Then only it will remain in that position. Let's find that torque. Now, torque will be MB sine of theta. What is the value of theta over here? Sir, theta is 60 degree. We have kept it at 60. So we say this torque is MB sine of 60. Sine 60 is root 3 by 2. Root 3 by 2. Now in this particular case, sir, this torque will be, sir, MB divided by 2. MB divided by 2 is W. Then you have W root 3. So means, so we have to apply W root 3 torque. We have to apply W root 3 torque to keep this dipole in the new position, Guys, is this question clear to every one of you? Is this question clear to every one of you? Let me know in the live chat. Is this question clear to every one of you? So root 3W is the answer in this particular case. That is option 4. Okay, great. Current carrying loop as a magnetic dipole. Now see, let's suppose we have a loop over here. Let's suppose we have a loop over here. And in this loop, current is flowing. Okay. Let's suppose current I is flowing in this loop. So whenever the current flows in a loop, it creates magnetic field. So we say, sir, it is creating magnetic field over here. So it behaves like a magnetic dipole. We say this loop creates magnetic field. How, sir? Because current is flowing in this loop. If current is flowing in this loop, we say, sir, it will behave as a magnetic dipole. It is like we have placed a magnetic dipole over here. So it behaves like a magnetic dipole. Or we say slash bar magnet. Sir, why are you saying this? Because if we have a wire, closed loop, in that wire current is flowing. We say, sir, this wire will create magnetic field. Okay, how to find the direction? Curl your fingers, thumb will give you the direction of magnetic field. So if this is creating magnetic field, we say it behaves like a magnetic dipole, because magnetic dipole also creates magnetic field. Or we say it behaves like a bar magnet, because bar magnet also creates magnetic field. Now the question is, if this behaves like a magnetic dipole, we know, sir, magnetic dipole has a magnetic dipole moment. So this will also have magnetic dipole moment. So we say, so it also has magnetic dipole moment. It also has magnetic dipole moment. And that magnetic dipole moment is equal to, M is equal to, we say I is the current flowing in this one, I into, we say A, I into A, where A is the area, I is the current, and A is the area, where A is the area of loop, okay? A is the area of loop. Now if I say this is not only one loop, there are so many loops over here. There are n number of loops. So we say for n turns, in the loop, or for n number of loops, the magnetic dipole moment will be NIA. For one loop it is IA, for n number of loops it will be NIA. Orbital magnetic moment, guys, just a second, okay? I'll go to the washroom. I'll come in 1 minute, okay? Okay, now guys, let me just show you over here in this particular case. That is nothing but orbital magnetic moment for an electron. Let's suppose we have an atom over here, okay? This is the nucleus, okay? And inside the nucleus we have positive charge. And we say, sir, over here, an electron is revolving around this nucleus, something like this. This is the electron, okay? Now, we know, sir, when this electron is revolving in this orbit, we say here electron is revolving in an orbit. Electron is revolving in an orbit. Now, when electron is revolving, means charge is revolving, means charge is moving. So we say current is produced. So we say current is produced. We say current is produced. Now, if current is produced in this case, we say, sir, this now behaves like a current carrying loop. And we just studied current carrying loop behaves like a magnetic dipole. Current is produced. So it reduces, we say magnetic field. So we can say it behaves like a magnetic dipole. Magnetic dipole. Yes, sir. Magnetic dipole. So we say if an electron is revolving, means charge is revolving, means charge is moving. If charge is moving, we say, sir, current is being produced. If current is being produced, it will create magnetic field. If it creates magnetic field, we say, sir, that magnet, if it creates magnetic field, it behaves like a magnetic dipole. Now, if we write over here, that dipole moment, sir, we say this dipole moment is equal to M is equal to, we say it is simply I multiplied by A. Okay. Let's suppose this has radius R. I multiplied by A. Sir, what is A? A is the area, I is the current. Now listen to me very carefully in this case. Sir, I can write this M is equal to current. I can write as, sir, Q is the charge, that is Q, because, sir, I is equal to Q by T. Charge upon time. And charge in this case is electron. So we say E divided by T. Yes, sir. So I can write over here, this is E divided by T into, we say, sir, A. E divided by T multiplied by A. Now what is this? Listen to me very carefully. Sir, when an electron is revolving around this in an orbit, can you tell me what is the value of time? Sir, we know velocity is equal to distance upon time. And this time is equal to distance upon velocity. When it comes to the distance, sir, this is a complete circle. For this circle, its distance is 2 pi and r, that is circumference, divided by velocity is v. Okay, divided by velocity is v. Now put it over here, sir, this M is equal to E upon, instead of this time we can put 2 pi r divided by v. And then you have area of this loop is pi r square. We can write pi into r square. Instead of current, I write E by T. Okay, instead of time, I write 2 pi r by v. Instead of area, I am writing pi r square. This square and r, this pi and this, take this in the numerator. So we can write this M will be simply, sir, this is E, and this will go in the numerator. This is v, and then you have r, then you have divided by 2. So we say M is equal to EVR divided by 2. This is the orbital orbital magnetic moment of an electron. See, this E is the charge on an electron, V is the velocity. Sir, R is the radius. R is the radius of that circle. Okay. And this is the magnetic moment over here. One more thing I just want to tell you in this case, sir, if we have, let's suppose this is an electron which is revolving over here. Okay. It has mass M. This is an electron. It has mass M. And this is the radius R in this case. It is moving with the velocity V. Can you tell me the angular momentum, sir? Angular momentum of an electron. Angular momentum of an electron. Angular momentum of an electron in moving in circle. We say moving in circle. Angular momentum of an electron moving in circle. Sir, we say this angular momentum is mvr. If somebody asks you, if a particle is moving in circle, its angular momentum is how much? You say, sir, mvr. As simple as that. Now, sir, its magnetic moment is how much? EVR by 2. Its angular momentum is how much? MVR. So we say, sir, this is the equation first. This is the equation second. We say divide first by second. Listen to me very, very, very carefully. So we say that will be M divided by L. This first equation divided by second equation. It will be simply, sir, EVR divided by, then we have 2 and then L. What is the value of L? That is MV and this R. Sir, VR will cancel. So this M by L will come out to be E by 2M. E by 2M. This is called gyromagnetic ratio. This is what we call the gyromagnetic ratio. M by L, where M is the magnetic moment of an electron, L is the angular momentum, and their ratio is what we call the gyromagnetic ratio. Everybody, guys, let me know in the live chat if this is clear to each and everyone. We have an electron, it is revolving, it is producing current, so it behaves like a magnetic dipole. Its dipole moment is EVR by 2. Okay, and for the same electron, if it is moving in circle, its angular momentum is MVR. If you divide magnetic moment with angular momentum, it comes out to be E by 2M. This is what we call the gyromagnetic ratio. Is this clear, guys, or I am confusing you? I think I am going fast right now. I think I am confusing you because this vibe is coming from I'm actually getting this vibe. I'm actually getting this vibe. Is it true? Okay. Great. Now, moving coil galvanometer. Everything is there. Now see, let me just tell you, Sir, it is a device which is used to detect the current and also measures small currents. Measures currents. Okay, also measures current. Moving coil galvanometer. It is that device which measures the current. Okay, I have told you this in current electricity also. It is that device which measures the current. Listen to me very carefully. I'll tell you something over here. I'll make a galvanometer. Okay, before that, let me just tell you. We have a magnet over here. Okay, a magnet has got a north pole and a south pole. This is north pole and this is south pole. Like I told you, I have a bar magnet. Okay, this bar magnet has got south pole, it has got north pole. This south pole has got pole strength. This north pole has got pole strength. Same is the case over here. I am basically taking the north pole from this side. I am taking, maybe this is one magnet, this is another magnet. So this is the south pole and this is the north pole. And listen to me very carefully, my dear friends. One thing I just want to tell you. Remember that, sir, magnetic field lines are always from north pole to south pole. If I say it something like this, outside of the magnet, I'll tell you this. We have to study this after some time. But as of now, magnetic field will be from north to south over here. Sir, why are you placing these two magnets? Because we have to create the magnetic field over here. Sir, north pole, south pole, and inside this magnetic field, we have placed this coil. Okay, this is a square shaped coil inside this magnetic field. Now listen to me very carefully. Sir, we know as the coil, this coil is placed in a magnetic field. Sir, we have north pole, we have south pole. These two north pole and south pole are basically creating the magnetic field. And in that magnetic field, we have placed a coil, this square shaped coil. Okay, yes, sir. And in the square shaped coil, current is flowing. Now listen to me very carefully. As the coil is placed in the magnetic field, this coil carries current I. It carries current I. So it behaves like a dipole, like a magnetic dipole. So can we say, sir, if this coil behaves like a dipole, we have placed a dipole inside the magnetic field? Yes, 110% we can say. So we have placed a magnetic dipole. We have placed a magnetic dipole in a magnetic field. We have placed a magnetic dipole in a magnetic field. Yes, sir. Now, you have told us, sir, concept. What concept you have told us? That is nothing but if we place a magnetic dipole inside a magnetic field, sir, torque is being produced. It will rotate, sir. So same will be the case over here. So we say over here. So torque is produced. And it will rotate. Yes, sir, 110%. Now, if I ask you, what is the value of that torque? You say, sir, the value of that torque will be tau is equal to, we say, sir, MB sine theta. Now listen to me very carefully. Sir, this is north pole, south pole. We have created the magnetic field from north to south. Inside that magnetic field, we have placed a coil in which I current is flowing. and this coil is nothing but a magnetic dipole. So we have placed a magnetic dipole and magnetic field. So torque will be produced, that is mb sine theta. Now, can you tell me the magnetic moment of this coil? Sir, if in a coil current I is flowing, how much is the magnetic field in that coil? Sir, magnetic field will be I into A. Magnetic field is I into A. You just studied, you just told us recently, okay? Now, for N turns, we say, sir, magnetic field is, we say NIA, okay? Magnetic moment is NIA. Now, you guys tell me one thing. Sir, instead of this M means magnetic moment. Can we put NIA? So, torque will be, sir, this N, I, A, and we have B, and sine of theta, and sine theta in this case will be sine of 90 degrees. Sir, theta is the angle between magnetic moment and magnetic field. Theta is the angle between M and B. See, this is the magnetic field. And what is the direction of magnetic moment? Direction of magnetic moment will be something like this, or it will be perpendicular. Something, curl your fingers. This is the direction of magnetic field or magnetic moment. Magnetic moment and dipole, they are perpendicular. See, they are perpendicular. So sine is 90 over here, theta is 90. So finally, what I'm trying to say is that torque will be, we say, sir, NIAB. NIAB. Listen to me very carefully. Clearly, we see over here, sir, torque is proportional to current. If current in the coil is more, we say, sir, torque is more. And if torque is more, we say coil will rotate more. Rotate more. Guys, I am telling you each and every single step over here, because a lot of people also feel this moving coil galvanometer is tough. I'll give you the exact feel. Now see. Sir, as of now, we studied if we place a coil in a magnetic field, torque will be produced in it. That torque is equal to NIAB sine of theta. That torque, N is the number of turns in the coil, I is the current in the coil, A is the area of coil, B is the magnetic field over here. Now. Come over here. This is the diagram of moving coil galvanometer. Just this I need to make over here. This is the diagram of moving coil galvanometer. Listen to me very carefully. See, we have a north pole, we have a south pole. And inside this, we have placed a coil. Okay. We have a north pole, we have a south pole. Inside this, we have placed a coil. Okay. And there is, we say, this is what we call the helical spring. Okay. And then we connect a jockey to this. And this jockey is basically connected to this coil over here. And this is the meter. This shows us the reading. Now you guys tell me one thing. Sir, you said tau is equal to NIAB. Sir, if current is more, torque is more. Now see, sir, this moving coil galvanometer measures the current. If we send, let's suppose, more current through the coil, sir, on sending more current through the coil, torque will be more. Sir, rotation will be more. So if rotation in the coil is more, you have connected this jockey. So this jockey will rotate more. Let's suppose you are sending small current over here. Listen to me very carefully. Sir, at small current, sir, less torque is produced. So we say, sir, jockey will rotate less. So it will show less reading. Let's suppose 10 ampere over here. Okay. Yeah, 0.5 ampere, 0.7 ampere. Now, if you increase the current, sir, over here, Sir, torque will be increased. Sir, this jockey will now rotate more because coil will rotate more, so jockey will rotate more. It will show more reading. This is the working of moving coil galvanometer. This is how actually moving coil galvanometer works. Okay, so we say if current is more, I have written it over, I have mentioned, if current is more, torque is more, coil will rotate more. So jockey will rotate more and shows more reading. Okay, this is how galvanometer actually works. Now listen to me very carefully, my dear friends. See, if I say over here, guys, tell me one thing. If you have this jockey, okay, if you have this jockey over here, if you are sending some current through the coil, you want to measure that current. What will happen, sir? This will rotate and it will be placed something over here. Let's suppose it shows us some current, let's suppose 0.5 ampere. Now you guys tell me one thing. Will this jockey, if we basically remove the current in the coil, what should happen in this case? Sir, this jockey should come back to this original position. Like you are sitting inside the car, okay? You are driving the car. It is like that only. As you keep on increasing the speed, that jockey on the speedometer will keep on increasing. It will keep on showing you the more reading. Once you lift your foot from the accelerator, it comes back. Yes or no? It comes back to the original position. Same should be case over here. Now, if you remove the current, this should come back to the initial position 0. Oh, yes or no? In the chats. Yes or no in the chats? Now we say when current is removed, the jockey should come back to original position. Okay. Now for that, in this moving coil galvanometer, we have used this helical spring. This helical spring will basically bring the jockey back to the original position by creating the restoring torque. So I'll just write over here. So we use helical spring, which creates restoring torque, and that restoring torque is equal to, my dear friends, C into theta, where C is the, we say, spring constant, where C is the spring constant. Okay, spring constant. And theta is the angular displacement. So we say over here, first equation is this one. Because of this torque, listen to me, sir, because of this torque, NIAB, this jockey got deviated and it showed us the reading. Now we want to bring the jockey back. For that, restoring torque has to be there here. Someone should create the restoring torque. So we say helical spring is creating the restoring torque, which brings it back. Now we say, sir, when this restoring torque is equal to this torque, let's suppose forward, this torque brings it forward, something like this. Restoring torque brings it back. So we say when they are equal, then only it will bring it, it would be able to bring it back. So we say here we say NIAB AB should be equal to C theta, then only jockey comes back. Guys, is this clear till over here? We are done with the galvanometer. This equation, the above equation is called the equation of moving coil galvanometer. This is called the equation of moving coil galvanometer. Is this clear, guys? How does galvanometer actually work? Is this clear, guys? How does galvanometer actually work? Because of this torque, we are able to measure the current. Now we want to bring the jockey back. We use helical spring, which creates the restoring torque. That is called the C theta. That is equal to C theta. Now we define two things over here. That is galvanometer sensitivity. Okay. Or we say, sir, current sensitivity over here. Let me just write current sensitivity. Sir, what does current sensitivity mean? It means how much sensitive galvanometer is. More the sensitive galvanometer is, more small currents it's able to measure. Less the sensitive galvanometer is, it won't be able to measure small currents. We say, sir, how do we find the current sensitivity? See, we say, sir, moving coil galvanometer equation is C theta is equal to NIAB. What I want you guys to do is take this, keep this theta over here only. Now divide it with I. Theta divided by I is equal to, we say, sir, this is this is NAB and divide it with C. This theta by I, it is called, sir, current sensitivity. We say, sir, SI is equal to NAB divided by C, or SI is equal to theta by I. This is what we call the current sensitivity. So we say it is nothing but how sensitive galvanometer is. If I say galvanometer is very sensitive, means if you even send very small currents, it will measure that also. Means it is very sensitive. We say my friend is very sensitive. Even if I touch him something like this, he becomes very aggressive. So that's what we say sensitive. Now see, if C increases, means C means spring constant, stiffness. If I say C is more for a spring, means the spring is very tough, very tight. So if spring is very tight, so it is the sensitivity will be less. So SI is inversely proportional to C. If C increases, SI decreases. Sir, how? Let me just tell you. If I say this spring is very tough, so it would be difficult for jockey to deviate to show the reading. So we have to send very large currents, then only it will be deviated. So small currents, it won't be able to deviate. Why? Because spring is tough. This spring won't let the jockey to deviate. So that's why we say, sir, over here, this current sensitivity is inversely proportional to the C. Guys, is this clear? Every single point I am explaining over here. Is this clear, guys? Let me know. If you are not like the session yet, guys, like the session. Simply galvanometer sensitivity is theta by I, that is NAB divided by C. NAB divided by C. Now see. Now let's talk about the voltage sensitivity. Sir, first and the foremost thing, let me just tell you. Sir, we know Ohm's law, V is equal to I into R. As over here, we know, sir, C theta is equal to NAB. Okay. C theta is equal to NIAB. Okay. NIAB. So we say, sir, if I want to find the current over here, sir, current would be simply that is C theta upon NAB. C theta upon NAB. Now from Ohm's law, V is equal to IR, we can find this voltage. Instead of I can put this C theta upon, we say NAB, and we say over here, sir, this is R. Okay. Now, when it comes to the voltage sensitivity, see, the current sensitivity was theta by I. SI is equal to theta by I. Sir, when it comes to the voltage sensitivity, that is nothing but we say SV. It will be simply theta upon V. If current sensitivity is theta upon I, voltage sensitivity will be theta upon V. So put the value of V over here, sir, theta upon. What is the value of V? That is C theta R divided by NAB, So SV will come out to be theta. Theta will get cancelled, okay? So what we can write? Theta will get cancelled. Take this in the numerator. So this will be NAB divided by CR. Okay? Over here I'll write, sir, SV is equal to NAB divided by C. What is NAV divided by C? NAB divided by C. So we say, sir, NAB divided by C is SI, current sensitivity, upon R is the resistance, where SI is current sensitivity, SV is voltage sensitivity, and R is a resistance of galvanometer. That's it, guys. We are done with the galvanometer. Is everything crystalline clear? Is everything crystalline clear? Is everything crystalline clear? This was the question asked in, we say, NEET 2018. In this case, current sensitivity of a moving coil galvanometer is 5 division per milliampere. Sir, SI is given as 5 division per milliampere. Okay. And its voltage sensitivity of a galvanometer is given as 20 division, we say, per volt. Okay. We are supposed to find the resistance of the galvanometer. Very simple. Now, first of all, this is in milliampere, convert it in ampere. We can write 5 division upon per milliampere. If you convert milliampere into ampere, we say, sir, 10 raised power minus 3 ampere. Now, take this in the numerator. You can write, sir, 10 raised power minus 3 becomes 10 raised power plus 3. So 5 into 10 raised power plus 3 becomes 5,000. This is 5,000 division per ampere. Now, we have to find the resistance of the galvanometer. Sir, SV we know, SI we know, resistance we can find. So we say in this case, SV is equal to SI divided by R. Now, SV is how much? That is 5,000. Sorry. SV is how much? That is 20. Is equal to SI is, we say, sir, 5,000 divided by, we say, R. And we say this R will be, sir, 5,000 divided by 20. And this R will come out to be this, and this is 250 ohms, 250 ohms. Is this clear? Is this clear to each and everyone, guys? All the people, guys, give me the signal. Is this crystalline clear, guys? Every one of you? Yes, yes, yes. Rocky bro will start Earth's magnetism also. See, solenoid, this is a solenoid. Okay, this is a solenoid. So we say, sir, if you send a current in this wire, so it is something like this. There are so many loops and it forms a solenoid. It is not one loop. There are so many loops. This is a coil basically in n number of loops. And when you send a current in this solenoid, okay, it creates magnetic field around it, which is something like this. And the value of that magnetic field is mu naught n into I. As simple as that. Mu naught n into I. Number of turns, and this I is the current flowing in this one. And we say outside the solenoid, we consider magnetic field 0, and we consider it along the axis. That's it. Okay. We have questions that we will be doing in the electromagnetic induction regarding the solenoid and all. Over there, we'll explain it in. Over there, I'll be showing you good number of problems on solenoid also. Now see, magnetic field lines. You guys tell me one thing. Let's suppose we have a charge Q. Okay. We say, sir, this charge creates the electric field around it. And we represent that electric field with the help of electric field lines. Sir, this is a charge. It creates electric field around it. That electric field will be basically, that electric field will be shown with the help of electric field lines. So this is the concept of electric field lines. Now, what is the magnetic field lines? Sir, we represent magnetic field with magnetic field lines. If I say I have a magnet, it is creating the magnetic field. So how do I represent it on pen and paper? How do I show it? You say, sir, these are the lines, magnetic field lines. It is creating magnetic field. So I'm showing this with the help of magnetic field lines. Okay? And these are from north to the south outside of the magnet. Let's suppose I have a magnet over here. Clearly you can see on the screen. Sir, this is the south pole of the bar magnet. This is the north pole. Sir, when we say over here, these field lines are from north to south outside of the bar magnet. See, sir, this is the north. The field line will leave from north and it will enter south. So it is from north to south outside of the magnet. This is inside, this is outside. Similarly, it can go something like this, okay, from south to north. So these field lines, if you have to show this is a magnetic field, how do you represent magnetic field lines? From, we say, south to north in this particular case. Now see, in this case, these are from north to south outside the magnet. These are from north to south outside, and from south to north inside the magnet, and from south to north inside the magnet. So from south to north We say, sir, magnetic field from south to north, it will be, magnetic field lines will be from south to north inside the magnet. Okay. Then we say it forms a closed loop. See, clearly, these field lines clearly form the closed loop. These field lines clearly form the closed loop. Does not intersect with each other. They do not intersect. They do not cross each other. Okay. Remember this. They do not cross each other. They do not cross each other. Okay. No. They do not cross each other. Okay. Now it can come out and go in at any angle. Like if I say, sir, this is bar magnet. Okay. Sir, this is south and this is north. Sir, these field lines can come out at any angle. It's not like, sir, they have to come at this angle only. They have to come out at this angle only. They have to come out at this angle only. No, they can come out at any angle and they can go in at any angle. Okay. Okay. It does not matter at all. That's what is mentioned over here. Okay. Field line density represent the magnetic field strength. If I say there are so many field lines over here, so many field lines over here, means magnetic field is more. Density of these lines represent how greater the magnetic field is, how strong the magnetic field is. So this was the detail about magnetic field lines. Is it clear, guys? Is it clear to each and everyone? Is it clear to each and everyone? Is it clear to each and everyone, guys? Okay, great. Now, let's move on to the Earth's magnetism. See, the first thing that we need to study over here is, that is nothing but we say Earth as its own magnetism. We say Earth has its own magnetism. Sir, what does that mean? What does that mean? I know in order to understand the rest of the topics, I know this is deleted, but in order to understand the rest of the topics that I need to explain on which questions have been asked, it is mandatory for you to study. Without understanding this, it is not, I'll not go in much detail. I'll be to the point only. I'll be to the point. There is a reason why I'm showing you this. Okay. Now see. We say Earth has its own magnetism. What does that mean? Sir, there was a place, that's what we call the Magnesia. Okay, that was an island. Over there, people were working and they used to have the shoes. In that shoes, they used to basically have the nails, iron nails. So while they were walking on the earth over there, their shoes started sticking to the earth. Why? Because they were having the iron nails inside their shoes. Okay. So from there we got to know that Earth has its own magnetism. Inside the earth there is a kind of magnet which attracts. Okay. So we say, sir, Earth has its own magnetism, and we consider there is an imaginary bar magnet inside the earth. If we have this earth, we consider inside this earth there is an imaginary bar magnet. Inside this earth, there is an imaginary bar magnet, which has the south pole, which has this north pole. Now listen to me very carefully. Are you able to see this particular diagram? Is this particular diagram visible? listen to me very carefully over here. Listen to me very carefully over here. See, if we say, sir, this is Earth, and this axis over here, this axis is what we call the rotational axis. This axis is what we call the rotational axis. We know, sir, Earth is rotating. Earth is rotating. So Earth is rotating about an axis. That axis is what we call the rotational axis. Okay? What we call the rotational axis. And there is one more axis. If I take one more line over here, and it should cross exactly through the center of the magnet, through the center of the bar magnet, which we assume inside the Earth, this is what we call the magnetic axis. There are two axes over here. The first one is the rotational axis. It is that axis about which Earth is rotating. Then we have magnetic axis. It is that axis which passes through the center of the magnet exactly. Okay? These are the two things that we have over here. Now, listen to me very carefully. We say, sir, you might have heard north, south, east, west. North pole, south pole, east, west. Sir, what is this north pole? What is the south pole? Listen to me very carefully. Sir, over here, sir, this is what we call the north pole. In real life that we say, okay, in daily life, this is what we call the north pole. And this is what we call the geographic north pole. And from the lower side, we have geographic south pole. From the lower side, we have geographic south pole. Okay, if you take a look at this rotational axis, on top of it, we consider, or on top of the Earth, we consider geographic north pole. And from the bottom of it, we consider geographic south pole. Okay. Now, this is basically the geographic north pole and geographic south pole. Now see, sir, we can clearly see this magnet. From the upper side, we have south. From the lower side, we have north. So we say, sir, from the upper side of the Earth, we have magnetic south pole. And from the lower side of the Earth, we have magnetic north pole. Remember this, my dear friends. What I'm trying to say is that when it comes to geographic north pole, first of all, we have two axes that we define over here. First is rotational axis. Second is magnetic axis. Rotational axis is that axis about which Earth is rotating. And we have geographic north pole from the upper side of the Earth. And we have geographic lower side, geographic south pole from the bottom of at the bottom of the Earth, from the lower side. And when it comes to the south pole, we have magnetic south pole from the upper side, magnetic north pole from the lower side. Guys, is this clear? Is this detail clear till over here? Give me the signal in the live chat. Give me the signal in the live chat. Give me the signal in the live chat. Is this clear or any sort of doubt over here? Is this clear or any sort of doubt over here? Said Zishan Dar Tajamul. Where are you guys from? Okay, Zifan. Okay. Great. Okay. Now see, now comes basically, I told you two axes, rotational axis, geographical axis. Okay. When it comes to the geographic north pole, it is from the upper side. When it comes to geographic south pole, it is from the lower side. When it comes to the magnetic south pole, it is from the upper side. When it comes to the magnetic north pole, it is from the lower side. Now we have over here, that is magnetic meridian. This is bit complicated to understand, but if you keep your mind over here, everything will be sorted. See, what is this magnetic meridian? See, I say at my throat is gone today, completely gone. Now see, we say at any point on the Earth's surface, at any point on the Earth's surface, the plane passing through the magnetic poles, the plane passing through the magnetic poles, and that point is called the magnetic meridian. Sir, what is this? See. Let's suppose you have got this over here. Okay, you have got this over here. This is the magnetic axis that you can see over here. This is the magnetic axis. This is the magnetic axis. Okay, this is the magnetic axis. What I want, what I want you guys to do is, I want you guys to do one thing. Just take a plane. Just take a plane. Cut this earth, or fix this plane inside the earth such that this magnetic axis, magnetic south pole and magnetic north pole should lie on this plane, You are supposed to basically fix this plane in such a way. Plane means which has area, sheet. You are supposed to fix this plane inside the earth such that the magnetic south pole as well as magnetic north pole both should lie on this plane, or this magnetic axis should lie on this plane. Then I can call this as magnetic meridian. Then I can call this plane as magnetic meridian. When you fix it over here, so we say this is nothing but the magnetic meridian. Now, that's what is mentioned over here. At any point on Earth's surface, the plane passing through magnetic poles means magnetic south pole, magnetic north pole. And that point which you are taking as reference, that should also lie on this one. So, is called the magnetic meridian. Simply, like over here, this is the magnetic meridian. Okay? Similarly, simply what I'm trying to say is that you take this and cut it over, fix it in the earth such that magnetic south, magnetic north both should lie on this one, okay, or the magnetic axis should lie on this one, and the reference point, then we can consider this as a magnetic meridian. Is it clear, guys? Magnetic meridian. Is it clear? And if you see, means we say, if you take any point on earth, you are sitting at earth, okay, if you take any point on earth, place yourself, then if you take any point on earth or place, okay, if you take any point on earth or place, then you must include yourself, and magnetic poles axis is called magnet. Same. The meaning of this is same. I have mentioned it twice. Simply, if this is the earth, this is the magnetic, we say, sir, south, and this is the magnetic north over here. Okay. I want you guys to basically do one thing. I want you to make a magnetic meridian. You just fix this plane so that this should lie on this one. This should also lie on this one. Then we can consider this as a magnetic meridian. And then we have a geographic meridian. It means that if you take any point on Earth's surface, then over here, at any point on Earth's surface, the plane passing through the geographic poles, and that point is called a geographic meridian. Sir, show us over here. Show us over here. Just a second, guys.
Okay, let me. Okay. Now see, I want to make the geographic meridian only. Sir, geographic meridian is that plane. Geographic meridian is that plane. So, if I have to make the geographic meridian over here, so we say in that geographic meridian, you have to fix it inside the earth in such a way so that geographic north pole as well as geographic south pole both should lie on this plane. They should come over here. So it is that plane on which geographical north pole and geographical south pole both are present, or geographic axis is present, as simple as that. Okay, at any point on Earth's surface, okay, at any point on Earth's surface, we say it is that plane which should lie, which contains geographic north and geographic south. Magnetic meridian is that plane which contains magnetic south and magnetic north. Guys, is this clear? That's it. Is this clear? Is this clear? Let me know in the live chat if this is clear to each and everyone. And if you take a look over here, let's suppose I'm saying this in over here I have made. Let's suppose I call this as magnetic meridian. Okay. So this magnetic meridian contains what? Magnetic south, magnetic north. And that point, we say, let's suppose this point. What is that point? That's the reference point. Simply magnetic south and magnetic north. That's it. That's it. What I have to show you in this particular case is basically this. Basically this. Now listen to me very carefully. If let's suppose something is getting out of your mind over here, I know it is very complicated for a student to analyze or understand this. So that's why I tried to make it very simple, okay, as much as possible. Now, what I want you guys to do is, whatever I say, just remember it. Do not use your mind, okay? You don't have to use your mind. Just follow me, as simple as that. See, we know, sir, meridian is a plane. Axis is a line. So when I say geographic meridian, it is a plane which contains geographic north, geographic south. When I say magnetic meridian, it contains magnetic south, magnetic north. Now see, let's suppose I am taking a plane over here. That's what we call the magnetic meridian. Okay. And we know, sir, magnetic meridian contains, we say, sir, magnetic field. And we represent this magnetic field with B. Okay. Because magnetic meridian contains magnetic axis, or magnetic north and magnetic south. So we say over here, sir, this magnetic meridian, if this is magnetic meridian, it contains magnetic field. Magnetic axis will be in this line only. Yes, sir. Yes, sir. Now see, if I say, sir, over here, this is magnetic meridian. This is another one is geographic meridian. I have taken both over here. Sir, this is magnetic meridian inside the earth, and this is geographic meridian inside. Suppose this is the earth. You have fixed the magnetic meridian, something like this. You have fixed the geographic meridian, something like this. And angle between these two is what we call phi. So this is the angle, what we call angle of declination. Angle of declination, it is the angle between magnetic meridian and geographic meridian. So angle of declination is nothing but the angle between magnetic meridian and geographic meridian. If you have this earth over here, you are fixing a plane, you have this earth, you are fixing a plane, this is magnetic meridian. You are fixing one more plane, this is geographic meridian. Angle between these two, whatever it may be, that's what we call the angle of declination. That's what we call the angle of declination. Now see, sir, when it comes to the magnetic meridian, it contains magnetic axes. Sir, let's suppose this angle is what we call delta. This angle is what we call delta over here. This angle is what we call delta. Sir, if this is B, can I say this is the horizontal component of B? That's what we call BH. This is what we call the horizontal component of B, that is BH. Sir, this is magnetic field. This is the horizontal component of magnetic field.
And this one is the vertical component of magnetic field. This is what we call BV. Listen to me very carefully. Sir, this is magnetic field which is on magnetic meridian. Its horizontal component is BH, vertical component is BV. Now over here, we say, sir, this BV is the vertical component. And we know, sir, vertical component is the sine component. So this is B sine of theta or B sine of delta. And this is B cos of delta. Cos of delta. B horizontal, B vertical. So B vertical is B sine of delta because this angle is delta. And we say, sir, BH, that is horizontal component, is B, we say, sir, cos of delta. B cos of delta. Now, if I say, sir, divide first by second, we say, sir, BV divided by BH, we can write over here B sine of delta divided by B cos of delta. This and this will cancel. Sine by cos is tan. So we say, sir, tan of delta is nothing but BV divided by BH. BV divided by BH. So we say this tan of delta is vertical component divided by horizontal component BV by BH. Where, let me just tell you, delta is called the angle of true dip. This delta is what we call the angle of true dip. This delta is what we call the angle of true dip. So we say, sir, it is that angle. It is that angle which is made on magnetic meridian. So from now onwards, you remember that any angle which is made on magnetic meridian is what we call the angle of true dip. And over here, sir, this is magnetic meridian. On this magnetic meridian, what angle is made? This angle phi or this angle delta? Obviously delta. So delta is called the angle of true dip. It is that angle which is made on magnetic meridian. Guys in the live chat, fast. I just need to know if this is clear to each and everyone. Everyone, guys. Is this clear, guys? Okay, great. So tan delta is equal to BV by BH, where delta is the angle of true dip. Clear? Yes. Now, we are given a question. At a certain place on Earth, BH is equal to 1 by root 3 BV. Means over here it is given as BH is equal to 1 by root 3 BV. Find angle of dip at this place. We are supposed to find the angle of true dip. That is delta we are supposed to find in this case. So we say, sir, if we just do one thing, that is nothing but, we say, sir, take it over there. We say, sir, BV. So we can write this BV divided by, sir, BH is equal to, if you take it over there, we say, sir, root 3. Okay. BV by BH is equal to root 3. And we recently studied that BV by BH is tan delta. So we say tan of delta is nothing but root 3. When is the value of tan? When is the value of root 3 for tan? At what angle? At what angle? 60. Delta is 60 degree. Okay. Now, apparent dip. Sir, what is apparent dip? Listen to me very carefully. I'll make you understand what is apparent dip. See, apparent dip. See, my dear people. If we say this is a magnetic meridian, okay? And we say, sir, this is a geographic meridian. This one plane is geographic, this is magnetic. Angle between these two is angle of declination. Listen to me very carefully. If I say this is magnetic field B, if I say this is magnetic field B, can I say this is horizontal component of magnetic field? This one is BH, this one is BH, and this one is BV, this one is BV, okay? That is vertical component. Now you guys tell me one thing. See, sir, if this is BH, this is phi, can I say this component, can I say this component will be BH cos of phi? Guys, once again, this is sir B, this is sir B. This angle is delta. So we say, sir, this is BH, this is BH. Horizontal component of this, that is how much? B cos of delta, B cos of delta. Now, over here, we say this angle is phi. Can I say this has one more component? This has its horizontal. This is the horizontal component of this one. But this is the horizontal component of this one. That will be, sir, BH cos of phi. As simple as that. As simple as that. If this is BH cos of phi, now listen to me very carefully. Sir, over here, if you take a look at this plane now, this is one component, this is another component. Okay, vertical is same. This is the vertical for this plane also. This is the vertical for this plane also. This is vertical for magnetic meridian also. This is vertical for geographic meridian also. Let's suppose I'm taking a line over here. Let's suppose I'm taking this line. Okay. And I call this angle as a delta dash. I don't know how much this delta dash is. I am calling this as delta dash. I'm taking this line. And this angle, delta dash, I am making on geographic meridian or magnetic meridian. Let me know in the comments. This angle, delta dash, I am making on geographic meridian or magnetic meridian. Tell me. Am I making this delta dash on geographic meridian or magnetic meridian? Everybody. Yes, we say, sir, geographic meridian. So we say that angle which is made on geographic meridian is called apparent dip. Okay, it is that angle of dip. It is that angle which is made on, it is the angle of dip on geographic meridian. Okay, it is the angle of dip on geographic meridian. So we say, sir, when it comes to the angle of true dip, it is that angle which is made on magnetic meridian. And when it comes to the apparent dip, it is that angle which is made on geographic meridian. Okay. Now you guys tell me one thing. My dear people, listen to me. You guys tell me one thing. Okay. Listen to me. Sir, can we just do one thing in this particular case? Can we just do one thing in this particular case? We say, sir, this, I can write, sir, tan of this angle. See. In the previous case, you said, sir, tan of delta is equal to BV by BH. Over here, because tan theta is perpendicular by base. So similarly over here, tan delta is vertical by horizontal. Can we do the same thing in this case? We say, sir, tan of delta dash, tan of, we say, sir, delta dash is equal to, sir, that will be vertical by horizontal. Like over here, tan of delta is vertical by horizontal. In this case, tan of delta dash is vertical by horizontal. Vertical is BV. Horizontal is how much? That is BH cos of phi. BH cos of phi. Yes. Now BV by BH is how much? Sir, we just studied over here. BV by BH is tan delta. BV by BH is tan delta. So we say, sir, as tan of delta is BV divided by, sir, BH. So we say, sir, tan of delta dash is equal to BV by BH. Instead of this, I can write tan of delta divided by, we say, sir, cos of phi. This is the relation between true dip and apparent dip. This, where delta dash is the apparent dip, delta is the true dip, phi is the angle of declination. So you can say this is the relation between all the three. This is the relation between all the three over here. Is this equation clear, guys? Is this equation clear, guys? Let me know in the live chat. If this equation clear, guys? All the people out there, is this clear? Okay. Let's move on to this question. Now, in this case, if true angle of dip is given as a delta, okay, find apparent dip on any other plane such that angle between the plane and magnetic meridian is 60 degree. Okay, see, sir, we know as tan of delta dash, tan of apparent dip is equal to, we say, sir, tan of true dip upon cos of this phi, where phi is angle of declination. And in this case, clearly we can see angle between that plane and magnetic meridian is 60 degree. Angle between geographic meridian and magnetic meridian is called angle of declination, or angle between any plane and magnetic meridian, it is also called angle of declination. So over here, phi is given as 60 degrees. Okay. And you guys are supposed to find the apparent dip. True dip is given as delta. True dip is delta. Apparent dip we have to find. So we have tan of delta dash is equal to, we say tan of delta upon, we say, sir, cos of phi is 60, cos of 60. Cos 60 is 1 by 2. 2 will go in the numerator. We say, sir, tan of delta dash is equal to 2 times tan of delta. Okay. Or you can say delta dash is equal to tan inverse of 2 times tan of delta. Now come over here. This was the question asked in JEE Mains 2021. The apparent dip is given as delta dash is equal to 45 degree. And the angle of declination phi is 30 degree. Find the value of true dip. This was asked in JEE Mains 2021. As we say, sir, tan of delta dash, tan of apparent dip is equal to, we say, sir, tan of true dip upon, we say, sir, cos of phi. And in this case, phi dash is 45. So I can write tan of 45 degree and is equal to, we say, sir, tan of phi, tan of delta divided by cos of 30. We say, sir, cos of 30. Take it over there. So we say, sir, tan of this delta will be, if you take it over there, sir, cos of 30 plus, multiplied by tan of 45 degrees. Okay. So this will be cos 30 is root 3 by 2
and then you have, this is tan 45 is 1 into 1. So this will be tan delta. So we can say true delta is equal to tan inverse of root 3 by 2. Is this clear, guys? Is this clear, guys? Every one of you, let me know in the live chat. Now we have the vibrational magnetometer. Vibrational magnetometer. Is it clear? Let me know in the live chat, everybody. Class duration, now only it will take 30 minutes. Okay, in 30 minutes we are done. In 30 minutes we are done. Okay. My throat is gone, huh? Okay. It is -5, -6 degrees outside, and I'm just wearing this Unacademy jacket. That's it. And nothing else. No, we have to finish just in 30 minutes. How can I take the break right now? And have some tea break. Who is going to make tea for me right now? Okay. Let's take a look at this one. We say it is used to calculate the magnetic moment. It is used to calculate the magnetic moment. Let me just tell you how. It is a, you can say, kind of device which is used to calculate the magnetic moment of the magnets. Let's suppose we have a magnetic field over here. This is B. Okay, this is B. And in this magnetic field, you have placed a dipole. This is a dipole which you have placed in this field. Okay. Now, we say, sir, if you rotate this dipole, something like this. If you rotate this dipole, this is the magnetic field. And if you rotate this dipole, something like this. Okay. If you rotate this dipole, something like this. Now, sir, this is minus M, this is minus M, and this is, we say, sir, plus M. On this plus M, we say, sir, force will act something like this. On this minus M, force will act something like this. So it will again rotate. So when it rotates, when it comes back to the original position, so it will not stop over here. So it will start oscillating. It will start vibrating. It will oscillate. It will oscillate. Okay, it will oscillate. So when it oscillates, it will have the time period. When it oscillates, it will have the time period. Sir, we say over here, as we
displace the dipole, or as we disturb the dipole, it starts oscillating. Okay, so we say as we rotate the dipole, now it starts oscillating something like this. Okay, now as it starts oscillating, so it will have time period. What is time period? In how much time it will complete one oscillation. Like it is something like this. See, I'll tell you what is one oscillation. See, let's suppose this is a dipole. I'll show you. Let's suppose this is a dipole. I'll tell you what is one oscillation. This is the mean position. If we say it will go till extreme, something like this, and then it comes back. Okay, then it will go to the next extreme, then it comes back. This is called one oscillation. If I show you pendulum is at mean position. It will go till extreme and then comes back. Then go till another extreme and then comes back. The time it takes in this complete one oscillation is what we call the time period. So we say it will have time period, and that time period is equal to, we say 2 pi under root of I upon mb. So it will have, as if we disturb this magnetic dipole in this magnetic field, it will start oscillating and it will have the time period. We say, sir, that time period will be 2 pi under root of I by mb. Time period is in how much time it will complete one oscillation, where we say I is moment of inertia. This you might have studied in rotational motion, moment of inertia. Okay, and we say, sir, m is magnetic moment. We say, sir, B is magnetic field. Okay, like over here, B is the magnetic field, M is the magnetic moment of this dipole, okay, and I is the moment of inertia. Now this is how this vibrational magnetometer actually work. So we take a magnetic field over here, we place a dipole, and it gets displaced and it starts oscillating. Then we say, let's suppose its time period, we know we'll place the time period over here. We know its moment of inertia, we'll place it over here. We know the external magnetic field, we'll place it over here. Then we can find the value of this magnetic moment B, M. Then we can find the value of this magnetic moment M. Okay, this is how it helps us. Let me just give you the exact feel. Just a second. We say, by this vibrational magnetometer, you can also compare the magnetic moment of two dipoles. If you have, let's suppose, this dipole and this dipole, okay, and you guys are supposed to compare the magnetic moment of these two dipoles. Listen to me very carefully. How do we compare it? There is a long derivation. I am just telling you directly. Sir, we say, you can compare their magnetic moments. How? Sir, M2 by M1 will be equal to T1 by T2, its whole square. Let's suppose its magnetic moment is, let's suppose, M1. Let's suppose its magnetic moment is, we say, M2. Okay. And let's suppose its time period is T1. Let's suppose its time period is, we say, T2. In how much time it will complete the oscillation? In how much time it will complete the oscillation? So we say, sir, this is the relation. We say, sir, magnetic moment of second divided by magnetic moment of first is equal to, we say, sir, T1 divided by T2 and its whole square. If you know the time period of first one and second one, you can find the M2 by M1. It helps us to compare the magnetic moments of two magnets. Now we say if the two magnets are placed in opposite sense, over here the two magnets are placed in the same sense. Like south of this magnet is exactly over here, okay? South, north. They are placed in the same sense. But when it comes to the over here, another case, in this case you have south, this magnet, you have north from this side. You have north over here, you have south over here from this side. In this case, how do you compare the magnetic moments? This is the formula. We say M1 by M2. M1 is the magnetic moment of this one. T1 is the time period of this one. M2 is the magnetic moment of this one. T2 is the time period of this one. M1 by M2 is equal to T1 square plus T2 square divided by T1 square minus T2 square. Or you can also say, sir, T1 by T2 is equal to M1 minus M2 upon M1 plus M2. Okay, both of these. So use these formulas when the two magnets are placed in opposite sense, and use this formula when the two magnets are placed in the same sense. Is this clear, guys? Is this clear? Is this clear, guys? Now, let me give you the question on this one only. By solving the questions, you will get to understand. This was asked in NEET 2010. We are given a vibrational magnetometer placed in a magnetic meridian has a small bar magnet. See, we have a magnetic field B is equal to, we say, sir, 24 micro Tesla. B1 is equal to 24 micro Tesla. And in this, we have placed a dipole. We have placed a dipole. Okay. And this dipole has time period T1 is equal to 2 seconds. If you displace it, it will complete its oscillation in 2 seconds. Okay. And this magnetic field is 24 Tesla. Now, what you are doing is that in this case, you are afterwards. This is initially. So finally, what you are doing is that, sir, this was the 24 micro Tesla in the forward direction, and in the backward direction you are applying 18 micro Tesla finally. In the forward direction 24, in the backward direction we say 18 micro Tesla. And this dipole, you have the same dipole placed in this one. Okay, you guys are supposed to tell me what is the time period T2 in this case. You have got a dipole, you placed it in the 24 micro Tesla, its time period is 2 seconds. You have the same dipole, now in the same magnetic field 24 micro Tesla, but in the opposite direction you applied 18 micro Tesla. Can you tell me what is the value of magnetic field finally, that is B2? You say, sir, that is simply 24 minus 18. That is 24 minus 18. So B2 in this case will be 6 micro Tesla. This is B2. Okay. Now we know, sir, T1, B1. Now we know B2 and we are supposed to find T2. Listen to me very carefully. As we know, sir, time period is 2 pi under root of I divided by MB. I by MB. Now in this case one, we have got A magnet, a bar magnet, it has moment of inertia something. Now same magnet is placed over here only. So it has got the same moment of inertia. Now I is same. We say, sir, pi, I, it is same. Sir, magnetic, okay, magnetic moment. This magnet, they are same magnets. So M is same, M is same. In this case, in both the cases, M is same. So can we say, sir, in this case, time period is equal to 1 upon under root of B. So time period only depends upon the magnetic field because the rest of the things are constant. Now, if time period depends upon the magnetic field, we can write over here, sir, T1 is equal to 1 by B1, 1 upon B1 under root B1. Sir, in this case, T2 is equal to 1 upon under root, sir, B2. Okay. So we say, sir, T1 divided by T2 is equal to 1 by root B1 upon 1 by root B2. And if you reshuffle it, it becomes root of B2 by a root of B1. So further you can write over here, T1 divided by T2 is equal to under root of B2 by B1. Now what is the value of T1? Sir, value of T1 is 2, B1 is 24. So we say value of T1 is 2 and value of T2 we have to find out is equal to under root of value of B2. Sir, value of B2 is 6. We say, sir, 6 upon value of B1 is 24. Okay. Because B1 over here is 24. Now we say, sir, 4 ones, 6 ones, 6 fours. So this will be 1 by root 4. So that is 1 by 2. 2 upon T2 is equal to 1 by 2. Okay. Now take this T2 over here and multiply over here. T2 will be 4 seconds. So answer is 4 seconds. Yes, 4 seconds is the answer. Now we have the next question over here. The time period of oscillation of a magnet in a vibrational magnetometer is 2 seconds. The period of oscillation of a magnet whose magnetic moment is 4 times as that of the first magnet. Which option is correct over here? Let me know in the live chat. Which option is the correct option over here? Which option is the correct option over here? Which option is the correct option over here? I didn't say the question. See, the period of oscillation of a magnet in vibrational magnetometer is 2 seconds. Okay, it is not visible. Okay. Now in this particular case, what is given is that, listen to me very carefully. We say, in this case, we have the period of oscillation of a magnet. We have a magnetic field, okay? And in this magnetic field, we have placed a bar magnet, okay? And the period of oscillation of magnet whose magnet is 4 times that of the first magnet. This magnet has magnetic moment M, okay? And it has got the time period T1 is equal to 2 seconds. We have a bar magnet. It is placed in the external magnetic field. Its magnetic moment is capital M. Its time period is T. In how much time it will complete 1 cycle. And then we have another magnet. Its magnetic moment is 4M. Its magnetic moment is 4 times that of the first magnet. and you have to find its time period. What will be its time period? Tell me. Yes, yes, yes, yes. A lot of people are actually giving me the correct answers over here. One is the correct. I want everybody of you to tell me the correcto optiono in this case. And these two magnets are placed in the same sense, okay? Like this magnet is also over here. This magnet, this is 4m and it has got the time period T2. Just now, sir, as we know, we have recently studied this equation over here. The equation is basically T1 by T2. We can write T1 divided by T2 is equal to under root of, take the square over here, that is M2 by M1. Okay. T1 by T2 is equal to M2 by M1. And this is when the two magnets are placed in the same sense. So we'll be using this formula only. So we say, sir, T1 divided by T2 is equal to under root of M2 by, we say, sir, M1. Sir, T1 is how much? That is 2 upon T2 is equal to under root of, sir, M2 is 4M upon M1 is how much? We say, sir, M. This and this will cancel. Root 4 is, we say, sir, 2. So we can write over here, we can write in this case 2 upon T2 is equal to root 4 is also 2. So T2 will be 1 seconds. So this has the period of oscillation as 1 second. Next question. Can you solve this question over here? Can you solve this question over here? This one. It's a good question actually. Can you solve this question over here? It's actually a good question. It is not visible? Okay. We have got the two magnets. We have got the two magnets. We have got the two magnets. A and B. We have got the two magnets. They are geometrically similar, but magnetic moment of A is twice that of B. Magnetic moment of A is twice that of B. This is the magnet, okay? It has got the magnetic moment 2m, and this is another magnet. It has got the magnetic moment m. The name of this magnet is A, the name of this magnet is B, okay? With their like poles and unlike poles are capped together. If this is south, this is north. If this is north and this is south. Then if this has the time period T1, this has the time period T2. We have got two magnets over here, okay? This has the magnetic moment 2m, this has the magnetic moment m. You guys are supposed to tell me what is the value of T1 by T2 in this case. What is the value of T1 by T2 in this case? Everyone, solve it.
Yes, 1 by root 3 is correct. See, this is the case. I told you over here, when the magnets are placed in the opposite sense, like south with north, north with south, okay? This is what we say opposite sense. In this case, time period is, you can find the time period by this formula. T1 by T2 is under root of M1 minus M2 upon under root of M1 plus M2. Now in this case, you can clearly see, sir, south of this magnet is with the north of the another magnet. North of this magnet is with the south of another magnet. The two magnets are placed in the opposite sense. So which formula I'll be using? T1 divided by T2 is equal to under root of, we say M1 minus we say M2 upon, we say M1 plus we say M2. So we say, sir, T1 divided by T2 is equal to under root of M1 is how much? That is 2M minus M divided by, this will be 2M plus we say, sir, M, because it has got 2M, it has got M. Now we say, sir, 2, 1 divided by 2, 2, T1 by T2. It is nothing but 2M minus M is M. So this is under root of M divided by 3M. This and this will cancel. So it will be 1 upon a root 3. T1 by T2 is 1 by root 3, option C. Great, great, great. Types of magnetic materials, okay? This is the theoretical topic, small topic, okay? I am leaving this topic on you guys, okay? Okay, I am leaving this. This is a small topic, just a theoretical topic. Every detail is mentioned over here. Okay? Okay, guys, because my throat is gone now completely. It's a very small topic. You guys can do it easily. If not, I'll make a separate 10-15 minute video on this one and post it on the channel. Okay, that's not a problem. Like, we have three types of materials. See, let's talk. Let me just tell you susceptibility. SUSEPTIBILITY. Okay, susceptibility. See the spelling later on. Sir, this susceptibility means we represent it with chi. Okay, it is equal to, we say I divided by H. What does susceptibility mean? It means I means intensity of magnetization. Intensity of magnetization upon, we say magnetizing field. Magnetizing field. What does that mean? I'll tell you. Let's suppose you have a material over here. You have some material over here. And you want to magnetize this material. I have an iron over here. We say, have you ever basically did this experiment? That is, at your home, you have a magnet, okay? This magnet is attached with the coin, okay? Like you place it for, I say, 2 days, 3 days, okay? And after 3 days, that coin also started showing the magnetic behavior. It also starts attracting the pieces of iron. Have you ever basically, yes, coin is behaving like a magnet afterwards. So we say that's what we call the intensity of magnetization. If you are magnetizing, if this is a material, like you have this iron, okay? You want to magnetize it. You want to make this as a magnet. You want to make this behave like a magnet. It should also attract the things. So you do one thing. You place this magnet inside a magnetic field, in the external magnetic field, okay? So we say after some time, it will also start behaving like a magnet. So how much
it has magnetized. If I say you have placed it in this magnetic field, how much it has magnetized, that is what we call the intensity of magnetization. So it has magnetized more. Now it is like completely a magnet. It is attracting a small piece of paper, small piece of coins, everything. So we say intensity of magnetization is more. How much it has magnetized. And then you have magnetizing field. It is that field in which we are magnetizing the material. It is that field in which we are magnetizing the material. So we say intensity of magnetization is I is how much a material has magnetized. And we say, sir, H is the magnetizing field. H is the field in which we are magnetizing it. In which we are magnetizing it. This is what we call the susceptibility, or this susceptibility is also what we call, it is also what we call output divided by input. Input is the magnetic field you are giving. Output is the how much magnetized it has become. That's what we call the susceptibility. And after this we have this, we say the paramagnetic, these diamagnetic, three types of materials: diamagnetic, paramagnetic, ferromagnetic. Now you can read the details over here. I'll be sharing this PDF also with you guys. I'll be sharing the PDF with you guys, okay? So you read these, all the PDFs over here. This is paramagnetic, all the details, okay? That's it. Thank you, guys. Comment down below, okay? I'm ending the live stream, okay? My throat is gone. I want all of you, whoever is present in this one, okay? If you really want to thank me, then thank in the comments, okay? I want you guys to let me know how was the session actually, okay? Really, from your heart. Everyone, okay? Not in the live chat, in the comments when I end this this particular stream, okay? So thank you so much, boys and girls. The guys who are right now over here, this is the actual competition for the NEET, okay? Don't look at that, those masses, that crowd. This is the actual competition. So take care. Bye-bye. See you guys in the next one shot. Done and dusted for today. I think it's been 9 hours, I guess. Yes. So take care, guys. Thank you so much. Make sure you comment down below. I'll be waiting. Thank you so much.